Welcome back. In the last video, we downloaded a pre-trained EfficientNet B0 and adjusted it to our own problem. So we downloaded some weights, we set up a model using those weights, we set all of the base layers to have the requires grad attribute as false, so we froze them. Then we adjusted the classifier head and checked out a summary of our model, and we saw that most of our model is untrainable now. So let's train the part that is. And this time we're going to do it a little bit differently to what we've done in the past. So train a single model and track results. So the whole purpose of this notebook is to explore experiment tracking with PyTorch. But before we start tracking multiple experiments, let's see what it's like to track a single experiment. And to begin, we will define a loss function and an optimizer, just like we always do. Loss function is going to be nn.crossEntropy loss, because we're dealing with multi-class classification. And the optimizer is going to be torch.optim.atom, and we will optimize our model.parameters, and we will set the learning rate to 001, just to keep everything consistent. Now, if you went through the little challenge I set for you in the last video, how to use TensorBoard with PyTorch, you might have found that we can use a summary writer instance. So summary writer. So you can think of this, I like to remember this as like it's just writing a summary of whatever parameters you pass it. So let's explore this a little bit more, hey? From torch.utils TensorBoard import summary writer, let's just copy this out and see what happens. So set up a summary writer. So from torch.utils.tensorboard import summary writer. And then if we set writer is equal to summary writer, what do we get? What does this say? Well, that doesn't give us much at all, does it? How about we look up the documentation? Torch summary writer. Here we go. Beautiful. So before going further, more details on TensorBoard can be found at tensorflow.org/TensorBoard. Okay. So if we wanted to learn more about TensorBoard, we could look through here. Now this is the TensorFlow website, another deep learning framework, quite similar to PyTorch. So TensorBoard is TensorFlow's visualization toolkit. What can we do? TensorBoard provides the visualization and tooling needed for machine learning experimentation. Hey, that's us. Tracking and visualizing metrics such as loss and accuracy. Hey, we've seen loss and accuracy before. Visualizing the model graph, ops and layers. So ops is short for operations, but recall that a layer is also a collection of operations. Viewing histograms of weights, biases, or other tensions as they change over time. Okay, so during training. Projecting embeddings, displaying images, text, and audio data, profiling TensorFlow programs, and much more. Oh my goodness, there's a fair bit going on here. So if you'd like to learn more, I'll encourage you to have a look at this website. So I'm just going to link this in here. Let's get a few resources here. So to track experiments, we're going to use TensorBoard. So TensorBoard, so all of this information that we've got, this is important to note as well. And to interact with TensorBoard, we can use PyTorch's summary writer. So this is an important point, is that all of what we're doing here is not just like we've pulled this out of the air. Like this is documented. We're just going to be practicing it by writing code. So let's get rid of a few of these tabs and we'll just jump straight into summary writer. What do we have here? Summary writer. Do we have the documentation? Beautiful. So I'll just link to here. So that's going straight to the documentation. Also, see here. So summary writer. Ideally, what we'd like to end up with is, well, TensorBoard's website spelled it out for us. We want to track our loss and accuracy. So we want to get some loss curves, but visualize them in TensorBoard. Yeah, just like that. Epoch, loss and accuracy. So what do we have here? Summary writer writes entries directly to event files in the log.dir to be consumed by TensorBoard. So a log directory. So what this means is that the summary writer is going to help us track some metrics to file, which TensorBoard can use. So how about we see that in practice? But the thing is that where are our metrics? So if we were to call from going modular, import engine, and then if we go engine.train, what happens here? That's how we've previously trained models, right? Well, we've got some metrics already been printed out by the train function. So let's jump into going modular, and let's have a look at engine, which is where our train function is. A little bit confusing. We've got a train step, we've got a test step, and we've got train. So previously, we've been printing out a dictionary of our model's results. And you can imagine we could keep doing that, but if we were to build like 10 models and we wanted to track all of those dictionaries, that could get a bit hard. So what we'd like to do is track these programmatically and track them to files so that they're saved. And if we wanted to export them or view them with TensorBoard, we could. So let's see how we can use the summary writer to extract these values from the results dictionary and save them to file so that they're visible with TensorBoard. To do so, I'm going to rip the function out of here, the train function, and bring that into the notebook so we can alter it. But I'm going to import.engine because our train function from engine.py uses the train step and the test step function, we have to import those as well. And we also have to import the dependencies from here. Otherwise, what we're trying to do won't work. So I'll just bring those in here and I'll go back here and I'll go back into engine.py. So all I've done is I've imported these things and I'm going to copy the entire train function into our notebook so we can alter the functionality here. So that's all I've done. So I've got engine.py and I've got the dependencies of engine.py and I've got from going modular.engine, so this function or this Python file, import train step and test step. So if I alter this function, it's got access to train step here and it's got access to test step here. So what we want to do now is update this so it uses a summary writer. So let's add a parameter up here. We'll set this to, well, we've got device. What we might do is set this to writer. Or actually, can we pass in a writer here? What we might be able to do is just track it here. So let's go down and let's add new. That's what we want to do. So let's put in experiment tracking. We don't need a parameter just yet. We'll just set up a default writer because we've already set up a writer class up here. Let's see how we can use this in the train function. Writer, we will go writer.addScalars. Now, if you want to see this, we've got different methods here. Add scalar if you wanted to add a single value, or add scalars, adds many scalars. That's what we want to do. Recall a scalar is just a single number. And then we've got other things like add histogram, and we've got add image. We could track our images if we really wanted to. And then we've got add images. But let's just stick with scalars because that's what our training loss and training accuracy values are. And we're going to put in the main tag parameter, which is going to be equal to loss for one of them. So this is going to be the loss scalars. Let's go tag scalar dict. And so if you want the documentation for this, see summary writer, documentation for these parameters here. Tag scalar dict. We're going to pass in the values we'd like to track, train loss, as being the train loss values. So we've got that there. So this is just getting the train loss, and putting it in there. And then we can get the test loss and put it in here as well. And then we can finish off with global step. So global step is going to be tracking the values every epoch. So we're going to see what this looks like in a second. We just want to set up the writer to add some scalars to file. And then the main tag here, we want to also track the accuracy. We'll pass in a dictionary of our scalars. Now you might be able to guess what goes in here. We'll pass in the train acc, we need to do this as a string, string, and then we'll go train ACK here, and then we'll go train loss, and we'll pass in the test ACK. So that's all we've done. We've got a results dictionary, but we're also now tracking them to our writer. And our writer is the summary writer. And then we'll put the global step here is going to be equal to the current epoch, which is up here. We are looping through a range of epochs that gets passed in up here. Now, we could parameterize this. We might do this later on, actually, as I was hinting at before. Put a parameter here, so writer equals XYZ. We can put in a writer there. I'll let you do that if you'd like to try that for some extra curriculum, but we'll see that later when we run more experiments. For now, we just want to focus on tracking one. And I'll also show you there's another thing we can add, We can add graph, so we can see the computations our model goes through. So model equals model, and then we'll go input to model, which is just a demonstration of variables to go through our model, equals torch.randn. We just need a shape of random tensors to go through. It's just going to do one forward pass on our model so that we can see the computations as it goes through our model. And then finally, we're going to close the writer. So let our writer know we no longer want to track anything else. So writer.close and then end new. So a few steps there, but essentially all we've done is we've explored what TensorBoard is, a way to visually track machine learning parameters, different things. We saw that we can interact with TensorBoard using PyTorch's summary writer. And we see that the PyTorch documentation for that there. We then created a writer class with summary writer here. Now, by default, summary writer is going to track to a log directory. So the default is, here we go, logdir, save directory location. The default is it's going to save it to a file called runs, current date time, host name, which is the name of your computer. Now, we could change this to be logdir equals experiments, but we're going to see that later on. So we'll just leave it everything as default just to see what it looks like. So we've got a train function. Our original train function, we set up an engine.py, we imported it in here, and then we added some functionality here to write some information to our writer for the loss value, and write some information or some scalars to our writer for the accuracy values. And we can also track the computation graph of our model. So let's just leave that as it is. And in the next video, we're going to see what it looks like when we run the train function, our updated train function that is, and train our model. So you might want to give that a go and see what happens. What happens? Oh, we've got a runs directory. We've got one already. Look at that. Our writer has created a default runs directory for us. Okay, beautiful. So give that a shot. Use our updated train function just as we have in previous videos and see what happens. What gets added to the runs directory? We'll do it together in the next video. I'll see you there. 4, 3, 2, 1. Welcome back. In the last video, we set up a bunch of things to prepare for tracking a single model's results. We've got a loss function, we've got an optimizer, we saw what TensorBoard is, we investigated what PyTorch's summary writer class does, it allows us to interface with TensorBoard, and we saw that when we instantiate a writer, it creates a runs directory over here, and by default, it's going to be saving our logs, or whatever we've told the writer to save, to this folder here, which is by default the current date time plus some information about whatever your machine is called. So in our case, it looks like this Google Colab instance is called something like this string of numbers here. Yours might be different. It might be your computer name or something else. But let's keep going. We also adjusted the train function to add some values here to our writer. You might have given this a shot. I've set the challenge to you in the last video to train the model with our updated train function. So note, not using engine.py or engine.train since we updated the train function above. So previously, let's set the seeds before we start, and we'll save the results to a dictionary. Previously, we might have used something like engine.py, or sorry, engine.train. But now, because we've imported the train function from engine.py into here, we've got train here, we're just going to use this function. So I'll just rerun that again. And I'm just going to go train model equals our model, our efficient net B0 feature extractor. The train data loader equals what? The train data loader, of course. The test data loader equals the test data loader. And the optimizer is going to be the optimizer we created above. And then the loss function equals the loss function. And then the epochs equals 5. And then the device is going to be the device. So if all works well, this is going to save some information to our log directory, which is somewhere over here. So you ready? We're going to train our first model and track the experiments with TensorBoard. 3, 2, 1, let's go. Beautiful. Looks like we're getting quite good results with our feature extractor model already. 85% test accuracy. Is anything going on in the runs directory? Oh, there we go. Accuracy, train acc, train loss, test loss, train loss. Do we have the right thing? I think we do. Oh, oops. Okay, did you notice that? So we got train loss. We need to update this to be test acc. Okay, that would have been confusing. Let's rerun this. We'll try again. So this is going to resave everything to a runs directory. And the beautiful thing is it doesn't take too long to run. So let's just let this run. And if we refresh, we should have, okay, there we go. So we have accuracy, the test accuracy, the train accuracy, the test loss, and the train loss. Wonderful. So there we go. We get some pretty good results, close to 88% accuracy to finish off. Now, I wonder if we could go in here and then, do we have load extension? Or I'd like you, my challenge to you is we've got some files here. Now you'll see that these are saved as .tf events. Now I'd like you to give it a shot of how to view these with TensorBoard from within the notebook. So what you might want to search before the next video and we explore it together is how to view TensorBoard experiments in a Colab notebook. Because we're using Google Colab, you might be using something else. There we go. There's a good resource for you. Check that out, give that a shot, and we'll explore our model's performance results with TensorBoard in the next video. I'll see you there. How'd you go? Did you view our model's training results with TensorBoard from a Google Colab notebook? I hope you gave it a shot. Otherwise, let's check it out how we can do it. So I'm going to create a new section here called number 5, view our model's results with TensorBoard. So previously we had the results dictionary, and if we had a look at this, results, we could plot the loss curves of that. But as we've been talking about, the whole purpose of experiment tracking is to track experiments programmatically. So let's see how we could do that with TensorBoard. There are a few different ways. One is to view it from right within the TensorBoard notebook. Or if you go into PyTorch experiment tracking, and then if we go to view our model's results in TensorBoard, there's another way to do it using VS Code. So you can set it up there. I've got a resource for you there. But since we're using a Jupyter and Colab notebook, or Colab that is, we can view it directly from within our notebook. The third way is you can also upload your experiments to tensorboard.dev and reproduce what's in the notebook in a public way. So a few options there. I'm going to leave them there as extracurricular. We're going to focus on viewing it from within a notebook. So to do so, let's view our experiments from within the notebook. And what I might do is, before I forget, I'll just link this here. There are a few ways to view TensorBoard results. see them here. I'm just going to link this section here so that you can reference something. Beautiful. So we're going to use the magic here, load extension in Colab. Now, this requires TensorBoard to be installed. If you don't have TensorBoard, if you're running this locally, you might have to install TensorBoard. And how can you figure out how to do that? So how to install TensorBoard? How do I install TensorFlow's TensorBoard on PyPy? There we go. However, Google Colab already has TensorBoard installed, so we don't need to install that. That's one of the benefits of using Google Colab. And then we're going to go TensorBoard. So we're loading the extension here. And then TensorBoard, we're going to use this parameter here. The log directory that we want to view is runs. So by default, we saw that PyTorch's summary writer, if we look in here, summary writer, saves to a folder called runs, and we haven't changed that. So we're just going to keep that as runs. Yeah, logdir by default is runs, and then something, 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 current, date, time, host name. So that's all we're going to do. Now you ready? The magic of TensorBoard. Let's see if it worked. Launching TensorBoard, it may take a minute or so because, as you'll see, TensorBoard is quite the visualization tool. I'm just going to give us some more space. Here we go. So that took a few seconds. Oh, look at that. How beautiful is that? It's so interactive already. And we've even got do we have a dark mode? We have a dark mode. How cool is that? Browser default. I'm just going to leave that like that. And you might notice this refresh button. This means that TensorBoard can be updated. So say our model was training for quite a long time. You can update TensorBoard live in the browser every 30 seconds or so, or just by clicking this. Now, there's a fair bit going on, and the best way to figure it out is to explore it. So I'm going to encourage you to explore most of this on your own, but let's look at a few things such as what we just tracked. So I'm in the Scalars tab here, which is where this came from up here. Writer.add scalars. So this is, we're viewing the scalars that we tracked. I like to turn smoothing off. What it does is it just makes these lines a bit smoother, but I like to just put it all the way down to 0 because that's going to give us just the raw numbers instead of like averaging them out or something like that. You can play around with this. So we've got over here a bunch of our different runs. So let's focus on just viewing the test data. So we've got June 27, that's the date that I'm running this. So I want to keep loss, test loss. I want to keep that there. Train loss, I want to get rid of that. You might notice, look, see, train loss goes away. And then accuracy, train accuracy, I want to get rid of that. I want to get rid of the train loss. I want to keep the test accuracy. Beautiful. So this is our test data set. Now we can press Alt and scroll out, in and out here. Oh my goodness, it goes quite up and then quite down. So that's the benefit of smoothing. If we smooth this out, what does this look like? Yeah, that's what happens with smoothing. And the same with the loss. That looks like it's going down and it's going up. Now let's bring the train back in. Loss, train loss, and accuracy, train ac. So if we zoom out, so it looks like our test accuracy is quite a bit higher than our train loss at the end. And then if we go down here and if we zoom out a little bit by holding Alt and zoom out, this button doesn't work too well for me all the time because I think the browser's a bit too zoomed in. But there we go. It takes a bit of a fiddling around to get your optimum view. But we see here the loss curves are slowly, I mean, if we kept going, they're heading in the right direction. It looks like here that the test loss kind of goes up towards the end. So that might hint at overfitting. So recall that overfitting is when the training loss is lower than the test loss. That's over here in section 4. We can look at the loss curves. I believe it is section 4, maybe section 8. So if we go down here, what should an ideal loss curve look like? Yeah, there we go. Looks like towards the end, our model is starting to overfit. So a few things that we could try out there, how to deal with overfitting. I'll let you look into those. But this is the crux of what we're looking at. We've now got TensorBoard, a way to programmatically view our experiments. And you can see here that if we ran a bunch of experiments, we can start to toggle them on and off. And if we wanted to search here, so say we only wanted the test values, we can just look at the test values. And say we had multiple different runs, we only wanted the ones that went for 20 epochs. You could use 20 epochs as a way to search different things. We've got along here, this is the number of epochs our experiment went for. We've got some values there, such as how many steps it took, the time it went, and the relative time, the compute time that it took. And then one more thing I want to show you is the graphs. So this is our model here. We've got an input. Let's have a look from the input. This takes a little bit of playing around with to get used to. There's our image data, 32 by 3 by 224 by 224. There's our efficient net model. So if we open that up, we've got 3 blocks. So we've got sequential, which is the features. Then we've got adaptive average pool. And then we've got the classifier. And if we jump into this, what do we see in here? Well, there's our dropout layer. And there's our linear layer. So we've got weight, bias. It's going in there. I'm trying to scroll and look at this at the same time and talk. There's a fair bit going on. Hold Alt and scroll to zoom, this is. So there's our weight and bias tensor is going into the linear layer. And then the output here is, what do we got here? We can just click on all of these nodes. And then if we really wanted to dive into, we've got this sequential. We drag this. This is what our efficient net model is made of. So we can jump in. We've got conv2D norm activation. We've got a conv2D layer. We can see what happens inside there. We've got a batch norm 2D, and we've got a silu. So if you want to explore what these are, you can look at the structure of many different models with TensorBoard. This is how valuable of a tool it is. Not only can you view your model's training results, you can inspect your model's architecture. And of course, how could you find out anything more about what this is? So how could you find out about batch norm 2D? Well, PyTorch batch norm 2D. Here we go. There's the documentation. Applies batch normalization over a 4D input. And if you're like, what's batch normalization? Well, there's a paper there if you would like to read that, or you can go, what is batch normalization? A gentle introduction to batch normalization for deep neural networks. So this is how you can be exploratory. You can experiment, not only with training different models, but inspecting different models. So that's just a little hint at what the power of TensorBoard can offer. If you'd like to track more things with your summary writer, I'd encourage you to look at the documentation. You've got add scalar, that's a single value. Add scalars, we've seen that one, we've used that one. We've got add image if you wanted to track some images. We've got add images. Add figure, add video, add audio, add text. There's a whole bunch of different things you can try out. But that is enough for now. And I think my browser's a bit all over the shop here. We've viewed the experiments of one model, which is our model up here, this one. But how would we view multiple experiments? So let's tackle that in the next video. We'll alter the train function to take in a writer parameter so that we can update our writer class on the fly. Let's see how to do that in the next video. We've only really scratched the surface of what's possible with TensorBoard, but rather than go through everything, I'd rather you explore the other things that you can do with TensorBoard. What we're focused on in this section is tracking our model's experiments programmatically, and we've seen how to do that with one model. Let's now start to write some code to do that for multiple models. So I'm going to create another heading here. It's going to be number 6 is create a function to prepare a summary writer instance. Now, what if there were some other things you'd like to append? Because by default, I just want to write this down. By default, our summary writer class saves to the logdir parameter. Now, ours is right now just runs / current date / hostname or underscore hostname, hostname being the name of the computer that you're running it on. And I'm running it on Google Colab, so it's given it this name here, this unique identifier. It might be your own personal computer name if you're using it there. Let's write here, how about if we wanted to save different experiments to different folders? So what I mean by that is one way of tracking experiments and keeping them separate is, in essence, one experiment equals one folder. So let's say, for example, we'd like to track, I think the date time is a good thing. So the experiment date / timestamp, so we know when the experiment was run. And the experiment name, so we'd like to call it something specific. And then maybe the model name that we used. So in case we use a different model architecture. Right now we're using EfficientNet B0, but what if we change that to EfficientNet B2? And then extra. Extra could be anything else. Is there anything else that should be tracked? Now, I want to emphasize that there really is no limit to how you could name your folders for your experiments. There is really no set way of how you could track them. This is just one way. So as many different experiments as you could run, there's as many different ways as you can track them. So this is just to give you an idea of how you could track your experiments and keep them separate. So let's create a function to create a summary writer instance to take all of these things into account. So ideally, we end up tracking experiments to a directory, and we want to call it, let's say by default it's going into runs, and then we do a reverse year, month, day, timestamp. And then you could put the time in there if you really wanted to. I'm just going to keep the date. Experiment name, model name, and then extra. So, and that way, every experiment is going to have a unique name of this. So let's give it a go. So def create writer, that's what we'll call it. Experiment name. We'll take that in as a string. The model name, that can be a string as well. And then the extra, we'll use that as a string. And by default, we'll set this to none. So we need an experiment name, and we need a model name, and we need a timestamp. They're going to be our three defaults. So let's just put in the little doc string here. Creates a torch.utils.tensorboard.writer.summary instance tracking to a specific directory. So one experiment, one directory. And then we can view that in TensorBoard later on. That's a little bit of a spoiler. So from datetime, import datetime. We're going to get the timestamp first. Import OS. And we'll get timestamp of current date in reverse order. So we want year, month, day. So the timestamp is going to be timestamp equals, we'll use the datetime module here, datetime.now, which means right now. So let's have a look at what this looks like. You might have already used datetime before. If not, just want to give you a little import datetime, from datetime, import datetime. And if we go datetime.now, I believe this is the number of seconds since, oh no, this is right now. Okay, beautiful. And then if we do that, this is going to update. Then if we do that, it's going to update. It is the 27th of June, 2022, right here in Australia. So let's go string f from time. And we want to get it in the format, I believe, I always get this mixed up, but I think it's just year, month, percentage day, return. So well, let's just see if that works. Timestamp, we'll just make sure. Yeah, beautiful, that's what I want. So reverse date time, and we're going to go if extra, let's go create log directory path. So this is going to be logdir. We will take in the os path.join. This is where os comes from. So we're going to join the timestamp, the experiment name, the model name, and extra if extra exists. So we'll save it in runs. We'll keep that by default. Timestamp, we don't need to stringify that. It's already a string. Experiment name should already be a string as well. Then we'll get model name and then extra. And then else, if extra doesn't exist, well, the logdir will just be everything except extra. There might be a more elegant way of doing that, but that'll do for now. Logdir. So let's test this out, hey? We will go create writer equals, and we might print out a little info here, just so we know. Print info. Let's go creating, or created by now. Created summary writer, saving to logdir. Return logdir, create writer equals create writer. Oh, excuse me. We'll go here, example writer equals create writer, and then we'll pass it in the experiment name. We can call this one, let's go data 10%, because right now recall that the data we are using is 10% of the Food 101 data for the classes pizza, steak, and sushi. The model name that we're using is EfficientNet B0, and the extra, we'll just keep it here that we're training for 5 epochs. And then we'll have a look at the example writer. Example writer. Oh, it didn't print out our info. Beautiful. Created summary writer, saving to runs, date, data 10%, EfficientNet B0, 5 epochs. So then, if we were in TensorBoard, we could filter by, say, everything that's ran for 5 epochs, or everything that's used data 10%, and it will show our runs there. So let's get rid of that. But I've just noticed this is just a string. We actually want to make sure we return a summary writer. So I'm just going to import here from torch.utils.tensorboard, import summary writer, and I'm going to create a summary writer instance. Summary writer and logdir parameter is going to be equal to logdir. And now this should update. Beautiful, there we go. Okay, that's what we're after. So now, do you see the power of where we're heading towards? We've tracked one experiment, but now we've got a programmatic way to track multiple experiments. So we could update these on the fly. We could put this functionality into our train function up here. Into this function. So we could put a parameter here called writer, and then every time this train function is called, it creates a new writer and saves to a particular writer folder, which is going to come over under here. And in fact, you might want to give that a go. See, there's the one we just created. 27th of June, 2022, data 10%, FNet B0, 5 epochs. How cool is that? So this is going to be one experiment. And this might even be in TensorBoard already. Let's have a look. If we refresh this, TensorBoard, refresh, do we have our latest run? I don't think it will because it doesn't have any files in there. Oh yeah, there we go. Data 10%, FNet B0, 5 epochs. So see, this is a live TensorBoard viewing session happening. We can update that on the fly. So there's nothing in here yet, so we can't view any experiments, but I'm going to give that to you as a challenge. Update our train function to be able to use our create writer function. So over here, update train to use create writer. That's your challenge for the next video. So that way we can programmatically track multiple different experiments. Give that a shot and I'll see you in the next video. How'd you go? Did you update the train function to be able to use the create writer function? Now, I might have confused you a little bit because it's not necessarily going to call the create writer function directly. It just needs to have access to be able to use it. So let's have a look at what that looks like in this video. So 6.1, update, slowly working towards our mission. So update the train function to include typos galore, Daniel, include a writer parameter. Now, we're slowly working towards our mission of being able to track experiments programmatically, which is very important as you start to build more and more machine learning models. So let's copy all of this. So we'll come back down here. Previously, our train function had ability to just track to one writer, but we want to track to multiple if we want to run multiple experiments. So this is just to reiterate. We are importing the dependencies from engine.py. All I've done is I've copied in from going modular. I've copied in the imports, and we need to import train step, which is what we're doing here, train step, and we need to import test step, which is also what we're doing here. And I've just copied in the train function, the whole function, so we can adjust it to use a summary writer. So I'm going to get out of all that. That's all I've done. So from going modular to going modular engine, import train step and test step, because the train function leverages train step and test step. So we had here writer. It's going to save some scalars for loss and accuracy, and it's going to save our model graph, and then it's going to close the writer. So we really only have to tweak something minor here, and I've hinted at it before, writer. So this is going to enable us every time we call train to pass in a writer, and that writer could have been one that we created programmatically. So let's give a little hint. This is going to be a torch.utils.tensorboard.writer.summary writer, and it's this here. That's just what I've copied in there. That's all we have to add there. And so now let's create a if clause. So if a writer exists, if writer, so if that writer exists, well, we might set that to, should we set that to default none? I don't think it should matter. If writer, let's save, I'm going to tab with this, just tab, and then close the writer. Maybe this needs to be up here now. Tab, tab, tab. Make sure our lines are in line there. And then else pass. So if a writer exists, what have we got wrong here? Okay, so if our writer exists, we track some information to it, and then we close it, and then we pass if it doesn't exist. But now we could pass in to this writer parameter a create writer function, our create writer function that we just made. So we are now primed to set up a series of modeling experiments. In fact, you might want to jump ahead and try this out. You might want to set up, I might just get this heading here ready, is number 7, is setting up a series of modeling experiments. So if you want to jump ahead, you can go into this section, number 7, and see some ideas for different experiments you could run. But my challenge is to set up 2 times modeling experiments with fnet b0. So same architecture, pizza, steak, sushi data. So pizza, steak, sushi data. So our data that we have, and train one model for 5 epochs and another model for 10 epochs. So you might be thinking, I might have to create a list of epoch values, and then in that list, write a for loop to go through and run train twice, once for each epoch value. So give that a shot, but otherwise we'll start moving towards setting up a series of modeling experiments. But my little challenge for you, if you want to jump ahead, is try to start with 2 to begin with. I'll see you in the next video. Welcome back. In the last video, we ended on a little challenge here, and that is we're going to start setting up a series of modeling experiments to programmatically track our food vision mini experiments. And the challenge I left was to set up 2 times modeling experiments with EfficientNet B0, so a feature extractor model, the pizza, steak, and sushi dataset we've been using, and one experiment would be for 5 epochs, and then another experiment would be training for 10 epochs, and then compare their results with TensorBoard. So I hope you gave that a go. If not, let's start moving towards setting up a series of modeling experiments we're not going to do this one per se. We're going to set up a larger series of experiments because why not, right? Let's see what we can do. So 7.1, what kind of experiments should you run? So this is a little bit of an overview video. So we're just going to discuss some different options. So the number of machine learning experiments you can run is like the number of different models you can build. Almost limitless. However, you can't test everything, of course. So what should you test? So anything that you can imagine that is some form of hyperparameter, you can try to test. So change the number of epochs. You could change the number of hidden layers / units. You could change the amount of data. So right now, we're using 10% of the Food 101 dataset for pizza, steak, and sushi. You could increase that amount of data, or you could collect more data if it's not easily accessible to you. And this is actually one of the best things to do in terms of machine learning because generally more data equals better. And so if we go into the course GitHub, PyTorch Deep Learning, then if we go into extras, number 4, custom data creation. This is how I created the 10% pizza, steak, sushi dataset. So it creates a dataset like this. It uses Food 101 from Torch Vision, this one, or Food 101 here, and then creates a split. So we download the training data from PyTorch and then creates a split based on how much we dictate here. There's also a 20% split, but you could increase this as well if you wanted to run more experiments. The reason why I started small is because in machine learning, you want your first experiments to run quite quickly before you scale things up. Because if you scale things up and the compute takes a long time and it turns out to not work, well then you've wasted quite a bit of time there. So what we're doing is slowly progressing towards running a series of modeling experiments that run within a few seconds or a few minutes max before we go and use, say, the whole Food 101 data set. And in fact, after we've covered everything in this section, that might be something that you go and try yourself. Then you can, of course, change the learning rate. Then you could try different kinds of data augmentation. There's really no silver bullet here. This is what we're going through in terms of what you should experiment with is actually possibly the main question of machine learning. What makes the best model? That's what all of the research is going towards in machine learning. How do you improve your models? So if you're looking at this and going, wow, there's so many things to keep track of, well, that's the wonderful world of machine learning. Choose a different model architecture. We've seen a fair few model architectures now in Torch Vision. Well, we haven't been hands-on with them, but we've seen that there's a fair few pre-trained models that we could try. We've only used EfficientNet. So maybe you want to try a different one of these. In fact, that's another good extension that you could try out. So if you want a visual overview of what we're doing, this is the model we started with so far. Potentially we might use EfficientNet B2 or B1 or B3, increase this number, see if it does any better. Then what experiments should you try? Just to reiterate, try to change the model architecture. Try to train for more epochs. So you might find that if you cut off here, your loss value could have actually gone lower if you trained for longer. Increase the amount of data you're using. Add data augmentation if your model is overfitting. Try mixing up the learning rate. Right now, we've just been using a stock standard Adam learning rate of 0.001, but you might want to change that to something else. Or even look into learning rate scheduling, which changes the learning rate over time. And then you can also change the number of layers / hidden units. So these two are closely tied together, model architecture and number of layers / hidden units. But truly, what experiments should you try? Well, all of these, plus any hyperparameter you can think of. So with that being said, there's a lot going on here in terms of experiments you should try, which is why I'm such a big advocate for using transfer learning. Because this is why transfer learning is so powerful. because it's a working model that you can apply to your own problem. So there's a few things to keep in mind. We're going to start designing some experiments around all of these over the next couple of videos. So I'll see you there. Now we've discussed what kind of experiments should you run, let's map out the experiments we're going to try. So 7.2, what experiments are we going to run? So in light of all these, we could test all of these things, but we're going to keep it simple, and I want you to start imagining every little hyperparameter, every setting in a machine learning experiment could be like a little dial. So we're going to turn 3 dials here. We're going to turn 3 dials, and the first one is model size. The second one is dataset size, and the third one is training time. So in lieu of model size, we might use EfficientNet B0 versus EfficientNet B2. In dataset size, we might use 10% of pizza, steak, sushi images versus 20%. And for training time, we've trained a lot of models for 5 epochs, so we might go 5 epochs versus 10 epochs. And now, of course, we are definitely not limited to just running these, but in my experience, these 3 factors are often some of the biggest influences of your model results. So model size, this is in terms of number of parameters. And this is dataset size. So generally, more data equals better results. And generally, longer training time equals better results up to a point. So that's a little caveat there, is that you might think, well, why are we stopping at 10 epochs? Why don't we do 10,000 epochs? Well, generally, it goes, say you wanted to train for 10 epochs. If you train for 20 epochs, you might get better results. But if you train for 100 epochs, your results might start to degrade. So up to a point. But to begin, we're still keeping things relatively small so that our experiments run quickly. Now, that's a very important point. We don't want to be waiting here all day for different modeling experiments to run. We want to quickly test a bunch of different things such as model size, dataset size, and training time and see what is worth pursuing. So if we're waiting here for hours, it's going to take us a long time to figure out what doesn't work. So why did I pick EfficientNet B0 versus B2? Well, if we come into the Torch Vision documentation, and then if we go here, you could truly pick almost any of these models to compare against each other, but I've decided to stick within the EfficientNet family, EfficientNet B0, and there's B1, B1 again with V2 weights, and there's B2 here. The reason I've decided on B0 and B2 is because B2 is about double the size. Not exactly double the size, but it's close enough. We could do B3, we could do B4, we could do B5, but recall, what is our overall goal of our Food Vision Mini? We'd like to build a model that's not too big so that we could deploy it to a website or a mobile device. Because if someone is taking a photo of their food, they're probably going to do it on their phone. So we can't use a model that has a ridiculous number of parameters. Although it may perform better, it might not fit on a mobile device, such as this big model here. It's got 600 million parameters versus our 5 million for EfficientNet B0 and 9 million for EfficientNet B2. So in lieu of all that, let's check out the keynote. What experiments should you try? Model architecture, this is what we're going to be trying. Tweaking this dial. We're going to be tweaking the epoch dial. And we're also going to be tweaking the amount of data dial. Now, of course, we could try these other things here, but I'm going to leave that to you to explore, such as tweaking the learning rate over time or adding in data augmentation. So let's get an overview of what we're going to be running. We've got experiment number here, the training data we're using, the testing data. Something to note here is that we're going to be using the same test set for every experiment. That way we can compare apples to apples. If we used a different test set for every experiment, well, then it's hard to really evaluate which experiment did the best. So we start off with 10% training data, so just the experiment that we've already run. Efficient net B0 for 5 epochs. Then we keep the data set the same, we change the model, we keep the epochs the same, use efficient net B2. Then we train with 10% training data again, use efficient net B0 just like 1, and 10 epochs. And we slowly start working towards number 8 here, which ends up being double the amount of training data as experiment 1, double the model size or thereabouts as experiment 1, and double the amount of epochs. So do you see the trend that we're following here? We're slowly increasing as we go. So hopefully running these experiments is going to show us some insight into which one of these combinations works the best. Now, if you had to guess of all these experiments, what do you think is going to perform the best? Will it be a smaller model trained for longer? Or will it be a model that has more data, more parameters, and trained for the longest? I'll leave that to you to think about. But let's now, in the next video, start to prepare our data set. So we need a 10% training data set and a 20% training data set. I'll see you in the next video. You ready to run some experiments? So we've discussed what experiments we're going to be running. We're starting with 10% training data, efficient net B0, and 5 epochs. And then we're slowly going to scale things up. We're going to slowly double the data, slowly double the model size, and slowly double the number of epochs, so doubling the training time. So starting small and scaling up when necessary. So let's jump back to our notebook here. And I've just got a note here. We're still keeping things relatively small so that our experiments run quickly. The quicker the better, so that we can work out what doesn't work, so that we can spend more time on what does. And what is our goal? A model that is well performing, but still small enough to run on a mobile device or web browser. So Food Vision Mini can come to life. So we need our model to be able to run on a smaller device. Now, if you had, I just want to put a note here, if you had infinite compute plus time, you should basically always choose the biggest model and biggest data set you can. And that's the bit of lesson, right? Or a general method as well. That's another thing. So the bit of lesson, I think I've mentioned this before in a previous video. See here. But that's some extra curriculum for you. Let's create some data sets, shall we? 7.3, download different data sets. Now, we've already got the 10% data set, but just for completeness, we're going to re-download it. So if we look over here, we've got data, pizza, steak, sushi. There we go. Now, if we did start with, if we come over here, if we did start with the whole Food 101 data set, we could quite easily download this from PyTorch using torchvision.datasets food 101. But I would still encourage you to even split out a random set of this, even if you have access to the full data set already. When you first begin, because this is 101,000 images, you want to keep your experiments quick. I can't stress that enough. Otherwise, you'll be sitting there all day waiting for a model to train. Once you figure out something that does work, well, then you can leave your model training all day and go to the gym or go for a walk or something like that. But to begin with, try to split out a small portion of whatever data set you're using and practice on that. And just a little reminder as well, if we go back to GitHub, this is the data sets we're downloading. Pizza, steak, sushi, there's the 10% version, and this is the 20% version, created in the same way as this one, but it just has doubled the amount of data. And if you'd like to see how they're created, I'll just get this notebook here, custom data creation. Takes the Food 101 dataset and splits it. So we want 2 data sets, which is 1 pizza, steak, sushi 10%, 2 pizza, steak, sushi 20%. So double the data. They were created with that notebook there, and we can go into this, PyTorch Deep Learning, data. We'll just copy the download link for this. You could download this locally. I'm going to write some code to download this into the notebook. So there's that link there. What I might do is while I've got that link, I'll just copy this one while we're here. Let's get up there. Oh, we need the raw link. So just make sure if you're downloading from GitHub, you use the raw link. There we go, raw. Beautiful. So let's download these data sets. And lucky us, we wrote a function up here to download data. So we can pass our link to our download data function. So let's try it out. We'll go back down to where we were. And we will create an image path. So we'll download the 10% data first. We don't have to do this, but we're going to just do it for completeness. And 20% data sets. So we'll create data 10% path equals download data. And the source is going to be equal to this link here. And then the destination is going to be, let's just create it as the same folder it already is in, pizza, steak, sushi. And then we'll create the data 20% path, which is going to be equal to download data source equals 20%. And then we will set the destination. We'll create a destination for that one. We'll just save it to pizza, steak, sushi, 20%. If I could spell percent right, that'd be amazing. So let's see what happens when we run this. So it skips the 10% because we've already got it. That makes sense. And then it didn't find the pizza, steak, sushi 20% directory, so it downloads and unzips that. We should now have, we've got those two data folders there. So you know what the next step is. We have to now turn these data sets into data loaders. And luckily, we have a script to help us do that in datasetup.py. We've got create data loaders. So that's my challenge to you for the next video, is to turn these data sets. Oh, what have I got going on? I've rearranged my window here. I'm going to fix this, but your challenge is to turn these two data sets into data loaders. And just recall, we're going to use the same testing data set, so the pizza, steak, sushi testing data for all of the experiments. So you only have to create one test data loader. So give that a shot, and we'll do it together in the next video. How'd you go? Did you manage to turn our data sets into data loaders? Well, I hope you gave it a shot. If not, that's all right. Let's give it a go together. We're going to transform data sets and create data loaders. So just as we've done before, we'll need to transform our data in a few ways. So because we're going to be using pre-trained models, namely EfficientNet B0 and B2, these have been pre-trained on ImageNet. So what do we have to do? We have to format our training data, our custom data, into the same format that these models were trained on. So let's go ahead and go, we need resize the images. We're going to use 224, 224. We need to make sure image tensor values are between 0 and 1. And this is not the case just for image data, by the way. This is often the case for any type of data you're working with if you're using a pre-trained model. So text or audio or something like that. And then finally, we need to normalize the images so they have the same data distribution as ImageNet. And so we've seen a few different ways of how to do that. If I jump back up, the normalized transform, we've done this before, so I'm just going to copy this down here. We need to create the data paths, don't we? So we'll just set up normalize there. And now let's create the data paths for each of our data sets. So set up training directory paths. We'll go train dirt. We'll start with a 10% equals data 10% path /train. So this is this path here. That has come from our download data function, which we created earlier. And then we're going to go train dir 20% equals data 20% path slash train. So that's the training paths. Now let's set up the test directory. We only need one test directory path because, as we've said in our experiments, we're using the same test data set for all of our experiments. That is to keep our evaluation consistent. If we were using a different test data set, we wouldn't really know which, if we tweaked one of these knobs, we wouldn't know which setting offered the best benefits. So let's go down here, set up the test directory. We will go test dir equals data 10% path slash test. We only need one test directory. And then let's check out the paths. Train dir 10%. Train dir. We'll just make sure these are all correct. And then test dir. Pizza steak sushi train. That looks correct to me. Pizza steak sushi 20% train. And pizza steak sushi test. Beautiful. So now we can create a transform. So let's jump in here and we'll go from Torch Vision. Let's import transforms. And then we'll set up a manual transform pipeline here. We could use an automatic transform, but we're going to keep things consistent by using our own manually created one. Compose transforms into a pipeline. We'll go simple transform equals transforms.compose. And in here, we're going to call transforms.resize. So both of our models will use the same transform pipeline. Transforms.toTensor, make sure our images are between 0 and 1. And then we'll put in the normalize transform here. Beautiful. So we've seen this before. Let's now create our data loaders using our, we go into here, our ever faithful data setup script, and we're going to use create data loaders. This is opening in a new way. I haven't seen this before, but this is the function we want to leverage. Let's get out of that. And we will go here. So let's set a universal batch size equals 32. And we'll go create 10% training and test data loaders. So train data loader 10% and test data loader. We can call test data loader just plain old test data loader because we're using the same test data set across all of our experiments. Data setup.create data loaders. And then I'm going to set the train dir is equal to train dir 10%. So I'll put that there. And then the tester is going to be equal to the test directory. The transform is going to be the simple transform we created in the cell above. And then the batch size is going to be equal to the batch size. Beautiful. So now we can do the same thing, but with the 20%. So I'm just going to copy this. It's the same code, but we need to just change the path. So this is going to be train data loader 20%, same test data loader. So it doesn't really matter if we change this, because this is going to create it with the test directory path here, which is this one here. We've only got one test directory path. So we're just going to update this to be training dir 20%. And then let's have a look at, we'll print out a little bit of the difference. So number of batches of size, we'll go batch size in 10% train data. And then we'll go length. We'll get the length of the train data loader 10%. Just to make sure our training data sets are, one is bigger than the other. So there should be double the amount of batches in the 20% training data loader. And then we could do this one more time for in 10% test data, because we only have one test data loader. We'll go test data loader. Test data loader. And then we'll go print f class names, and we'll just make sure our class names is correct. Beautiful, look at that. So number of batches in the 10% training data, we have 8. And number of batches of size 32 in the 20% training data, we have 15. So just under double. It won't be exactly double because 32 might not exactly fit into the number of samples we have, but that's close enough for me. And then we have number of batches of size 32 in the 10% test data is 3, that's okay. And then pizza, steak, and sushi. Looks like we're all ready to go. We've got some data loaded. Now, what's the next step? Well, it's time to create some models. So we've already discussed this. We're going to be using EfficientNet B0 and EfficientNet B2. My challenge to you is to create 2 functions that are going to return feature extractor models for EfficientNet B0 and EfficientNet B2 that we can use with our experiments. Because we want to create them as a function so that for each experiment, we're instantiating a new instance of the model architecture and not just retraining one from a previous experiment. So give that a go. We want one function to create an EfficientNet B0 feature extractor, just like we have in the previous videos, and another function to create an EfficientNet B2 feature extractor. I'll see you in the next video. How'd you go? Did you create some functions to prepare our EfficientNet B0 and EfficientNet B2 feature extractors? I hope you gave it a shot, but if not, let's do it together and we'll compare code, hey? Create feature extractor models. So we've prepared our data for our experiments. We've got 2 data sets, 10% data loader and the 20% data loader. Now, what we want to do for our feature extractor models is we want 2 functions. So one is going to be create a torch vision.models.efficientnet B0 feature extractor with a frozen backbone / base layers and a custom classifier head. And 2 is going to be basically the same thing as number 1, except we're going to use EfficientNet B2. So that's the only difference. So we'd like to freeze the base layers just as we've done before by setting their requires grad parameter to false. And the custom classifier head is because these models have been pre-trained on ImageNet, they have 1,000 output classes, whereas we only want 3. Now, that will depend on how many classes you have, but in our case, we have 3, so we're changing the output classifier head to have 3 output classes. So we've seen how to do this with EfficientNet B0. Let's have a look at how we might do it with EfficientNet B2 just for some practice. So let's go import Torch Vision, and I'm going to create, actually, I just want to put a note here that whenever from now on, if I refer to this number 1 model, it's FNet B0, and this number 2 model is FNet B2, just for short. So I'm not saying this whole long sentence every single time. So FNet B0 is this, FNet B2 is this. So create an FNet B2. So we want FNet B2 weights. I just had to retype it out. You know when you think about something too much and you can't do it? That's exactly what just happened to me. So this is going to be our model from Torch Vision, FNet B2 weights, or our weights per se. The pre-trained weights, we want the default weights. So default, recall, equals best available. And just to highlight, I'm not pulling this from thin air. This is Torch Vision. This is the documentation. And we go to the unstable version for now because we want at least 0.13 plus. Just keep that in mind. That's the version of Torch Vision I'm using. So classification, we find EfficientNet B0 or B2. There we go. So if we want the weights, we can go EfficientNet B2 weights.default is equivalent to using this one. So, and there's the number of parameters we have there. There's some information about our model. So this is what we're doing. We're downloading those weights. And then if we want to set up the model, let's go FNet B2 equals torchvision.models.efficientnet B2. the weights is going to be equal to fnet b2 weights, which is just that value we got above here. And then if we had a look at this fnet b2, what happens? So it's downloading from PyTorch. Beautiful. Look at that. Look at all those layers there. That's the power of transfer learning, is we get all of these layers in a couple of lines of code. And these are all pre-trained, by the way, because we've set the weights. So if we look at the structure of it, it's quite similar to what we've already seen with EfficientNet B0. So usually if you find a series of models with the same name, so if we jump back into here, we find all of these: ConvNext, DenseNet, MobileNet, RegNet, ShuffleNet, VGG. We've seen VGG before. VIT, so Vision Transformer. If you find the same models or a similar naming scheme such as VIT-B, that's base 16 weights, usually if they have the same naming scheme and then the number goes up, that means it's just the same style of architecture, so the same style of layers, but they've just been scaled up. So they might have more layers or more parameters or more hidden units or something like that. And that's the case generally for most of these. It's definitely the case for EfficientNet B0 to B2. B2 you can just think of as a scaled up B0. So let's jump back into here. We've got features. That's going to extract features from our images. What are the features? Well, it really depends on what the model has learned. Hopefully they are useful. It looks like they are because this model gets pretty good results on ImageNet. Then if we scroll all the way down, look how many layers there are. What do we have? We have an average pool layer that's going to turn the features tensor into a feature vector, so a vector representation of our input data. Then we have a classifier head here, which is slightly different to what we've seen with EfficientNet B0. So you'll notice that there's more in features here. That's because EfficientNet B2 is a scaled up version. So there's about 200 or so more values here. Well, actually EfficientNet B0 is 1280. There's 130 or so more in features to this final layer. And the dropout's a little bit higher to prevent overfitting. So what do we have to do in order to turn this into a feature extractor model? Well, we have to freeze all of the base layers and we have to update the classifier head. And if we wanted to get a summary of this, let's see how we got a summary before. Model equals. I'm just going to copy this, bring that down here. Let's check out a summary of our EfficientNet B0 or B2, sorry. I'm getting all of these mixed up. Excuse me. Okay, summary. EfficientNet B2, there we go. Okay, so we've seen this before. There's our EfficientNet. We've got all the layers are trainable. This time, because we're using B2, we have more total parameters. And we have a bigger classifier feature vector here. 1408 instead of 1280. So this is something to keep in mind when you're exploring new models. You have to make sure the input and output shapes line up for every layer, including the last layer. Otherwise, you'll get shape issues. So now let's create some functions to turn not only EfficientNet B2 into a feature extractor, but reproduce what we did for EfficientNet B0. So if we do requires grad, we want to functionize this. So how about we give that a try? We'll come down here and we'll create two functions. That way, for every experiment, we instantiate a new instance of a model. Now, what could we call these? We'll go import torch vision, and we'll go from torch, import nn. And we want, I'm just going to write a note here. We've already got a note above, actually. I might just save us some space by commenting out this. Want two functions. Let's create these. So they're both going to have the same number of out features because we have how many classes? Well, we have 3, right? So let's create an fnet b0 feature extractor. We want def create fnet b0. Now we've done these steps before. All we're doing is turning it into a function this time. So we're going to go get the weights and set up a model. We want the weights is equal to torchvision.models. It's a little confusing here that one of them uses capitals and spaces. whereas the other one doesn't. But that's all right. We want weights dot default. So they're the best currently available weights. Then the model is going to be torchvision.models efficientNet B0. And we can instantiate this with weights equals weights. In a previous version of Torch Vision, you might see pre-trained equals true, but we're using the latest, most up-to-date version of the Torch Vision API, so weights equals weights. Now we want to freeze the base model layers. How do we do this? Well, we've done this before. So for param in model.parameters, we want to set the param requires grad. So this means PyTorch is no longer going to track the gradients of, we want to set this in features.parameters, not every layer, so just the features. And then we can go change the classifier head. So what was our efficientNet B0 classifier head? Well, first things first, we're going to set the seeds so that when we set the classifier here, model.classifier, we will go model.classifier equals nn.sequential. I'm trying to remember these all off the top of my head. Sequential. But that's good practice, you know, when you try to remember these things. You don't always have to do it because that's the nature of programming, is being able to reference the documentation. But when you've got some practice, you can just start to fly through things. So in features was 1280 and out features is going to be out features 3. And I believe this was in place in their architecture. So we might also send this to the target device. Why not? And this to the target device as well for device agnostic code. And then finally, let's give the model a name so we can track the model that we're using in our experiments if we wanted to. Model.name equals fnetb0 and print. We'll just give a little info statement to finish off here. Info is going to be created new model.name model. And then we're going to return the model. Beautiful. Oh, what did we get wrong here? Didn't finish off the print. Okay, so let's call created model test. Let's see if this works. Create fnet b0. Wonderful. And then let's get a summary of it. We'll copy the summary code down here. We're going to do the same thing for fnet b2 in a second. Let's just put in created model test here. See what happens. Wonderful. That's looking like a feature extractor model that we're after. Base layers frozen, output layer trainable, total parameters. So this is 4 million or so. This is our B0 version. We have just under 4,000 trainable parameters. So we've seen this type of model before. Now let's reproduce this function, but for efficientNet B2. In fact, we could actually probably condense this into one function and update this based on a parameter, but let's just, for now, we'll just use it as 2 functions. If you want to extend this, you can do it by one function and then just put the logic in the function to create a certain model. So we're just going to change this to B2 now. So weights, B2, efficientNet B2 feature extractor, model is torchvision.models efficientNet B2. We're going to freeze all the base layers. This will stay the same. This is going to be different. So let's go fnet b2.classifier. So this is when we need to update this. We want 0.3 and the in features. Remember, one of the most important things in machine learning is making sure your shapes match up. So if we didn't change this, we would get a shape error. Or actually, I wonder if we do try that. Let's see what happens. Model name, fnet b2, return the model, and then let's just change this. Created model test is now going to be fnet b2. Created that. Now, if we pass through this image size, what's going to happen? There we go. Failed to run torch info. So it's run a whole bunch of different layers, but we've got an issue here. There we go. 1408 and 1280 can't be multiplied. So we've got a shape error. But as soon as we change 1280 to 1408, let's see what happens. Oh, that's too big. Run that, run that, run that. There we go. That looks like a feature extractor efficient net B2 model. So it's false, false, false. And then we have nearly 7.8 total parameters. And 4,000 are trainable. So let's just we'll copy this. Created model, test, fnet b2, just to make sure both of our functions are working. We've already seen fnet b0, but we'll do it again for the hell of it. I love practicing and seeing our different model outputs. So we should get two different models here. Wonderful. So we'll change this one to fnet b2, and we'll change this one to fnet b0. So our fnet b2 model has 7.7 million parameters total, and about 4,000 or just over of them are trainable, whereas our fnet b0 model has, if we go down, 4 million, whereas just under 4,000 of them are trainable. So you see here now, we've got two models where fnet b2 is thereabouts double the size in terms of number of trained parameters as fnet b0. So I think we've got all of the pieces of the puzzle ready to go to start running our different modeling experiments. If we come back, we've got the two data sets, 10% training data, 20% training data. We've got the two model architectures that we can use, feature extractor models, B0 and B2. Now we just have to set up the number of epochs, but this is quite easy because this is a parameter to our train function, which we've used before. So let's now in the next video create some experiments and set up the training code to run all of these experiments at once and track their results so we can view them later with TensorBoard. You might want to give this a shot yourself. We've got all the tools to do so. Try it out, and we'll do it together in the next video. Put your hand up if you're ready to run some modeling experiments. Well, you can't see me, but my hand is up in the air. Let's get started. You might have already tried this out yourself, and if you have, I applaud you. Let's create experiments and set up training code. So we've prepared all of the pieces of the puzzle. We've got a function to save our results to file, and now we've got different data sets, different data loaders, and different feature extractor models to run our series of modeling experiments. We've got 10% training data, we've got 20% training data, we've got efficient.net B0 and efficient.net B2 feature extractor creation functions, and we can set up the number of epochs by passing them to our train function from engine.py. Let's put all of this together. We'll go into here. This is one of my favorite steps of machine learning. Aside from getting good model results with the transfer learning model, one of my other favorite things is writing a series of experiments to see which transfer learning model works the best. So create models list. So need to create a new model. This is important. This is when we created functions. We create a new model instance per experiment so that each of our experiments starts with a model that starts from the same point. So it's a fresh version of that model rather than already being trained. So what we're going to do is create a list. I've already kind of done this. I'm talking too much instead of just coding. Number of epochs. We're going to loop through this list. We're going to loop through this models list. And finally, we're going to loop through this dictionary, create a data loaders dictionary with train data loaders equals data 10%. Now, you might be able to think of a more elegant way to set up these experiments. I'm just setting them up like this so that they're as straightforward as possible. So if you're running more, perhaps looping through dictionaries and lists isn't the best way, but for now, we're running about 8 experiments, well, exactly 8, so this will be good enough for us. So can you see what we've done here? We've got double the training time, that's one experiment. We've got double the model parameters or thereabouts. So 4 million for efficient.net B0 and nearly 8 million for EfficientNet B2, and then double the data. So these are the various knobs that we're turning to see how they affect our model's results. So now what do we want to do? Well, we want to run code to loop through the various combinations of all of these and train our various models for 5 epochs, 10 epochs, and on train data loader 10% and train data loader 20%. So let's start to do that. I'm going to put in the magic here called time so that you can see I'm putting my money where my mouth is and that these experiments shouldn't take too long to run. So here's my GPU. You might have a different one. I've got a Tesla P100 GPU. So all of these experiments should run within a couple of minutes. Let's see if they do. So from going modular, we want to import, or .utils, we want to import the save model function. So if you recall in the going modular section, we created utils.py, and in here we have save model, which is going to save the model to file. So the reason we want to do this is because as we're running our experiments, we want to save each of them to file, each of the trained models, so that we can later on import the best performing model and further evaluate it. So if we just ran these experiments, sure, we might see which model performs the best, but if we don't save that model, well, then we've kind of lost it, right? So we come back, we want to save each model as we go, and then first things first is set the seeds, so we get reproducible results. You don't necessarily have to set the seeds all the time, but I'm just doing it so your numbers line up as close as possible to my numbers. We want to keep track of experiment numbers. We don't have to do this, but this is just I like to print out stuff while it's going to see how things are going. One of my favorite things in the world is watching machine learning model train. Now, let's start to loop through our various combinations of dictionaries and lists. So we'll start by looping through each data loader. So we'll go for data loader name. So because this is a dictionary, we're going to loop through the key and the value. So the key is the data loader name and the trained data loader. Recall that all of our experiments use the same test data loader in train data loaders.items. Then we're going to loop through again, loop through each model name and create or actually we might loop through the epochs first, loop through the epochs. So for epochs in num epochs, and then we can loop through each model name and create a new model instance. This is where our functions come into play. So for model name in models, we're going to create a new model. So before we do that, actually, let's print out some info while we're here. Because we're 3 loops in, we might as well see where we're at. So let's go print out info. Want to go experiment number. This is where I'm just keeping track of what's happening. Plus equals 1, so we know how many experiments we've done. So print info experiment number. Wonderful. And then we're going to print out the number of epochs, model name, and data loader we're using. So this can be model. Model is model name. And then we'll go data loader is the data loader name. Data loader name. And then finally, the number of epochs here. Number of epochs equals epochs. Beautiful. So that's going to give us some information about what we're doing. And then we can go select and create the model. So if the model name is equal to fnet b0, we want to set the model equal to create fnet b0. Else, if the model name is something different, we want to set the model equal to create fnet b2. And we could put in some asserts and error clauses to make sure that the model name is one of these two models, but I'll leave that to you as an extension. What do we need to do next when we're training different models? Well, we need to set up a loss function and an optimizer for every model. So create a new loss and optimizer for every model, because as I've said, the important thing about each experiment is we want each of our models to start, or each of our experiments to start from the same starting point. Hence why we create a new model instance and a new loss and a new optimizer per experiment. Torch.optim, Atom, the params is going to be model.parameters. So we're going to optimize that. The LR equals 001. Another extension would be to vary the learning rate. You could add that to our list of experiments. Say you wanted to try a different learning rate. This could be another column over here. That's just one idea. Or even a different optimizer function. Instead of Atom, you could try stochastic gradient descent. Now let's train the target model with target data loader and track experiments. This is where our create writer function is going to come in. Create writer. So we can leverage this function. So every time we run a new experiment, we're going to create a new writer. This is why we created a function up here. So for each experiment, 1 through to 8, we want a new writer to save to a new directory. So for example, it's going to save to a new directory here for data 10% fnet b0 5 epochs, data 10% fnet b0 10 epochs, data 20% fnet b0 5 epochs, etc., etc. So let's come right back down to where we were. Oh, we're going full steam ahead. Look at us setting up this experiment code. There's undoubtedly an error here somewhere, but we'll figure it out. Maybe you've spotted it already. So model equals model, and then we're going to go train data loader. Now the reason we're calling the train function here, I just want to write note, using train rather than engine.train. So this is because what did we do before? We modified our train function in this notebook here to use the writer parameter. So we modified it there to use this writer parameter. That's what we need access to. So we're using this version of train rather than the one that's in going_modular.engine. So we could save this to engine.py, but we haven't done that yet. So we will just use this. Train data loader is going to be equal to the current train data loader. So because this train function is being called within the loop here, we are using this train data loader, which is going to first be this one, and then second iteration is going to be that one. And then we'll go test data loader is always going to be the test data loader. So we can just set that to test data loader because we use the same test data loader for each experiment. Optimizer is going to be the optimizer we just created. Same thing with the loss function. Epochs is going to be epochs, which because this train function is within the epochs loop, it's going to be one of these two values. Then if we keep going, we're on a roll here. Device equals device, which is the global target device. And then here's the important point to track our experiments. We're going to leverage our create writer function. And in here, we're going to set the experiment name. Experiment name. I'm going to call the experiment name the data loader name. So for example, pizza steak sushi 20% or 10%. The model name is going to be equal to the model name we're looping through. So the model name here is going to be one of these two values. And then we can do a little bit extra here. Is going to be F. We'll go create an F string for epochs underscore epochs. So that's going to be the number of epochs and then epoch. So this will be an integer, 5 or 10 for how long we're training for, and then saving with epochs as the final tag there, just so we know what that integer means. Finally, we've just trained a model. After this, hopefully, one of our experiment models has been trained. Now what do we need to do? We need to save the model to a file. Save the model to file so we can import it later if need be. How can we do that? Well, we've got access to our save model function, which we created in Going Modular. So now let's go save file path equals F07. And here's where we're going to get creative with the file path name. So we'll go model name and then underscore. We'll go data loader name underscore epochs underscore epochs. And then if we're saving a PyTorch model, we want to make sure it has the .pth extension or .pt. So we'll use pth, and then we can call save model, and we'll set model equals to model. This is using our save model function, which is from utils.py. So it takes in model, target directory, and a model name. Beautiful. So model equals model, the trained model that we've just trained. And then we're going to go target directory equals models. And then we can go model name equals save file path. So that file path we've just created. And then we can go print. Now, I'm going to do a little trick here with strings. This is just to separate our different experiments. Oh my goodness. Look at how much code we have there to run different experiments. Now, I'm going to leave you on a cliffhanger. If you've written this all out, try it out, see if it works. But otherwise, we're going to run this together and run our series of modeling experiments in the next video. I'll see you there. All right, did you try it out? How did it go? Did all of the code work? I hope it did, because there's a fair bit here. But let's now run the code to run our first official PyTorch experiment tracking for a series of experiments to see which combination of data, training time, and model size gives us the best results for Food Vision Mini. 3, 2, 1, no errors. Oh my goodness, look at this. Here we go. Experiment number 1, model FNetB0, data 10%, number of epochs 5, created new FNetB0 model, and created a summary writer and saving it to data 10%, FNetB0, 5 epochs. Over here, we've got some live commentary of a machine learning model training. There we go. It's now the 28th of June. Yesterday was the 27th. So the data 10%, FNetB0, FNetB2, 5 epochs. Oh my gosh. Ladies and gentlemen, look at what we've got here. Look at what we've created. Experiment number 2. Model FNetB2, data 10%. Number of epochs 5, new FNetB2 model. Saving the runs to data 10% FNetB2 5 epochs. Experiment number 3, we are chugging through this. Look at this. Here we go, 1, 2, 3, almost halfway. So we come back, this is running quite quickly. Remember how I said you want your experiments to run quite quickly in the beginning so that if one of these works far better than the rest, I have a feeling they'll all be quite similar because they're all pretty good models and there's only a small amount of data. But you want these to run quickly so you can work out what works and what doesn't work. So let's just let this run. I'm going to watch these run for a little bit and then I'll be back in a few seconds. Would you look at that? All of our experiments have run. I'm very surprised that there was no errors here, but we could go back through all of these values and see which model performed the best. Oh, and do you note? At the end of each experiment, our models get saved. So now we have a series of different models over here. How cool is that? We just ran 8 different experiments across different levels of model size, different amounts of data, and different training times, saved all of their trained models to file, and all within, what do we have here? How long did it take? It took about 5 minutes on my system here. I'm running with a NVIDIA SMI, Tesla P100 GPU, just to reiterate. So just do beware. The amount of time things take may differ depending on the hardware you're using, the amounts of data you're using. But to drive home the point here, putting my money where my mouth is, you want your first series of experiments to only take a few minutes. If you're waiting longer than 10 minutes for an experiment to run when you're beginning, well, then you're probably waiting too long. In reality, we would probably try to reduce this to under 3 minutes. so that we can quickly move through different models. So now, instead of trawling back through and seeing which model performs the best, you might have already seen which one has the highest test accuracy or which one has the lowest test loss. Let's not do that. Let's not look at numbers on a page. Let's get visual. So in the next section, or the next video, we're going to see how we can view multiple different experiments using TensorBoard. So you might want to give this a shot. Try some code similar to this and see if you can view and find which one of our modeling experiments has the best results. So try to view the logs with TensorBoard, and we'll do that together in the next video. I'll see you there. We've run our series of modeling experiments, and we've got some saved models over here. And we've also got some runs files. So here's our models under the models directory. Look at all those beautiful PyTorch models. And so if we look over at runs, so I ran mine on the 28th of June, 2022. Data 10%, data 20%, FNet B2, or B0, sorry, FNet B2, 10 epochs, 5 epochs, and then the same again for the different data set. How beautiful is that? So let's now visualize. We're following all the mottos here. We've experimented. I'm trying to say that in past tense now because we've run the experiments. But now it's time to visualize. So let's write down, we followed the machine learning practitioner's motto of experiment. Not grammatically correct there, but that's okay. Now, let's visualize. My goodness, that's incredibly hard to type fast 3 times in a row. There we go. Okay, so we've already viewed our experiments in TensorBoard before, and you might have already tried this out by loading the extension TensorBoard and then said, TensorBoard, hey, look at the log directory runs, which is over here. All of our model training history is saved into this directory there. So let's give this a shot. I'm going to bring this down. We're going to retype it anyway for fun, but just for reference. So we could run that cell, but just for practice. So let's view our experiments within TensorBoard from within the notebook. So load extension, TensorBoard, and then we're going to say, hey, TensorBoard, log the directory, log dir runs. Well, let's see what this comes up with. It may take a little bit to load. Oh, is it saying it's already loaded? Oh, there we go. Yeah, we could reload the extension by running this command because we've already got a TensorBoard instance above. But this is just going to load TensorBoard. And of course, depending on where you are, so if we go back to section 5, if you're running in VS Code or something like that, you might want to look up how to run TensorBoard in VS Code, which is another popular place to write machine learning code or code in general. However, since we're using Jupyter and Colab notebooks, we've made sure that TensorBoard is installed. That comes installed on Google Colab by default. And then we're running the load extension TensorBoard magic. And then we can view our TensorBoard logs with TensorBoard logdir and then directory name with logs. And then if we wanted to publish our experiments publicly, you could do so on tensorboard.dev. We'll have a look at that in a second. So here we go. Wonderful. We've got a TensorBoard instance here. We've got our accuracy and loss. How about we just look at the test values? So, oh, look at that. All of our modeling experiments automatically loaded. How beautiful is that? And we can turn smoothing off to see the absolute values. Or we could keep it there, maybe at 0.5. That should be enough. See, I'm not the biggest fan of smoothing. I like to see absolute values, but we'll just keep it there for the sake of it. Now, if we scale this out, what do we have here? Look how many experiments there are. There's that extra one. We might get rid of that. So we're only after the ones that are prefixed with today's date, which is the 28th of June in my case. So if we go right to the end here, what do we get? We get some different values. So you can see how long each one of those experiments took. The longest one there took about a minute, which is using the most amount of data. So data 20%, I can't scroll and highlight it because if I go off, it's going to remove it. But if you look at the dark blue dot, which is second from the bottom there, we've got data 20%, FNet B2, 10 epochs, accuracy test ACK. we finish up with just under 95% test accuracy. Oh my goodness. Ladies and gentlemen, we have a new best performing model, and that took 10 epochs. It took about a minute. So the other models aren't very far off though. Like the one on the very bottom, the green dot, trained for half the training time, but only was just over a percentage point lower in the value, so the accuracy there. And it took half the training time. So that's something you'll have to think about. That's the reason why we trained with different model sizes, different amounts of data, and different amounts of training time, so that you could see there is a trade-off between performance and speed. So our model that trained for the longest, with the most amount of data, with the biggest number of parameters, so EfficientNet B2, took a minute to train and ended up with 95% test accuracy. That is incredible. That's what we're after. So let's now have a look at the loss. We'll just zoom out here. So we've got 8 values for 8 different models. We'll go right to the end. Now I'm looking at the value column here. Which model has the lowest loss? Well, it looks like the gray dot has the lowest loss. Or what's this dark blue dot? Oh, okay. So the model with the lowest loss is actually EfficientNet B0 for 10 epochs. It's finished up with 2.2856 loss, and it took about a minute or 51 seconds or so to train. Now, the second lowest loss was the gray dot here. I'm just going to highlight that. Was twice the amount of data, so data 20%. EfficientNet B2, 10 epochs. We have a loss value of 0.01 or thereabouts, or 0.1, higher than the dark blue dot here. So it looks like the model with, are you noticing a trend here? So it looks like across all of our experiments here, it looks like the model's trained with the bigger data set and the bigger model and the longer training time turned out to have the best results. Now, does that make sense after what we've talked about? So generally in machine learning, the bigger your model, the more data you have, and the longer you can train for, up until a point, because it gets to a point where more training doesn't really help, the better your model will go. So I'm happy to take EfficientNet B2, the one I've highlighted here, with data 20% and 10 epochs, has the second lowest test loss, but it has the highest test accuracy. So if we go find that blue dot, there we go. We'll take that model because it's got a better trade-off here. If we were to take the second best or the best performing test loss, we get a little bit of a degradation in accuracy. So let's take the best performing model as being EfficientNet B2, this one here, the dark blue dot, data 20% and 10 epochs. So that's how beautiful TensorBoard is. And then if we wanted to only look at the models that train for 10 epochs, we could do this. 10 epochs. So we've got 10 epochs. And then, or maybe you could even do only look at the ones with data 20%. And then you could even put in a clause there that'll only show data 20%, 5 epochs. You can put in regex here if you wanted to really filter them, but I usually focus on the test data set and then explore my different models from there. So let's say here, the best performing model was the one with the experiment that had the most amount of variables. So the most data, the biggest model, and the highest number of epochs, which isn't too much of a surprise based on what we've talked about in the past. We had model was FNet B2, and then we had data set was pizza, steak, sushi 20%, and then we had epochs was 10. And the overall trend of all the results was that more data, bigger model, and longer training time led to better results, or generally led. I always say generally because it's not always the case, but usually it does. Led to better results. Now, this might give you an idea of what experiments you could run next. If our best performing model so far was efficient net B2 on the dataset of pizza steak sushi 20% and for 10 epochs, potentially you scale this up even more now. You could go to B4 and you could double this. So you could do 40% or 50% of the data, and you could maybe do 50 epochs instead of 10. It's all up to you, but this is just to give you an idea of the types of experiments you could run. And so one last thing to finish off is, say you had your experiments in a notebook and you wanted to share them publicly with your friend or with your colleague or something like that. TensorBoard.dev is a free way to do that, baked within TensorBoard. So let's see how we can upload our experiments to TensorBoard.dev. So if you come into here, this is PyTorch experiment tracking, view experiments in TensorBoard. We've gone through this. And if we go here, I'm going to copy this cell here, which is TensorBoard dev upload. Now, this has come directly from this website, TensorBoard dev upload. There we go. Very similar code here. You can read through this if you'd like a little bit more on TensorBoard.dev. Just a note that these results will be public if we upload them. So just be careful if you upload anything to TensorBoard.dev, make sure it's not sensitive data. Otherwise, it will be publicly viewable. So we're going to call this dev upload logdir runs, which is just the directory we've been viewing in TensorBoard. We're going to give it a name, PyTorch experiment tracking, food vision mini results from the video. And the description is comparing results of different model size, training data, data amount, and training time. So I'm going to run this, and then it's going to ask me for an authorization code. So I'm just going to put in yes here. So I'm going to visit this URL. So I'm just going to pause the video, visit this URL, put the code in so that my code isn't publicly available. I'm back. So I put in my code. Oh, there we go. It's there. So I'm just going to make sure that I blur this out, but it shouldn't be too bad because it's only a one-off code. It'll only work one time. So it's going to upload all of the results that are in the runs directory because that's what we've put here. Runs. And maybe it is. Well, let's just have a look at our experiment, hey? It should be publicly available at this link. So let's have a look. No data found. Let's reload. Oh, there we go. Total uploaded, 260 scalars. There we go, skipped. So if we come back here, I think if we refresh this, wonderful. So we can just go test, and there we get all of our data there. And if you go to this URL, I'm just going to link it in here so it's saved. Again, that authorization code shouldn't matter too much because it's a one-off code. But let me just put this down here. You can view the experiments publicly at TensorBoard.dev. There we go. Turn that into Markdown cell, and that's all of our experiments there. Now, just a little caveat, don't worry too much if your numbers aren't the exact same. As we've discussed before, the randomness of machine learning and deep learning will mean that numbers will vary very slightly. What you should be paying more attention to is the trends of your results. So we've viewed our experiments in TensorBoard and TensorBoard.dev. Now, how about we import the best performing model, specifically the efficient net B2, data 20%, 10 epochs, and make some predictions or some visualized predictions. Oh, I've gone to the wrong directory on the test data. So let's do that in the next video. I'll see you there. We've checked out our results of our experiment tracking with TensorBoard. Now let's do the fun part of importing in. So load in the best model and make some predictions with it. So just like we did in the last section, PyTorch transfer learning, I'll give you a little challenge if you'd like to pause the video here. So we're going to make some predictions on images from the test set. So if you'd like to give that a go with our best performing model, load it in and then follow this section here and see if you can make some predictions on images from the test set. And let me just clean up this. There's our results on the tensorboard.dev. Just going to get out of that. So we've got some space up here. I believe that is all we need for now. Wonderful. So we've decided that our best model was EfficientNet B2, Pizza Steak Sushi 20%, and we can come up here and get its path name. So it's this one here, models/07_FNET_B2 data 20%, 10 epochs.pth. Ooh, that's a bit of a mouthful. So this is our best model file path. Wonderful. So we can now write some code to load this in. So set up best model file path, and we'll go best model path equals, and we'll put that into a string. Now we need to instantiate a new instance of FNet B2 to load in, because this is a state dictionary. Our save model function saves the model state dictionary. So we need to create a new instance of FNet B2 to load in the saved state dict. So let's go best model equals create FNet B2, and then we need to load the saved best model state dictionary. So if we go best model.load state dict, we've seen this a few times across the course. We're going to go torch.load best model path. So we've got our best model creating a new FNet B2 using the function that we created above. We've got best model path here, and we're going to say, hey, for the best model, let's load in the save state dictionary that's here, and we'll do that using torch.load this file path. So let's try that out. We created a new FNet B2 model, and all the keys are matched successfully. Beautiful. Now, there's only really one way to test this, and that's to make some predictions. But before we do that, we're going to check the model file size. So this is a sound check to make sure. Remember, what's our goal? Our goal, this model is performing at 95% test accuracy, or so it says, numbers on a page. Our goal is to create a Food Vision mini model that performs well enough and is able to run on a mobile device/web browser. So very similar to what I'm doing here for Nutrify.app. This model runs directly in the browser. So because Food Vision Mini identifies different photos of food, and where do people take photos? On their phones. If we had infinite compute, we could maybe do a model that's much bigger, but phones and browsers are limited in compute. So from pathlib, import path, we're going to see how big the model file size is. And we can do that programmatically. Size in bytes. We'll get it in bytes first, then convert it to megabytes. Because that's pretty understandable, right? So we want FNet B2 model size, and I'm going to go path, and then I'm going to go best model path. So we're using the path module here, and then we can get some statistics from that using the stat method, and then we can get the stat size. So the stat size attribute, that's going to return the size in bytes, and then I'm going to convert it to megabytes by dividing it by the multiplier of 1024 times 1024, because there's 1 million and something or other bytes in a megabyte. So let's go here. My conversion might not be exact, but it gives you an estimate of how big your model is. So EfficientNet B2 feature extractor model size is FNet B2 model size MB. Let's see if this works. Oh, that's pretty good. 29 megabytes. Now, what is our limitation? Well, that's a tough question, right? We don't want it to be gigabytes in size. We also don't want it to be too small, otherwise its performance might be degraded. So I think this is a good value to go forward with for now, and we can check it out if it works or not later on in the course in another section that I'm not going to give away too many spoilers now, where we try to do something with our model which is very much like what we've spoken about here. So let's keep going. We're now trying to plot or make some predictions using our best trained feature extractor model on the test data set. So how about we do that? We're going to import a function to do this, to make predictions on images and plot them. So you might have seen this, you might not have, but in this section, section 6, we did create a function here, pred and plot image. What I've done with this function is rather than us rewriting it over and over again, I've been a bit sneaky here and put it into going modular, and we've got a function here or a file here called predictions.py now. And all I've done is I've put this function into here. So that way we can just import pred and plot image from predictions.py and use it. So you see the whole point of going modular is to, if you're writing code over and over again, you might as well put it in a Python module. So predictions, import pred and plot image. So we just saved how many lines of code that is, like 30 or so. 80 lines. We just saved 80 lines of code or thereabouts with one line of code. So let's get a random list of path names of 3 image path names from the test data set. You know how much I love randomness. Let's go import random num images to plot. I'm going to set this equal to 3. We just want 3 random test images or the paths to test images, because that's what pred and plot image takes in. It takes in an image path and a trained model, and we'll make predictions on that image and plot that image as well. So test image path list, we're going to get a list of path, and then I'm going to put in data. Let's get the 20%. 20% path / test. We'll qualitatively evaluate our model on the, I believe this is star, on the 20% test data set. And then we'll get a test image path sample. So we only want 3 of these. Random.sample, and I'm going to sample the population that is the test image path list. And the number of samples I want to get is num images to plot. And then here is where we can loop through this test image path sample. So for image path in test image path sample, what are we going to do? We're going to call our pred and plot image function, and the model is going to be equal to the best model, which we've instantiated up here to load the state dictionary. And then we're going to set in the image path is going to be equal to the current image path within the loop. Then the class names is going to be our class names variable that's followed us through most of the course. And then we got an image size here, which is 224, 224. We don't need to set that, that's the default, but we will anyway. Are you ready? We're going to use our best performing model so far to predict on images it has never seen from the data 20% path test set. In 3, 2, 1, let's go. Oh, I missed the key there. I'm so excited. Pizza, oh, that should be steak, so that's wrong. Sushi, that's correct. That's steak. Wonderful, that's looking pretty good. Let's go again. It is 95% accuracy on the data 10% test set, so there are going to be some mistakes. That's steak. Steak, sushi, well done. What do we have? We'll do one more after this. Pizza, beautiful. Steak, sushi, and one more for good luck. Pizza, steak, and pizza. Oh, our model is doing pretty darn good. So what was that, about 12 images and it got 1 wrong? What the hell, one more, we'll finish it off. Sushi, steak, sushi. Holy moly, our model is doing very well. So that is very exciting. Our best performing model is, in fact, doing quite well. Let's now finish it off by making a prediction on our own custom image. So images that aren't even in the test set. Now we've done this before. I'm going to issue you the challenge to give it a go yourself. If you go to the repo, we're going to use the old faithful Pizza Dad image. So if you want to download this into our notebook and make a prediction with our model, you could use this function here and see how our best performing model goes so far on it. I'll see you in the next video. Let's see if our model can correctly classify Pizza Dad. We've seen how well our best performing model is doing. And you know what? why don't we do it on 3 more random images from the test set while we're here? It's time to finish off the experiment tracking section. We've got pizza, pizza, sushi. Oh, so it was wrong on that one. Our model still has a little bit of improvement. I'll leave further improvement for you to experiment with. But let's go 9.1, predict on a custom image with the best model. Now, I encourage you to give this a go on your own custom images, but we're going to use the ever-faithful Pizza Dad image, which is a photo of my dad eating pizza, to test out our model. It's kind of been the way we've tested out our models throughout the entire course. So we'll keep things consistent. What I'm going to do is just import this code that we wrote in the last section. So this is PyTorch Transfer Learning. All it's going to do is download this image to the Colab repo or to the Colab file system, and then we can predict on it. So we've already talked through what happens here. So I'm not going to spend too much time reiterating what's going there. Import request. We set up a custom image path. If the image doesn't exist, we download it using the request library. We write the content to a file, which is this path name here. And that if it does already exist, we don't download it. So let's download it there. Oh, data path is not defined. Would you look at that? The one time I say we don't need to go through the code, we actually do. So from path lib, we're going to set up a path here manually. From path lib, import path. So we will create a path here. Path is going to be data/pizzadad.jpg. So that's where we're going to save that image. And I think this should work. And we can run the exact same code here. So let's go predict on our own custom image, which is Pizza Dad. Pred and plot. How do you think it's going to go? Our best model yet. On paper, that is. Well, qualitatively as well now. Image path is going to be the custom image path. And then class names equals class names. Let's see. Do we get 2 thumbs up? Yes, we do. Look at that. Predicted pizza with a probability of 0.982. Wow, that seems to be our most confident model yet. Look at this, back in our PyTorch Transfer Learning, in the last section, we had EfficientNet B0 on 10% of the data trained for 5 epochs, had a prediction probability of almost half of what our model has got here. Now that doesn't mean it's more correct, it just means our model is more confident in its prediction. So take that how you will, but to me that looks like our model is going, well, I definitely think this is a pizza image. And to me, that's sort of hinting that its patterns that it's learned are better than our previous models. So try to upload your own custom image here. You could upload it and just try it out to see how the best model goes on pizza, steak, or sushi. But let's now finish our first milestone project, or in fact, we've written all the code. So you should be very proud of yourself for how far we've come. We downloaded some data, we viewed our single models experiments with TensorBoard, and then we set up a series of experiments. We ran 8 different models in 5 minutes. Now it's time to cover some main takeaways, and I've got some extra curriculum and exercises for you to practice what you've learned. I'll see you in the next video. We finished off the last video with 2 big thumbs up. We saw the power of transfer learning and the power of experiment tracking. So let's jump into here. Let's wrap up Milestone Project 1 PyTorch Experiment Tracking. If you go into this section number 7, if we scroll down here, I've summarized some of the main takeaways from this section. And the most beautiful thing is that we've now gone full circle. So right back in the PyTorch workflow fundamentals, what did we say the workflow was? Get data ready, we turn it into tensors. We've done that plenty of times. Pick or build a pre-trained model to suit your problem. Create a loss function and an optimizer. Build a training loop. We've put a lot of this code into going modular. So engine.py creates all of our training loop for us. We fit the model to the data and we make a prediction. We saw how to evaluate it both quantitatively and qualitatively. Qualitatively being making predictions on our images. We've now improved through experimentation. The whole point of this section was to set up programmatic experiment tracking, adhering to the machine learning practitioner's motto of experiment, 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 and then save and reload your trained model. Well, we've just done that and made predictions on our own custom data. So we've gone full circle. Give yourself a pat on the back because that is no small feat. So the main ideas we should take away from this is, of course, the machine learning practitioner's motto: experiment, experiment, experiment. But yes, of course, we've been doing plenty of that already. In the beginning, keep your experiments small so you can work fast. Your first few experiments shouldn't take more than a few seconds to a few minutes. And we did that. We saw running 8 models in about 5 minutes. In fact, you could probably do quicker than that. And so the more experiments you do, the quicker you can figure out what doesn't work. And what does that mean? Well, that's the whole point of science, right? If you figure out what doesn't work, you can figure out what does work. And when you do find out what does work, scale up. So, for example, since our best performing model is now EfficientNet B2, perhaps you'd like to now see what happens when you scale that up to the whole Food 01 dataset. Oh my gosh, Food 101 that is, from torchvision.datasets. In fact, I wouldn't even recommend going straight to the whole dataset. I'd probably just start on all 101 classes, but only 10% of the images. See if you can give that a go. And then finally, programmatically tracking your experiments takes a few steps to set up, like we saw, creating a writer and TensorBoard and whatnot. But in the long run, it's worth it so you can visually inspect multiple experiments in one time. And of course, there are many different machine learning experiment trackers out there, and we've got that up here. How do you track a model? Different ways to track machine learning experiments. We've looked at TensorBoard because it's baked into PyTorch. There's also weights and biases experiment tracking, one of my favorites. And there's also MLflow, which is a great open source MLOps lifecycle library. And if we come right back down to the bottom, I've got some exercises prepared for you. So 3 exercises here: picking a larger model, trying out data augmentation, and then if we go down here, scaling up if you really wanted to. And then of course, there's some extra curriculum that I'll let you explore on your own. But congratulations, you've now finished the Milestone Project 1 PyTorch experiment tracking. Oh, and just a little tidbit, there is an exercise template notebook for number 7 and a solutions notebook for number 7. So here, these are both available on GitHub, but you've got the links to those. I'll let you go through both of them. So there we go, template and potential solutions. So we'll get out of that. Well, we're running out of sections here. Well, I'll keep the next one a secret. I'll see you there. Welcome back. In the last video, we left on the cliffhanger of a question: what is a machine learning research paper? Now, rather than talk about this out loud, let's actually have a look at one. So if we go here, this is the VIT paper, or the Vision Transformer paper, formerly titled "An Image is Worth 16 by 16 Words, Transformers for Image Recognition at Scale." And of course, if you don't understand anything of what's going on here, feel free to pause the video and search it up. What is a transformer? Machine learning. Transformer, machine learning model. Here we go. We've got transformers. We have a transformer is a deep learning model that adopts the mechanism of self-attention. That's really important. So a convolutional neural network will use a convolutional layer, but a transformer is typically an architecture that uses self-attention, and if you want to learn more about that, you can read up on that, as its main learning mechanism. So we're going to be focused on building a transformer with PyTorch code, rather than talking about the nitty-gritty of what each layer actually does. So differentially weighting the significance of each part of the input data. It is used primarily in the fields of natural language processing, NLP. In fact, that's where transformers were first introduced. And computer vision, which is what we're going to be doing. We're going to be using a vision transformer, so a transformer for computer vision. I'll let you read more up on that if you like. This is a machine learning research paper, and if we just scroll through this, we have an abstract, which gives a little overview, a 1 paragraph. We have an introduction, which maybe talk about what the problem is and what previous research has done and what this paper suggests they could try and do. Oh, there's related work. Okay, so there's some related work to the problem. Then we have a lot of figures. Sometimes we describe a model with visuals rather than just text, because I know for me, I really understand things in a visual format. Then we have method. We have a vision transformer VIT that describes the architecture, which is 4 main equations, because remember, machine learning models and PyTorch neural network layers and all that sort of jazz behind the hood are running some sort of mathematical function. We have a whole bunch of different sections, experiments, setup, what data sets we use, what hyperparameters we used. Now, there's a lot of information here. And so what you need to, and I'm going to stress this throughout the course, is that this was written by 12 researchers. So some of the smartest people in the world collaborated to create this research paper. So it makes sense if for the first time, I've read this about half a dozen times now, and there are still some things that I don't understand. So for your extra curriculum for this video is to read through this once. It may take you a couple of hours when you first begin, but if you're interested in getting involved in machine learning research, you're going to be reading quite a few of these. And it takes a bit of practice to begin with, but once you practice like anything, you get better and better. So with that being said, we've looked at one single paper, but let's get a high-level overview of the anatomy of a research paper, and in fact, many other kinds of scientific papers. So we might have a number of different sections here, and what each of those sections contains. Often, machine learning research papers and other scientific papers will begin with an abstract. Now, there might be different names for these, but I've just chosen some of the most generic ones and the ones that I've personally used and the ones that I'm most familiar with. So we have an abstract, which gives an overview summary of the paper's main findings and contributions. An introduction, what's the main problem? In our case, for the vision transformer, it might be image recognition. So if we go back, for image recognition at scale, in other words, image classification, just like what we're doing with Food Vision Mini. So if we come back here, we have method, or in the VIT transformer paper, it says experiments. So what steps did the researchers take? This is a lot like a cooking recipe. What's the method to reproduce the dish? What's the method to reproduce the machine learning research findings? What were the results? Did the paper achieve better than other similar papers? Or did it find something new? What's the conclusion? So what's the next direction for research? If the research was to inspire other research, where should we look next? References. So machine learning research papers, and in fact, a lot of scientific research in general, is built off the basis of previous scientific research. So if we look here, these are all the references that the Vision Transformer paper is quoting. So these are all research papers in themselves. So there's about, maybe 50, 60 odd other research papers that this research paper has borrowed ideas from. So if we see here, there's one here. In the model design, we followed the original transformer, Vaswani et al. 2017. Now this is, I believe, the attention is all you need paper. So if we have a look at this, this is a little bit of a treasure trail you can start to go down once you get familiar with machine learning research and how it's published. Attention is all you need. Now, did this introduce the transformer? Here we go. We propose a new simple network architecture, the transformer. So this is where the transformer that you may have heard, the architecture is very popular at the moment, was first introduced. Attention is all you need way back in 2017, which is 5 years ago now. I'm recording this in 2022. So in deep learning terms, this is quite an old paper because things change quickly. But it turns out the transformer is very capable. So not only can it perform on natural language processing, it can perform on vision data sets. And so this one is a little bit more recent, 3rd of June 2021. So if we come back here, finally, it might finish off with an appendix. And in the appendix, you might have extra resources and findings to look at that weren't included in any of the above sections. And as this little asterisk says, this is a fluid structure, right? It's more of a general guide than a rigid outline. So you might find the names of some sections chopped and changed, and you might find that they might have extra sections, but this is pretty stock standard for any general machine learning research paper. And so we go to the next slide. So this is just that table we looked at before, but condensed. So if we just draw some colorful lines here and colorful boxes, you can see that the VIT paper, the paper that we've been looking at, has an abstract to begin with and then an introduction. So again, we're going to be specifically focusing on the Vision Transformer paper itself in this section, but a lot of what we're talking about, the principles of turning a paper into usable code and different research sections, can be drawn, or lines can be drawn from that to many other different types of machine learning research papers. Of course, the individual steps may be different, but the overall principles are much the same. So let's keep going. We talked about what a machine learning research paper is, but why would we want to replicate a machine learning research paper? Well, let's talk about that in the next video. So now you might have the question, why replicate machine learning research papers? Well, the number one reason is that it's a fun challenge, and if you want the skills to be a machine learning engineer, well, here's the steps. 1, download a paper. 2, implement it. As other words, turn it into usable code, and a paper in this case is a machine learning research paper. And 3, keep doing this, in other words, practice 1 and 2 until you have machine learning skills. And I've put a little asterisk here, we'll see what that is in a second, but that's a quote from George Hotz, which was, I took this as a screenshot from one of his live streams on Twitch where he codes machine learning and other things. But he's the founder of Comma AI. Now, Comma AI is a self-driving car company building computer devices like this that use computer vision to understand what's going on in the world of driving and then form actions around that as to drive a car. So that's pretty darn cool. But let's dig a little bit into what's going on here. Why would this be the case? Well, download a research paper. In our case, it might be this PDF here. Now, this is from the Google Research Brain team. Now, Google are pretty sophisticated at machine learning, right? And if they're publishing research like this, and fairly recent as being state-of-the-art on computer vision, do we have the word state-of-the-art? There we go, state-of-the-art. So vanilla transformers competitive with or even better than state-of-the-art CNNs, meaning that their vision transformer is, let's just say, very good when it got published. So if we want to become a machine learning engineer, which I'm sure we all do, it's very fun being a machine learning engineer, we download a research paper, we turn it into code, because that's what a machine learning engineer does, right? Is they write code to take data, build a machine learning model to find patterns in that data, and then deploy that model so that it can deliver intelligence in some form of application. And then if we keep doing these steps, well, we get skills, because you get skills from practice. And the asterisk here that I've put is that machine learning engineering also involves building infrastructure around your model, so some way to load data, transform it, and then model it, / data pre-processing steps. And in fact, I'd probably add another step here, is that you want to go from taking data to building a model, in other words, downloading a research paper, the best of the best, and then find a way to deploy that said model. So get it into the hands of others. And we're going to be focusing on deployment in the next section. But for now, we're focused on becoming a machine learning engineer by downloading a paper and implementing it. And then after this, once you've gone through this, you can go on and do number 3 on your own, is that keep doing the things that we're doing in this section, PyTorch paper replicating, until you've got some machine learning skills. So with that being said, let's keep going. In the next video, we're going to cover where can you find machine learning research papers. Welcome back. In the last video, we covered why would you want to implement a machine learning research paper? And we saw this quote from George Hotz, machine learning engineer, downloads a paper, implements it, keeps doing this until they have skills. And that machine learning engineering, this is the little asterisk, also involves building infrastructure around this. So step 0 might be load data, and step 4 may be deploy model. But the whole premise of this is that if you want to build skills, why not just go straight to the latest and greatest and try to replicate it? So if all the smartest people in the world are publishing this as a research paper, you can be assured that if you were to be able to replicate this with your own skills, well then you're pretty good at machine learning, right? And then if this turns out to be a well-performing computer vision model, then you have the benefit of not only being able to recreate it yourself, you have the benefit of being able to use it. So replicating a machine learning research paper has a lot of benefits. So now let's go through the question, where can you find machine learning research papers? And now here's another caveat. There is going to be too much for you to go through because machine learning is booming, right? We all know that. That's probably why we're here. And deep learning as well. When I say machine learning, I mean deep learning as well. So the main resource where you're going to find a lot of things, and the way I found this is on archive.org, which is ARXIV, archive.org. of, if we go to archive.org and search machine learning, then we go down, these are all the recent machine learning papers. There we go, self-distilled vision transformer. That's what we're replicating. But that's another paper that uses the vision transformer. And there's a whole bunch more, but let's see that live. That's way more fun. Archive.org. So this is the home page of Archive. This is still Archive, where image is worth 16 by 16 words. But then if we go here, we've got a lot of different scientific topics such as physics, math, quantitative biology, and computer science. That's what I'm going to start searching for. And then we go in here, machine learning. We'll type in that. Here we go. Now, there's a lot of research papers here. Way too much for any one person to go through, but this is stuff that's just recently been released. And I'm going to be straight up with you. I often don't understand like 90% of what's going on here because it is a big field. But instead, what I do is I often filter down to things that are relevant for my problem. So do we have computer vision? Yeah, computer vision, computer vision. If we're working on Food Vision Mini and I want to use a computer vision model, I might come here to find computer vision models. But then let's go have a look at some other resources. Now, there's a beautiful Twitter account called AK, and it might be pronounced Akil. I might be saying that wrong, but AK does something similar to this. I'm not sure if they do exactly what we're doing here, but then repost them. And it's sort of like a filtered feed of different machine learning research things. So let's see if we can find something. There's demos. There's some information. There's a paper from DeepMind. There's neural radiance transfer fields. A lot of the stuff here, again, I don't fully understand, but I often dig out something that's related to what I'm working on. Vector quantized image-to-image translation. Okay, that could be related to food vision. What else do we have? Another demo. Exciting demo. So yeah, this is a great account to follow just for machine learning tweets. Specifically, research paper tweets. Data's with high hybrid matching. So a lot of stuff going on here. And this is kind of a big thing as well. I want to emphasize the fact there is a lot going on at the moment, and this is going to be quite an in-depth section. So again, if you ever do get stuck or anything, all of what we're covering is covered in chapter 8, but we're going to try and break this down piece by piece because the field of machine learning, it's a wild, wild west. Then we have GitHub repositories like Lucid Rain's Vit PyTorch, which was, in fact, a lot of the inspiration for the code in this module came from this GitHub repository. So this is Vit PyTorch, so Vision Transformer PyTorch. Then we have the Vision Transformer model there. But this is not so much a way to find research papers, but just to see an example of what it looks like translating a lot of research paper code, or research papers into code, that is. So there we go. We've got a usable Vit, a simple Vit from another machine learning paper. So Lucid Rains is a GitHub account that turns research papers into code examples. And they've got a whole bunch of different examples, not just with Vit PyTorch, that's probably the most popular one, but there's AlphaFold 2, which is using PyTorch for AlphaFold, which is to do with protein folders. There's DALI 2 in PyTorch. Now, DALI 2 is a text-to-image generator. I'll let you go through all of this here, but this is just a great example of someone who's publishing open source materials to help other people learn about the field of machine learning and deep learning. So let's get out of that. And you'll probably find that a lot of these are made with PyTorch because this is the last resource, by the way, paperswithcode.com. If we just go back to the keynote, yeah, Papers with Code is the last one. This is a place that's going to curate machine learning research papers for top, social, new, and greatest to find, yeah, there's TensorFlow, and there's Hugging Face Transformers, and there's PyTorch, a ConvNet for the 2020s, Saga, Scikit-learn. So here's all machine learning research papers, and often they have code examples with them. So this is trending research right now. And then if we go here, do they have code? So this is Apple One, an improved 1 millisecond mobile backbone. And then if we go here, we've got code example on GitHub. So this is machine learning research papers with code. And then we go here, we could dig into here and try to find the code. ML model. Beautiful. So this is four of my favorite resources for finding machine learning research papers. Archive, which is basically the hub for all kinds of technical papers. It's where the vision transformer paper, the VIT paper, is hosted on Archive. That's where you're going to find the white papers or the scientific PDFs. And then we have AK, which is a Twitter account. There are many more different Twitter accounts that share out machine learning. This is one of my favorites. You can find it like a filtered feed of different archive papers on AK's Twitter. You can find machine learning reproductions on GitHub, such as Lucid Rains, VIT PyTorch. There are many other different repos. This is just one example. And then finally, possibly the most comprehensive resource for finding machine learning research papers with code, that's why it's called Papers with Code, is Papers with Code. And then of course, you can go into here. This is one of my favorites, browse state of the art. You could come into computer vision. In our case, we could go image classification because we're looking up models for our image classification problem, and we can find the models that are performing the best. And so here we go, CFAR 10, VIT H14. That's a vision transformer. That's what we're working on. So there we go, VIT H14. Look at what paper that comes from. An image is worth 16 by 16 words. So we're using a state-of-the-art computer vision model, or we're going to be replicating one with PyTorch code. So let's jump back in. That answers the question for finding machine learning research papers. Let's now, in the next video, go over what we're doing. And we've kind of hinted at that, so we're not going to spend too much longer there, but we'll just make it concrete. I'll see you there. Welcome back. In the last video, we went through a few of my favorite resources. Now, this is definitely not an exhaustive list to find machine learning research papers and code, but here are four pretty great resources, and you'll definitely find more as you go through your machine learning journey. But let's now make it concrete of what we're doing. We've kind of hinted at this, or we've said it a few times now, but we're going to be replicating the vision transformer paper, or the VIT paper, with PyTorch code. And so here's the paper we've been talking about. An image is worth 16 by 16 words. Transformers, which transformer is becoming very popular and very effective type of neural network architecture for image recognition at scale. So this is the paper that originally brought in the transformer architecture for vision. Previously, prior to this paper, the transformer had been used mostly for NLP, or natural language processing problems, or problems dealing with text. So if you recall way back to, I think it was section 2 maybe, or section 1, I can't recall, but right back at the start of the course, we said there's some machine learning versus deep learning common algorithms, and we talked about the machine learning algorithms as typically being the best for structured data, and the shallow algorithms, that is, because the deeper learning algorithms are better on unstructured data. So this is like tables with rows and columns, whereas this is like audio and images and video. The more layers, the more chances you have to learn a representation of your unstructured data. So we did say, I did say that what we're focused on building with PyTorch was neural networks, fully connected neural networks, convolutional neural networks, and I kind of skipped out on the transformer, but I decided as I started making the rest of the materials, the transformer is getting too popular and too well-performing not to cover it. So we're covering a transformer, and not this kind of transformer, this kind of transformer, a vision transformer. So a transformer architecture is a convolutional neural network, uses convolutional layers for its main learning algorithm, whereas a transformer is generally defined as an architecture that uses multi-head attention or self-attention as its main learning mechanism. And if you'd like to read more about a transformer, you can read the paper, Attention is All You Need, or What is Attention in Machine Learning, or J. Alamar, Attention, there we go. These are all great resources. What is attention? Attention, what is attention? Attention mechanism, attention is all you need. This is the technical paper that you can read through that introduced the original transformer, but for text. A whole bunch of resources here for learning attention, and the illustrated transformer. So this is a great visual overview of what a transformer model is created with, but we're not going to be really focused on going through The technical details, well, we are going to be getting technical, but we're going to be focused on writing code rather than talking about overviews. So look at all this. This is a beautiful blog post. That's your extra curriculum. Alongside reading this paper, I'd highly recommend reading this blog post. You might not get many things the first few times you read them. I've read this paper probably half a dozen times now, and I still pick up on something new. But we're going to be focused on writing code so you can see what happens when we build a paper with code. So let's jump back in. That's what we're doing. We've got the vision transformer. We want to turn this into usable PyTorch code. And so specifically, we're going to take the vision transformer architecture and we're going to try it out on our food vision mini problem. So that's the project we've been working on throughout the last few sections, taking images of steak, sushi, and pizza, passing it through a computer vision neural network. Previously, we've been using convolutional neural networks and getting good results, and then we have some sort of classification output here. But we want to see, if we were a machine learning engineer, let's just pretend we are, and we want to get skills. Well, one of the ways to get skills would be to take the latest and greatest computer vision architecture published by Google Brain Research Team and try it on our own problem. In fact, maybe that would be a challenge that would be set if we were at a machine learning engineering role. It's like, hey, this new computer vision architecture came out a week ago. Can you implement that for the food vision problem? Well, let's give it a shot, hey? And so we've got our inputs. Now, this is a neural network, very customizable. We're going to be substituting in the vision transformer architecture. So this is the original VIT architecture, vision transformer. But if we turn it into food vision mini style, we might have something like this. We have an image of pizza. We break it up into patches. We'll see what this looks like later on. And then we feed those patches, or we embed them first and pass them through a transformer encoder layer, which is this, multiple times, a few layers here. We're going to go through this step by step, don't you worry. And then we pass the output of that to an MLP head. MLP stands for multi-layer perceptron, if you wanted to find out what that means. Multi-layer perceptron. As I said, there's going to be a lot of stuff here that I'm kind of just going to throw at you, but trust me, we can learn this all together. If you don't understand something, pause the video, search it up, read it, come back. If in doubt, run the code. So a multi-layer perceptron is a fully connected class of feed-forward artificial neural networks. So that's just the neural networks that we've been building. The term MLP is used ambiguously. Yeah, this is a little bit confusing. Sometimes loosely to mean any feed-forward artificial neural network. So in the case of the vision transformer paper, an MLP is a layer with, well, we can just search this up, right? Have a look at this. MLP, MLP, MLP. There we go. The MLP contains two layers with a Gelu nonlinearity. What the hell does that mean? Well, this is where we could get stuck on a little bit of a treasure trail. We can go Gelu nonlinearity. What is that? Gelu explained, papers with code. We could read that. We're not going to do that now, but just know that a multi-layer perceptron is some kind of neural network with a given number of layers. It could be any amount, but usually it refers to maybe one or two hidden layers. So yeah, I refer to as vanilla neural networks, especially when they have a single hidden layer. So a lot of things going on, but nothing we can't understand if we break it down step by step. And finally, let's finish off with what we're going to cover broadly. So we're going to get set up. That's how we'll start our code. We've written a whole bunch of reusable code in previous sections. So rather than rewrite that, we're just going to import it and run it. We're going to introduce machine learning research paper replicating with PyTorch. So we've kind of talked about that in a high-level overview. Now it's time to start writing code. We're going to be replicating VIT, the vision transformer, for our food vision mini problem. This is so exciting, taking state-of-the-art research, building it ourselves for our own custom problem. We're going to train our own custom VIT, and then later on, we're going to see if we train a VIT from scratch, so with our own custom data, does that perform as well as doing feature extraction with a pre-trained VIT or vision transformer? Now, this is transfer learning, right? Like what we covered in section 6. And how are we going to do it? Well, like we always do it. We're going to be cooking up lots of code. Just like a chef might go to a recipe and replicate it into an edible dish, we're going to, as machine learning engineers, go to this beautiful machine learning research paper and treat it as a recipe that we're going to turn into some usable code. So with that being said, let's code. I'll see you in Google Colab. Alrighty, let's write some code. I'm going to jump into Google Colab. And by the way, we've mentioned a whole bunch of stuff already. So if you want the resources for any of the links that we've searched or mentioned or things that we've talked about, such as paper replicating, what is a machine learning research paper? Why replicate it? Where can you find examples? What we're going to cover? Terminology, etc., etc. And now we're up to getting set up for code. You can, of course, go to Section 8 PyTorch paper replicating to find all the links you need. And then, of course, some extra curriculum if you want to dive in further for anything. But let's jump back up the top. We have to get set up. What we want to do is import some PyTorch modules. Now, as of July 2022, Torch Vision version 0.13 should be on Google Colab. So we're going to be using Torch Vision 0.13 plus, but let's stop talking about it. Let's just get involved at colab.research.google.com. I'm going to start a new notebook. Make sure I'm a little bit zoomed in here for the video. Beautiful. So let's title this 08 PyTorch paper replicating video. And now, of course, this will eventually live in the video notebooks folder, and the ground truth notebook is here. I've just appended the video tag so that you know that this is the notebook that we're working on through the videos. So let's go here. I'm going to call this 08 PyTorch paper replicating. Replicating, if I could spell, that'd be amazing. And so let's write down here, the goal of machine learning research paper replicating is turn a ML research paper into usable code. And as I've said a few times now, rather than just talk about replicating machine learning research papers in general, we're actually going to do one so that you can see what it's like to replicate a machine learning research paper from scratch with PyTorch. So in this notebook, we're going to be replicating the vision transformer, so VIT architecture / paper with PyTorch. Woohoo! And if you just search for vision transformer paper, you should be able to find it. If not, here's the actual title. All the links are in the resources, by the way, in PyTorch paper replicating. So if you see me jumping around a lot, just know that there's a ground truth for the resources. So I'm going to link to the abstract. So you'll notice an archive abstract link has ABS. If you link to the PDF, you can do that, except some browsers take quite a while to load the PDF. So mine's probably got this cache, so it loaded pretty fast. But what you'll notice over time is if you open up a new PDF, it can take a while if you're trying to read it on a new device. So it's often best practice to link the abstract instead of the PDF. And I'm just going to go here, abstract. And then we go, see, ground truth notebook here. And this is where all our materials are. So our first step in here is to get set up. So let's create a title, get set up. Now, we've done these steps a fair few times, but what we want to do is let's import code we've previously written plus required libraries. So most of the code that we created for this notebook in terms of the stuff that we want to use behind the scenes, we created in PyTorch going modular. So if we go to GitHub and we go to going modular, and then going modular, we want to import all of these scripts here, such as datasetup.py. This is going to help us create our data loaders. We've gone over this in previous videos, so we're not going to spend too much there. So what we essentially want to do is clone this GitHub repo and import all the code into our Colab notebook. That way we're not rewriting all of the same code that we've written before. So I'm just going to clean up some tabs here. And we can get the code that we need by going to section 0, getting set up. I'm going to copy this. All this block of code does is make sure we import Torch for PyTorch and Torch Vision, and make sure we have the right versions. Now, if your Google Colab instance doesn't have the right versions, it's going to download them. So just beware, you may have to restart your runtime once you install them. But before we do that, I'm actually going to set up a GPU. Save. So all I did there was runtime, change runtime type GPU. So let's run this. I believe as of July, current date, it is Friday, 29th of July, 2022. Oh, and this is giving away my location. Thank you for that. Well, I live in Brighton, which is a little suburb in Brisbane. It's a lovely place. So let's get set up. Torch version 1.2, and we have Torch Vision version 0.13. Wonderful. So these are the minimum versions we're going to need for this section. If you don't have these as a minimum version, you might have to install them you can go to pytorch.org. You can install them somehow. But if you're using Google Colab, you should be right. So get started. Yeah, we can install through there. 0.13. They should be the defaults on Colab. If you have later versions of those, they should still work with the code we're going to run. If they don't, let me know. So we've done the imports of Torch and Torch Vision. Now we need to import a couple of things, such as the helperfunctions.py file, which is here. That could really go in here, going modular. We could put all of the functions in utils. That might be a little extension you might want to try. So we'll go back here. Helper functions just has a bunch of different things, such as walking through a directory, plot decision boundary. We've seen all these functions before. There's nothing new in here that we haven't coded during the course. It's just a way to store them all so we don't have to rewrite them. So let's go back. Helperfunctions.py, we want to import that. We want to import download data and plot loss curves, and we created them in previous sections. There we go. Okay, so I'm going to copy this. And we're going to make sure we have all the imports. We're going to install Torch Info, which doesn't actually come with Google Colab, but we've seen what it does. One of my favorite Python packages for getting a model summary. So let's go here and we go run. Couldn't find Torch Info, installing it. I'll just let this run for a few seconds. Beautiful, there we go. So now with all this magic code here, we have our going modular, and there's datasetup.py, engine.py, modelbuilder.py, etc., etc. We're really only going to focus on using data setup and engine.py, or maybe utils later on, and then we've got helperfunctions.py. So we've got access to all of that, and finally we're going to set up device agnostic code. So I'm just going to get out of this little window here, and let's go device equals CUDA if torch.CUDA is available, else CPU. And we'll check the device. Beautiful, CUDA. So let's, in the next video, get some data. You might want to jump ahead and try it out yourself. There's the code there, that's a spoiler, but give that a shot, and I'll see you in the next video. How'd you go? Did you try it out? Did you get some data? Nothing too dramatically new here. We've covered this a few times now. So the whole goal of what we're trying to do here, let's write it down. The whole goal of what we're trying to do is to replicate the VIT, so Vision Transformer, which is a computer vision architecture for our food vision mini problem. And in fact, this is milestone project 2, so I should probably put that up here. Let's go milestone project 2, PyTorch paper replicating. Bit of a challenge to replicate a paper, but nothing we can't handle. So to start, to do that, we need some data. Namely, the pizza, steak, and sushi images we've been using so far. Because one of the reasons you would try to replicate a machine learning research paper, such as the VIT paper, is if it's published and it says Vision Transformer attains excellent results compared to state-of-the-art convolutional neural networks, while requiring substantially fewer computational resources to train, well, that's pretty attractive then, isn't it? Because if this is getting released as, say, hey, we've got a new architecture set up, computer vision architecture that gets state-of-the-art results on a benchmark, say ImageNet, you might go, hey, I'm working on a computer vision problem. I might want to try that neural network for my own problem to see if it does work. So that's one of the whole premises. We're getting the same data set so that we can compare apples to apples, or in our case, compare computer vision model on pizza, steak, and sushi images. But we don't have any data yet. So let's come over to here. We've got some helper functions. We can copy in, download data. Now, there's nothing really dramatically new here of what's going on behind the scenes. Download data is a helper function contained within helperfunctions.py. So let's have a look. We actually created this one in, I believe it was section 7. Yeah, download data function from helperfunctions.py in PyTorch experiment tracking section 1. Get data. Yeah, here's where we created that function, right? That's what's going to happen. So behind the scenes, this is what's running. Let's just see if it works here. If in doubt, run the code. We should get an image path back. Shouldn't take too long to download. Wonderful. Now we get some images. We now have data, pizza, steak, sushi, test, and train. We've set ourselves up basically already for the entire project. We want to replicate the vision transformer architecture, this fun little graphic here, for our food vision mini problem. So we want to figure out, how do we get that data? How do we get these images of pizza, steak, and sushi through the vision transformer? So we've seen how to process these before and turn them into data loaders. And in fact, we'll probably do that in the next video. But let's finish up by creating the training and test paths to our data. So trained-dir, this is just code we've written before. We'll bring it in here. Trained-dir equals image path slash train. Test-dir equals image path slash test. And I think that's all we need for this video. Yeah, we've got some data sets now. Trained-dir. I'm going to go a bit faster through the stuff that we've already covered and then spend a little bit more time on the things that we haven't covered. So now we've got some data. What do we have to do next? Well, we typically turn it into data loaders. So if you want to give that a shot, we've got a function within going modular. We've got data setup.py, and we've got our create data loaders function here that we've used before. So give that a shot, and we'll do it together in the next video. Welcome back. In the last video, we downloaded some data for our food vision mini problem, and we've got a training folder and a test folder. And I issued you the challenge of seeing if you could use the create data loaders function to turn our images into PyTorch tensors and then into PyTorch data loaders. So I hope you gave that a shot, but let's now do that together. And there's a little trick here. Our first step of actually replicating this paper is going to be in this section. And I didn't give you that, but hey, surprises are fun, right? Create data sets and data loaders. So we've got a function. I just closed it, didn't I? Going modular, create data loaders, data setup. Now our function create data loaders takes a transform, and we've got the transform, which is a Torch vision transforms to perform on training and testing data. So we've made transforms before, but let's start by going modular. The whole point of a transform is to do what? Is to transform your data in some way, shape, or form to prepare it for a neural network. Let's import data setup. In our case, we want to turn our images into tensors. So let's go data setup. If we were to call create data loaders, are we going to get a doc string here? Or do we have to run this? Maybe we have to run this. Create data loaders, missing 4 requirements, and we don't get a doc string. Okay, that's all right. We know what we need. So we need to create an image size. Previously, we've been using 224 for our image dimensions. Just bear with me for a second. We're going to bring this all together. But what are we trying to do? We're replicating the vision transformer paper. So if we really wanted to replicate this properly, we should see what size of image does this paper use. Now, if you've done your extra curriculum, your homework for reading through this, you might have found it, but it is actually a bit hidden. It's actually kind of a bit of a treasure, as you'll see many details in many papers are quite treasures, because look how much information is here. We're on page 13, right? We're page 13 already before we find out what the training size is. Now, the only reason I knew where to go is because I've read this a few times. So, hence my sort of workflow for replicating papers is to read through it at least once and then go back through the major tables and see if there's any information that sticks out to me. Now, this one is probably the first piece that we need to bring out of the paper. Training resolution is 224. That means that our images will be processed into 224 by 224, or height and width. So if we're going to use the Vision Transformer architecture in the state that it was introduced as, we want to make sure our data is pre-formatted in the same way that the data was pre-formatted for this architecture. There's another little tidbit here you might see, which is a batch size of 4096. Now that is a huge batch size. So if we were to go 4096 divided by 32, which is our regular batch size that we've been using, that's 128 times bigger. Now, since we're using a singular GPU on Google Colab, we don't necessarily have the memory there to store batch size of 496. So let's see what GPU I have. Now, just recall I'm using Google Colab Pro, so I might have a better GPU here than the default. So I've got 16 gigabytes. So that's pretty generous. However, what you'll often find is that machine learning research papers, especially ones from big companies such as Google or Meta or OpenAI, are trained with a fair amount of compute. So what you'll often have to do is if you're replicating it, you'll have to start small. So in our case, we can use a training resolution of 224, but we're going to reduce the batch size to 32 to begin with. So a lot smaller, but that's just because of the hardware that we're using. So that's the motto, start small, scale up when necessary. So this comes from table 3 of the VIT paper. So you're going to see this is going to be a little bit of a trend as we go through this replication. We're going to be jumping back and forth between the paper and the code. Again, all of the details you need are structured in PyTorch paper replicating or the actual PDF. We're going to be focused on here on just writing pure code rather than explaining what's happening. So let's create transforms pipeline now. Our transforms, we're going to make it manually. Previously, we've seen how to create transforms automatically when using a pre-trained model from torchvision.models. But we want to go transforms. I'm going to just import from torchvision, import transforms, compose. And then the first one we're going to do is a transforms.resize so that all our images are in the correct size. Image size, image size. This will just turn out to be 224, 224. And I've hard-coded this as capitals because you might want to change this later on, but to begin with, we can just set it as the default 224, 224. And then the only other transforms I'm going to use is 2tensor. So that's going to turn our images into 224 by 224 pixels and make sure that they're torch tensors. So let's find out what our manually created transforms look like. Manually created transforms. Manual transforms. What did we get wrong here? Resize transforms. Torch Vision transforms has no, oh, we need a capital R. Excuse me. There we go. Beautiful. Now, what can we do? Well, we can turn our images into data loaders. As I said, we're going to create a batch size of 32. The paper uses 4096, but this may be too big for our smaller hardware. Can always scale up later. So to begin with, we're going to start small as possible. We'll see this later on when we create a VIT base. I'm jumping ahead here, but I feel like we're up to it. Table 1, and there's 3 variants of the VIT model. You can see they all have different numbers of parameters. Starting with the smallest, we're going to be focused on building the smallest version of the Vision Transformer first, because if you build the smallest one, well, you can always scale up later on. So, batch size, I'm going to set this as 32, and then let's create data loaders together. Create data loaders. I mean, you might have already done this, so that's why I said create it together. line by line, replicating a PyTorch, or replicating a machine learning research paper with PyTorch. Excuse me, I don't know what that was. Create data loaders. And then we go train dir. We'll set up our training directory, and we'll set up our testing directory. And then we'll pass in our transform. See, this is the beauty of writing reusable code. Transforms, is it manual transform? Transforms, yep. So it's manual transforms. And then finally, we'll set the batch size to equal batch size. Create data loaders, yeah. That's the beauty of saving our code to scripts, datasetup.py, so we don't have to rewrite all of that stuff there. Now, let's go back to the notebook and we'll run that. Just gonna bin that so we have more space. Wonderful. So let's check out the length of each one. Train data loader should be about 8 or so. Test data loader is at about 3 maybe from memory. And class names, do we have what we want? Yes, we do. So we have 8 batches of 32 or thereabouts for our training data loader. We have 3 batches of 32 or thereabouts for our test data loader, and we have pizza, steak, and sushi as our class names. Now, we've created our data loaders, but you know me, I always like to visualize. So how about we visualize a single image, just to make sure we've got the right stuff on the go. Visualize a single image, and this is, as always, let's adhere to the motto, visualize. I might actually issue this as a challenge. So your challenge for the next video is to iterate through our training data loader and visualize one of the images. And that way we can actually use that image throughout the rest of the notebook as the demo image. So save a single image and its label to a variable, and then plot that single image and its label as a title using matplotlib. So that's your little challenge. Give it a shot, and I'll see you in the next video. How'd you go? Did you visualize a single image? Was it pizza, steak, or sushi? Well, I hope you gave it a shot. Let's now do it together, hey? So we'll start by getting a batch of images, because we turned our data, our images, into data loaders, which is batches of images and labels. So we'll get an image batch and a label batch to go along with that. And that'll be in next iter. We turn it into an iterator. So this is take train data loader, turn it into a Python iterator, and get the next sample from it. And then we can select a single one. So get a single image and label from the batch, and we'll just get the first one, hey? Image label equals image batch, we'll index on the above, image batch 0, we get the first one, and label batch 0. And then finally, we can view the batch shapes, just for fun. Always good to check out shapes. And image shape.label, yep, that's what we need. Oh, we're not really viewing the batch shapes there, are we? We'll view the single shapes, single image and label shapes. So we've got an image shape of 3 for color channels, red, green, and blue, 224, 224 for our image, which is in line with the image size that we set here, and also in line with the VIT paper for table 3. If we go back up here, training resolution is 224. That's what we're focused on doing. And there's our label, which is just a scalar, which is 0. So let's have a look at the plot of that image. So we'll go plot the image with matplotlib. Now we imported matplotlib before. We want to import matplotlib.pyplot as plt. And then we can go plt.imshow, and we go image. We have to permute it though, because matplotlib likes color channels last. So I'll just write this down. We want to go from color channels, height, width. This is what permute does. I'm just going to change the order of the axes to, or the dimensions to have the color channels on the end. That's why we go 0 on the end there. Then we go plt.title, and then we can go class names. We pass in the label. Label is just there. We're just going to index on the class names list, and we'll go finally plot. Do we want the axes? No, we don't. Just to make it nice and clean. Wonderful. We've got a pizza. Now, that's a all right looking pizza. Can we get one that looks a little bit better? That's a steak. It's always fun visualizing images. There's another steak. Let's get a good looking image, hey? Of course, this is always going to change because it's random. Okay, this one looks good to me. So we've got our image. Looks like our images have been loaded correctly. Now, let's start to... I think the only next step is to start talking about how we're going to replicate the vision transformer. We're going to have to put a few pieces of the puzzle together. And the main one is the vision transformer figure 1, because it's nice and visual. And we can see that we have some sort of input and we have some sort of output. But let's start to break this down, hey? I'll see you in the next video. Welcome back. In the last video, we visualized one of our samples of data, a lovely image of pizza. This might change because of randomness, so don't worry if you don't get the same one, because our data is going to be loaded randomly. We just needed an example to look at. But now let's start to move towards recreating the vision transformer architecture. So we're going to spend the next couple of videos, I'm not sure how many, kind of breaking this down to give an overview, and then we're going to start writing code to sort of match that overview. But we've got a few pieces of the puzzle here, and we're going to be jumping back and forth. Of course, the whole paper is pieces of the puzzle together, but the main ones we're going to be concerned with is figure 1. So this is the visual overview of the architecture. And then we have a method here. So section 3.1, if you want to read anything in the paper twice, I'd recommend reading section 3.1. So this is text. Then we have 4 equations. So these 4 equations make up each of the layers in mostly the transformer encoder layer over here, but they make up the vision transformer. We're tying everything together. It's kind of a little bit higgledy-piggledy, but that's all right. We'll bring it together. 4 equations. And then finally, we also have table 1. So I love how they're all on different pages as well. Now, we're going to be focusing on building VIT base, which is the smallest version of the vision transformer. But we're going to build it in a way that if we wanted to increase the hyperparameters, these values here are hyperparameters. Why are they hyperparameters? Because we can set them ourselves. If we wanted to increase from VIT base to these larger versions, we could do that. So let's jump back into the keynote. Yeah, that's where we want to go. What's the next slide? Oh, I should have shown you this before, but this is table 3, just extracted from the VIT paper. And a little treasure here, we've got batch size 4096. This is what machine learning paper replicating is all about. It's treasure hunting. We need a treasure hunt for the right steps and ingredients to build our vision transformer. And then there's an image size 224, 224. So height is 224 and width is 224. And there's a whole bunch of different details. We're focused on this one. VIT should be a B there, a patch size of 16. We'll get to all of this. We're not training on ImageNet because we haven't downloaded ImageNet. And we're going to do a smaller version of these parameters. But if you'd like to do more research, you're more than welcome to figure out what these are. But here's how I break things down with almost all kinds of neural networks, machine learning models, whatever you name it, deep learning architectures. I break it into inputs, outputs, layers, and blocks. So what are the inputs to your layer to generate some outputs? And now often, or very usually, a layer contains some kind of function to manipulate an input. So an input here could be an image, it could be some text, but not in image or text form, it's in numerical form. And it goes into a layer and it gets manipulated by some internal function such as attention. Now, this is the self-attention formula, which is what the vision transformer and all transformers usually use, is it takes 3 inputs, a query, key, and value, performs a softmax on the query times or matrix multiply the key transposed over the embedding dimension. We're going to see all these later, the square root of the embedding dimension, times V, which is the value. And a little bit confusing is that sometimes query, key, and value can be all the same, hence the term self-attention. Now, if we look up self-attention formula, we might find it, images, there we go, something like that. Basically the same, yeah, there's the same formula as we've got in the Keynote, same formula here as here. And if you want to research, you can go explained. We're going to focus on writing PyTorch to build this. So let's jump back. We're breaking this down. So that's a single layer. A single layer has some inputs and some outputs, and the inputs get manipulated by some sort of function. An example function could be attention. And in the case of the vision transformer, this is actually used in the architecture. Then we build it up from a layer to a group of layers into a block. So a block is a stack of layers, but if a single layer takes inputs and outputs, then a block also takes inputs and outputs, because a block is just a stack of layers. Now, the number of layers in here is arbitrary. I've just put 3 because it looks pretty, but you could have 5, you could have 10, you could have 2. And if we jump back into the vision transformer, we're going to be doing a fair bit of jumping around, but we can handle it. A transformer encoder block might have 1, norm, multi-head attention, 2, 3, 4 layers. So this is a block of 4 different layers. But if we go back here, again, the number of layers in a block can generally be arbitrary. And then if we go again, we have inputs. We want to stack multiple blocks on top of each other. We get a model. So a model is a stack of blocks, but the same principle remains. And we've seen this. We've seen this by building neural networks throughout the entire course, is that we have some sort of inputs. In our case, it's going to be images. And we want our outputs to be labels or classification labels, such as pizza, steak, and sushi. But these inputs could be almost anything you could imagine in machine learning, as long as you can define your outputs. Now, the whole goal is to build up layers, blocks, and a model to map from the inputs to the outputs. And the important thing, behind the scenes, the model learns the mapping from the inputs to the outputs. So even though we've got quite a task in front of us, as 22 pages of research code, the same premise remains. We have some sort of input, we have some sort of layers and block combination, and then we have some sort of output here. This is a block. We've got L times X. Then we stack a number of blocks on top of each other into this section here, and we have an overall model. So this is kind of what we're going to be using as our high-level overview. We have inputs, some data, some outputs, some manipulated data, layers, a function to manipulate an input, and a block, which is a group of layers, and then a group of blocks makes up our model architecture. So let's go and write this down. This is 3, which is replicating VIT overview. So I'm going to write, looking at a whole machine learning research paper can be intimidating. Thank God this is not a spelling bee. We're focused on writing code here. So, in order to make it more understandable, we can break it down into smaller pieces. That is the key there. We break it down, we break the paper down into smaller pieces. We go treasure hunting. We find the treasures in here, we find the different layers, we find the different blocks, we stack them together like Legos to build a vision transformer or whatever architecture you're working with. So we have inputs. What goes into the model? So in our case, we have image tensors or batches of image tensors. And then we have outputs. So what comes out of the model slash layer slash block? In our case, we want the model to output image classification labels. Now that may vary per problem, but we're focused on Food Vision Mini at the moment. And then we have layers, which is every deep learning neural network is comprised of a number of different layers. And so it takes an input, manipulates it with a function. And the function, for example, could be self-attention, which is what's inside the vision transformer. And then we're going to have blocks, which is a collection of layers. And then we have a totem model, which is a collection of blocks. Beautiful. So spend a little time revising that and just have a look. The homework for this video is to just have a look at this for 2 minutes and read through it, and then just step through it and follow the arrows through. So do that 2 minutes, and then we're going to go through this a little bit more over subsequent videos. In fact, the whole entire section is about reproducing this with PyTorch code. So we've got inputs, outputs, layers, blocks, model. Let's make this colorful, hey? I'll see you in the next video. 5, 4, 3, 2, 1. Welcome back. In the last video, we spoke about the concept of breaking a whole machine learning research paper, which can be quite intimidating to look at, into smaller pieces. And our goal is to put together these smaller pieces, or to build them piece by piece, and then put them together like Lego bricks to create the entire model. Another word here is or architecture. So let's make this a little bit colorful. We'll jump in here. There's our graphic for inputs, outputs, layers, and blocks. Let's reflect back on what is paper replicating. This is one of the first slides we looked at. So we have images, math, and text. And so we're going to start breaking the vision transformer architecture into different pieces of the puzzle. So we've had a look at figure 1, and if you did a little bit of a homework challenge, I said to look at this for 2 minutes. And that's okay. We're going to get heaps of practice with it. So even if you didn't do it, I mean, I hardly do my homework anyway. I only do really what's fun. We're going to start writing code, and that's the fun part. So we want to end up with something like this. There's a lot going on there, so we're going to not really look at that for now, but it sort of looks like what we're heading towards. But this is the pieces of our puzzle. We have figure 1. There, look at that little transition, pieces of the puzzle. We have figure 1, and we have 4 equations, and we have text. We actually have one more that's not really pictured here, but that is table 1. So we'll go here. Table 1. So we'll come back. Let's do a little section in the Colab notebook. And I'm going to break this down into Vit, overview, and this is pieces of the puzzle. So when I say this is a generic overview for many machine learning architectures, but now we're going to start get specific and what is Vit made of itself. So we have 3 main pieces of the puzzle, or 4 really, but we have figure 1, which is visual overview of the architecture. Then we have the 4 equations, which are math equations, which define the functions of each layer / block. And then we have table 1. We really have table 1/3, which is different hyperparameters for the architecture / training. And then of course we have all of the text around it. So let's start off by having a look at figure 1. So we're just going to go figure 1, and then we'll have a look at the 4 equations. We're not going to do all of them in this video. We're going to break this down over a series of videos because this is really breaking down the entire thing. And then table 1. So figure 1, I want to get an image in here. Here's one I prepared earlier. If I go to the GitHub repo, into images, and then if I search, we should have a figure 1 here. Figure 1, there we go. Architecture overview. So I'm going to click the download link here and copy the raw link, just so we have a copy of this in our notebook, so we don't have to keep jumping back and forth to the paper, even though we probably will keep jumping back and forth to the paper. Then we'll get the 4 equations. So we'll go over here, I'm going to search for 4, VitPaper 4 equations. Click the download, get the raw version. Can copy that, XX, and copy that there. And then finally, let's get table 1 as well. Oh, I love this. We're going treasure hunting here. Table 1. Do we have table 1? Yes, we do. VitPaper table 1. Now, of course, all of this is from the original VitPaper, so I'm not claiming it to be any of mine, even though it's in my repo. There we go. Okay, so here's our pieces of the puzzle. We have figure 1. We want to first map our Food Vision Mini inputs and outputs to this, so we'll probably do that first. Then we have 4 equations. These define what happens or make our layers sort of mathematically complete. We see the different inputs and outputs here. Z0, which stands for logits, or the inputs, this is an embedding here. We're going to cover this later on. And then we go to the next layer. So this gets inputted to here, and then this gets inputted to here, and then this gets inputted to here. And then we have hyperparameters for our different models. We're going to be focused on Vit base. So with that being said, let's jump into making figure 1 colorful. So this is the overview of Vision Transformer, inputs and outputs. One of the first things you should do when inspecting a machine learning research paper or any new architecture you've never used before is figure out what goes into the model and what comes out. So in this case, we have a Vision Transformer. An image goes in and it looks like it gets cut into different patches here, and then it gets manipulated by a series of transformer encoder layers. This over here is a blown up version of this. So all these layers here are what's inside there. And then it looks like the outputs are some class names. And we've got class bird, ball, car because the Vision Transformer was originally trained on ImageNet. However, in our case, what classes might we have there? We're going to see that later on, but let's just map inputs we've got here. So this is our input. We split an image into fixed size patches. A little bit of a clue there. How do we do that? Linearly embed each of them and add position embeddings. What's a linear embedding? What's a position embedding? Don't worry, we're going to cover all this later on. And feed the resulting sequence of vectors to a standard transformer encoder. What's an encoder? Well, let's make some definitions here. An embedding, we might write this down in a second, or a linear embed, or a learnable classification token. Anywhere where you see linearly embed, or embedding, or extra learnable something, it's a learnable representation. So rather than just, we're going to split our image into patches. So rather than just inputting the pixel values of our image into our transformer encoder, we want to embed them, so turn them into a learnable representation. And we're going to see this later on, but let's just define it in figure 1. So figure 1, we want to, or maybe we won't, make a bigger heading here. These are important pieces of the puzzle. So embedding equals learnable representation. So start with random numbers and improve them over time. So that's an embedding. Embeddings are one of the most powerful concepts in all of machine learning. And then we jump back into here. Now, MLP, a lot of acronyms in this paper. Multi-layer perceptron, we saw that before. Multi-layer perceptron is generally a stack of a couple of layers on top of each other, but the number of layers could be arbitrary. In the case of the VitPaper, we see that it's going to be 2. We'll see that later on. So this is the outputs. You see how we've just mapped our inputs and outputs? First thing, whenever you're dealing with a new research paper, what are the inputs? What are the outputs? In order to perform classification, so okay, that's a clue to us. This is a classification model. We use the standard approach of adding an extra learnable, wherever you see the term learnable, it's an embedding, classification token to the sequence. Okay, let's see what that looks like later on. And then we map the layers. So each one of these can be considered an individual layer. So the embedding, how we create the embedding, the image embedding, normalization layer, that's what norm stands for. multi-head attention. We have another norm layer. And you might notice this arrow here. This is a connection. This means that the output of these two layers, which is here, the input to those gets added to it here. And the same thing with this connection here. That's known as a skip or residual connection. We're going to see that later on. I know that this is going to be a lot to take in for now, but trust me, we're going to work through this together. Then we have another normalization layer and another MLP layer. And if we combine these, we get blocks. So we have a block here. This is in the paper known as the MSA layer or MSA block, which is a norm layer coupled with a multi-head attention layer. Recall that blocks are a stack of layers. And then we have another block here, which is an MLP block. And then so within this transformer encoder, it is a block in itself comprised of other blocks. And then we stack together, this is that LX, we stack together multiple blocks of the transformer encoder to create the overall model. So a lot going on here, but we've broken this down into inputs and image. The image goes through a series of layers and blocks, and then we get our outputs. Let's now convert this to Food Vision Mini style. We have this image of pizza, gets turned into patches, goes through this series of layers, and then hopefully outputs the pizza class. So this is what we're going to be working towards, replicating all of this for our Food Vision Mini problem. Whew, that was a fair bit to take in, I know. But step by step, we're going to be writing code to reproduce this. In the next series of videos, we're going to be going through the 4 equations and table 1, but I think we might start to... Actually, no, yeah, let's give a high-level overview of the 4 equations in table 1, and then we'll start writing some code. Otherwise, we'll be a bit too much all over the place, even though we kind of already are. So we just gave an overview of figure 1. Let's move through these 2 next, and then we'll write some code to replicate it all. I'll see you in the next video. Welcome back. Now, we're slowly putting together the pieces of the puzzle of the VIT architecture. And we've broken it down to 3 main pieces, being figure 1, the 4 equations, and table 1 and table 3. So in the last video, we broke down figure 1 into inputs, outputs, layers, and blocks. The next thing we're going to do is move towards breaking down the 4 equations. Now, if you are not familiar with mathematical notation, not to worry, it is just like another language like programming to learn. But what each of these equations defines is what's happening behind the scenes of each of these colored blocks. So I want to show you a trick before we jump into each of these of how I deal with mathematical notation and replicating papers in general. So if we come into the VIT paper, we've got section 3 method. Now 3.1 breaks down what goes on behind each of the equations. So we have an overview of the model is in figure 1, which is what we saw before. This is figure 1. And then if we keep reading through here, I'm not going to read it verbatim, this will be your extra curriculum. But if we start off with just an example, the standard transformer receives as an input a 1D, one-dimensional, sequence of token embeddings. So this is the sequence here. We've turned an image into patches and then into a sequence of patches. We're going to see how this works with code later on. So to handle with 2D images, we reshape the image. X is an element of a real number with dimension h times w times c. Where have we seen those letters before? That's height times width times color channels. And the reason why I know how to sort of read these, and in fact, there's a lot of mathematical symbols I don't know how to read, but I've just had a lot of practice reading symbols like this. And do you remember what the small non-capital letter means? It's often a vector. So we have an input image, but in this case, it's kind of confusing. So X is just the input in this case. And a capital is often a matrix. But again, the nomenclature here is a little bit confusing. But let's just say we have an input image X, which is an element of a real number. So all the numbers that comprise X are real, of the dimension height times width times color channels. That's just our input image. And then we convert it into a sequence of flattened 2D patches. So we have flattened patches here. We convert the image into patches. We'll see this with code later on. I sound like a broken record, just reiterating that we're going to turn this into code. And so then xp, p is for patch, is an element of a real number of shape n. We don't know what n is just yet. We haven't read it yet. Times p, I believe p might be patch size, squared because the patches are squares. So it could be patch size here, squared, and then the dot product of the color channel. So we can write some code later on to figure out these input and output shapes by hand. In fact, that's actually going to be a really good piece of practice. So if we keep reading here, where HW is the resolution of the original image, so that might be height and width is 224 pixels. C is the number of channels, so color channels. PP is the resolution of each image patch, so the patches are in squares. So patch width and patch height. And I'm sorry for jumping around a little bit, but we're trying to explain some non-linear information, as in this patch is related to this text that's expressed in a linear format. So it's a little bit hard to jump around, but we'll see some visualizations later on. Is the resolution of each image patch. And n, so n is this n up here, equals height width divided by patch squared. Okay, so that's how we can work out how many patches are in an image. So the number of patches, which also serves as the effective input sequence length for the transformer. So this will be, n will be how many patches we have here, the length of this sequence, which is the input into our transformer encoder. So let's keep going. We'll just finish this paragraph and I'll let you read the other 2 or 3 as extensions. The transformer uses constant latent vector size D, so this is going to be latent vector size, might be an embedding vector, for example, through all of its layers. So we flatten the patches and map to D dimensions with a trainable linear projection. So trainable linear projection here means embedding or learnable embedding, which is, if we look up here, linear projection of flattened patches. So we split the image into patches, turn those patches into a sequence, so flatten them, and then embed those patches into a linear projection of flattened patches, and that's going to be our input into our transformer encoder. But of course, we add a position embedding and a class token embedding. We're going to see those later on. So one more sentence here. We'll just reread this. So we keep the latent vector size D through all of the layers. So we flatten the patches and map to D dimensions with a trainable linear projection. That's equation 1. See how this paragraph is explaining what's going on in equation 1. We're going to look at each of these individually over the upcoming videos. And then we refer to the output of this projection as the patch embeddings. Okay, so equation 1 deals with the patch embeddings. So if you want to read on with these 3 paragraphs here, these are what explain equation 2, equation 3, and equation 4. So if we see here, the transformer encoder, Vaswani et al. 2017, so that's the original Attention's All You Need paper, consists of alternating layers of multi-head self-attention, MSA, so see Appendix A for a definition, and MLP blocks. So we've got MSA, multi-self-attention or multi-head self-attention, and MLP. So that's equation 2 and 3. And then if we keep going, layer norm is applied before every block and residual connections after every block. So there's a lot of information to take in here, but I'd encourage you to read back through section 3.1. What I like to do is when I'm replicating papers is I like to get this text into where I'm working. So, what you might also see is I've just replaced, in the previous video, we turned these images into markdown image tags. I've turned them into HTML image tags, so I can adjust the width and add alts here, so alt comments. That way screen readers can read out what's going on with the image. So now let's copy in section 3.1. This is my trick. If we just copy this, it doesn't format too well. Because see how there's a lot of symbols and whatnot? Yeah, look at that. We've got all that extra stuff. If we bring that back into here, look, that's just a big blob of text. We don't really know what's going on there. So let's delete this. One of my favorite tools is MathPix. And like all good cooking shows, here's some text I've prepared earlier. So if you read through all of this, this is all information from the VIT paper. See, I've got VIP paper replicating. You can create one here. I'm not going to do a complete demo of mathpix.com. I'm just going to show you what we're after. So this is just an editable notebook here. So if I type in something, yo, what's happening? It's going to appear on the right there. But I'm going to delete all this text just to give you a demo. And this is what I like to do. This is a beautiful tool. So if 3.1 is explaining the 4 equations that we'd like to break down, I might want to take a screenshot here. So I'm going to take a screenshot of what's going on. That's going to appear down over here because I'm using a Mac. And then I'm just going to drag this over. Looks like it's working. We'll just let this load. And oh my goodness, look at that magic. So you see here how we've got all these little dollar signs and all these math RM times, H times, math BF. I think that means math bold font. You can correct me if I'm wrong. But this is, I never really learned how to write LaTeX. This is what this is, LaTeX. So if we look this up, LaTeX. And that's how a lot of papers are written. Okay, so don't search LaTeX in images. I mean LaTeX as a document preparation system. So this is a way to write the formatted text as you see here. So now I've copied this over into mathpix.com and I can just copy this exactly how it is because Colab notebooks support LaTeX. And I might just break this into another cell, table 1. Okay, Command M minus in Google Colab to break another cell. And I'll break this into another cell, Command M minus. Beautiful. So this is what it describes equation 1. I'll just put this as section 3.1 describes the various equations. So we have a description of equation 1 here. We're going to go through these one by one in a second. Then we have a description here of equation 2. Or equation 4 actually. Yeah, see how it describes? Things are kind of out of order here. And then this is equation 2 and 3. And this is also a little bit of equation 1 here. So that's my trick for this video. We've read about equation 1. We haven't replicated it just yet, we've just read about it. And this is important. It's going to take you a few times, and it took me a few times to really realize what was going on, what's happening here. So for your extra curriculum for this video is to read through section 3.1 again from end to end, including the equations here. And don't worry too much if you're not familiar with the math symbols. Just read through it once or twice. And then if you want to, you can try out mathpix.com. You can get all of the text. This is going to use OCR behind the scenes and computer vision to break it into editable text so that we can copy that into our notebook. And we're going to come back over the next few videos and go through each one of these equations one by one. So I'll see you there. Welcome back. In the last video, we started to break down the 4 equations. And these are what describe what's happening behind each of these colored blocks here. And we learned that if we use mathpix.com, so if we go to mathpix.com, we can turn science or text, including handwritten math symbols, into editable text. And we also learned that many papers are written with LaTeX, which is a way of producing mathematical equations. Google Colab uses Markdown, but it also supports LaTeX, and LaTeX is between these dollar signs here. And be careful if you're searching LaTeX and you go to images, you might get something that is not what you were looking for. So let's get out of a few of these things. We'll come back into here. Let's start to break down equation 1a. We'll jump into the keynote. So we've looked over the VIT architecture in figure 1. We're slowly breaking it down. So reading a machine learning paper in its full can be a bit of a daunting task. So what we're doing is we're breaking it down. Figure 1 describes with colorful blocks the inputs, outputs, layers, and blocks. Paper reading, here's my tip, math to text, is you can use mathpix.com to turn a screenshot into editable text. There's the equations that we have. Then if we keep going, let's start to break down each of the 4 equations. We're going to do these one by one. We're going to focus first and foremost with equation 1. What I might do is reorder this text. So equation 1, And then equation 4, I'll put down the bottom. Beautiful. So there we go. And let's jump back into the keynote. Let's see what we have. So here's our 4 equations from section 3.1, and this is figure 1, section 3.1. Getting a little bit confused here. As you see, we're trying to describe nonlinear information, like as in this is all related, all of this information here, but the paper presents it in a linear stream of pages. So let's start to map things. So we split an image into fixed size patches, and then we embed those patches. So we've got the patch embeddings here. This is the original image split into patches, turned into a sequence. Then we embed those patches, and this is equation 1. However, there's a little bit more going on behind the scenes of this equation. So what you'll notice is that there's an extra learnable class token embedding here. So this is X class, whereas the embedded patches, we have X patch 1, so that would be that. X patch 2, the E here is for embedding, by the way, is this one. And then so on and so on and so on until you get to XNP, so X patch N E. There's a lot of letters going on here, but N is number of patches, P is patch, X is the input. So it goes all the way up, so dot 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 means all the way up until N, number of patches. Then what do? Well, we've got the classification token. So that's this little star at the start, and that goes right at the front here. So we need to first create a patch embedding, a learnable patch embedding of the image, which is this. That's what we're going to work on first. Then we need to prepend a learnable class token. So this, we follow the standard approach of adding an extra learnable classification token to the sequence. And then what do? We also add position embedding. So we see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now this will depend, of course, this is just for visualization purposes. This will depend on how many patches you have, but this figure uses 9 patches. And then we add that position embedding to the combined X class token learnable embedding and the patch embeddings. So then we get the overall patch plus position embedding. This is equation 1. That is our input into our transformer encoder. And so if we go back to read the description of equation 1, do we get what it was talking about there? So we've got X1 patch embedding, X2 patch embedding, all the way up to Xn. So there's N. N is the resulting number of patches, which also serves as the effective input sequence length for the transformer. Wonderful. The transformer uses content latent vector size D throughout all of its layers. So we'll see that later on in table 1. There's hidden size D. So that's going to be the embedding size that we project these patches to. Then if we keep going, so we flatten the patches and map to D dimensions with a trainable linear projection. So that trainable linear projection is a learnable embedding representation of our input. We refer to the output of this projection as the patch embeddings. So the patch embeddings here is this pink block. Then we have the class token, and then we have the position embeddings. So if we come back, we've got position embeddings are added to the patch embeddings to retain positional information. So what it means by positional information is what order did this patch of image come in? And we use standard learnable 1D position embeddings since we have not observed significant performance gains from using more advanced 2D aware position embeddings. So you can see Appendix D4 for more. The resulting sequence of embedding vectors, so this entire sequence here, serves as input to the encoder. So there's the embedded patches, and there's the encoder. So let's just to finish off this video, we'll do it in pseudocode. This is what I like to do. Equation 1, we'll put a line here to separate. So in pseudocode means just like fake code, but looks like it could be code. So let's just say we have X input, which is our image. I'm just going to zoom in a little bit there. So X input is our input image. What we're going to end up with is something like this. Class token, which will be a learnable embedding, a learnable vector. Image patch 1, image patch 2. And then we'll go ... because that's going to go up to image patch N. So that's the first half of equation 1. And then we're going to add the class token pos embedding, and then image patch 1 pos embedding, image patch 2 pos embedding, and then we'll go same thing, dot, 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 all the way up to image patch n pos. And that is going to be the input vector to our transformer encoder. So if we have equation 1 in pseudocode, we have x class token, we have image patch 1, which is this, the embedding, we have x2 patch, image patch 2 embedding, and we have dot, 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 all the way up to image patch n, plus we add the position token for each of the elements in this vector. We'll see this in code later on. We're just doing a high level overview here. So we've got class token, learnable class token. We've got patch embeddings, learnable linear projection of flattened image patches, and we've got position embeddings to retain the position of where the class token appears and where the image patch appears, in what order. So that's equation 1. You might want to give yourself a challenge and see if you can do the same sort of mapping we've done here for equation 2. MSA, I'll give you a hint. It deals with this block here. MLP deals with this block here. And LN, or equation 4, deals with this block here. So give that a shot. But in the next video, we're going to start to break down equation 2, and then we'll do 3 and 4. I'll see you there. Welcome back. In the last video, we did the very, very exciting thing, even though there's a lot going on, of breaking down the first equation behind the vision transformer. So let's keep going. We're going to break down equations. Why don't we give 2 and 3 a shot in the same video? Because they're quite similar. So let's see where we're going here. We have the transformer encoder, which is this big block here, the gray block, consists of alternating layers of multi-head self-attention, or MSA for short, which is this block here, this layer. Layer norm is applied before every block, which is what we've got here. Layer norm. There we go. And if we wanted to figure out more about these things, how could we find them out? Well, if we go multi-head self-attention. And then if we wanted to find out about layer norm, well, we've got layer norm, PyTorch layer norm, or layer normalization explained. So we've got layer norm as a PyTorch layer. So maybe that's a hint as to what we could use for this layer here. And then if we look into multi-head self-attention, what do we have? Transformers explained visually, part 3. Oh, that might break it down for us. Multi-head attention explained. We've got a whole bunch of resources here. Oh, PyTorch. Multi-head attention. Oh, we've got another layer here. Beautiful. So maybe that might be what we could use for the MSA layer. All right. Well, should we keep going? What else do we have? We have MLP blocks. All right. MLP blocks. We're up to equation 3 already. MLP. And what else do we have? Oh, we have another layer norm here. All right. So we've got the transformer encoder, which consists of alternating layers of MSA attention, so this one here, and MLP blocks. And in between each of the MSA and MLP blocks is a layer norm. So what we're going to refer to these little sections here from now on is equation 2 can be the MSA block, because it consists of these 2 layers here. And equation 3 can be referred to as the MLP block. So if we keep going, what else do we have? We add residual connections after every block. Oh, is that what these plus symbols are? Residual connections. And we got over here. So you'll notice that the residual connection here, what's residual mean? Well, another word for it is a skip connection. So if we take the embedded patches and put it as an input here to our MSA block, but we also have an arrow that goes up here that adds it. So what this residual connection is going to do, and if we look at the mathematical terms, we have Z of layer minus 1 as the input to the MSA and LN blocks, or layers, plus, so the output of this, MSA LN, the output here, plus its input. So that's a residual connection, and the same thing is going to happen up here. So we get the output of the norm and MLP block gets added to what the input was. So if we look over here, if we go back to Google, what is a residual connection? Residual connection explained. Beautiful. So we've got x as an input, and then we pass it down here, and we add it. All right. So residual connections are a type of skip connection. Yeah, that's another word for it. That learn residual functions with reference to the layer inputs instead of learning unreferenced functions. The intuition is that it is easier to optimize the residual mapping than to optimize the original, unreferenced mapping. To the extreme, if an identity mapping, so this is the identity is another word for the same, identity mapping were optimal, it would be easier to push the residual to 0 than to fit an identity mapping by a stack of nonlinear layers. So even that's a little bit confusing to me. So if I wanted to find out more, what could I do? What is a residual connection? What are residual connections in RNNs? A whole bunch of different things here. But the way I understand it, if we go back to the keynote, is that when you're dealing with lots of layers here, and you can imagine that the patterns where our layers are going to be creating behind the scenes are going to be lots of numbers. If those numbers get too small, well, then they become numerically unstable, right? So what adding the input to the output does here is prevent things from getting too small so that our loss or gradients don't explode. So we retain the input and add it to the output. That's how I understand it. You might find a different definition somewhere else, and in fact, that can be your extra curriculum, is to look up a little bit more about residual connections. So let's now turn both of these into pseudocode. So we've got an MSA block, a multi-head self-attention block, with a residual connection, and we have an MLP block with a residual connection. And if we come back here to the paper, and we know we can probably do multi-head attention in PyTorch with that, and layer norm with that layer. And if we wanted to search for more, so where are we up to? The transformer encoder consists of alternating layers of multi-head self-attention, MSA. So Appendix A defines what MSA is. So if we go Appendix A, a lot of information here, but we can do it. So standard QKV self-attention, so that's query key value, which was described in this original paper, is a popular building block for neural architectures. So for each element in an input sequence, Z is an element of a real number of dimension n, number of patches, times D, so embedding dimension from table 1, which we will see later on. We compute a weighted sum over the values V in the sequence. The attention weights A for ij are based on the pairwise similarity between two elements of the sequence and their respective query, Qi, and key, Kj, representations. So if you want to learn more about that, I encourage you to read more on multi-head self-attention there. Or there's another great blog post, J. Alamar Attention, which is linked in the extra curriculum, the illustrated transformer, which is great to learn more. Extra curriculum is, of course, in here. Or all the links you need, actually. They might not be exactly in extra curriculum, but everything that I mention here will be available in the online readable book version of what we're going through, such as the equation 2 overview, equation 3 overview, equation 4 overview. But we're not just reading this verbatim, we're talking out loud here. We're having a discussion of what's going on. So let's go back. We've done enough jumping around. Let's turn equation 2 and 3 into pseudocode. So Python in pseudocode, we have equation 2. So what's equation 2 going to be? The output, so x output of the MSA block, because that's what we've called equation 2. Equation 2 is the MSA block here, so a norm layer followed by a multi-head attention layer followed by a residual connection. So the MSA block, I'm just going to turn this into code, is equal to an MSA layer, so multi-head self-attention, wrapping a layer norm layer, which takes X input plus X input. So that's the residual connection on the end. So if we see here, X input is going to go into equation 2. And if we come back up here, what's X input? X input is this, and this is equation 2. Now let's replicate equation 3. So we're going to go equation 3. We're going to make this X output. We're going to see this in PyTorch code later on. I know I've been promising that for a few videos now, but we're just getting a high level overview of what's going on, because once we've done this high level overview, it'll just be about putting the pieces of the puzzle together. So now equation 3 is going to take X output of the MSA block as its input, and then it's going to add X output MSA block. So that's going to be the input to equation 3. The residual connection is adding it there. So if we jump back up here, our pseudocode is norm layer as an input, the output of the MSA block, into the norm layer, into the MLP layer, and then we add the input again. It's going to take a little bit of practice to fully understand what's going on here, but we'll see this with PyTorch code in subsequent videos. So now we've got equation 1 in pseudocode, equation 2 in pseudocode, and I might just command M minus here in Google Colab to turn these into different blocks so we can separate things a little bit more. Beautiful. So there's equation 2 in pseudocode. So MSA layer ln plus this, the X input, takes as X input in between those layers, then residual connection on the end. Same thing for equation 3, except instead of MSA, it's MLP, and instead of taking this as the input, it's going to take the output of the MSA. So step back through what we've got going on there. We've got equation 2 and 3. We're left with one more equation. And in fact, I'll give you the challenge to see if you can figure out what's going on in equation 4. We'll do that together in the next video. I'll see you there. Welcome back. So we've slowly been turning figure 1 and the equations from section 3.1 of the VIT paper into this colorful mess. But it's all organized chaos, and what we're really trying to do is just get our heads around what's going on. Because when you first read a paper, there's a lot happening, but what's our overall goal is we're trying to turn figures or images, math, and text into usable code. So it helps to understand what the connections are between all of this. And so far we've broken down equations 1, 2, and 3. Now we're up to equation 4. And you can see it takes ln, so layer norm, ln. Did you try to figure out what's going on? Now we haven't got the text here, but section 3.1 breaks it down a little bit more. But let's draw a line. We've got the MLP head, and then we've got layer norm. Now, do you recall what MLP stands for? So if we come back here, we'll just set another reminder, come back to equation 4, and just write ourselves a note. MLP equals multi-layer perceptron. And that equals a neural network with X number of layers. So it could have 10 layers, it could have 2 layers. And if you wanted to find out about MLP, what is a MLP? Master Limited Partnership. Oh, we're not going to get that, are we? Do we get? Nope. In machine learning. That's what we want. A multi-layer perceptron is a feed-forward artificial neural network that generates a set of outputs from a set of inputs. Yes, that's what we want to do. We want to map inputs to outputs. So let's come back. What do we got here? Let's read the text. Equation 4, similar to BERT's class token. So this is where reading papers kind of, I'm going to jump back around here, but this is on purpose because I'm trying to demonstrate what it's like to read an actual paper rather than just talk about it. So similar to BERT's class token. Now, what is BERT? So what is BERT in machine learning? BERT is a type of transformer architecture. There we go. BERT is an open source machine learning framework for natural language processing. So the original transformer architecture was for natural language processing, so processing text. But the vision transformer, recall, turned the transformer, which was originally for one-dimensional sequences of text, and made it possible to use for vision problems, which deal with 2D images. So when the authors reference BERT, they're kind of representing one of the major types of transformer architectures, but originally for text. So the class token is at the start of equation 1, and that's to represent the class that is present. So the class that whatever sample we're trying to classify belongs to. So for the class token, we append a learnable embedding to the sequence of embedded patches. So that's the class token here. So if we go back and continue reading about equation 4, we append a learnable embedding to the sequence of embedded patches. So Z0, 0 equals X class, whose state at the output of the transformer encoder, Z0L, serves as the image representation Y, equation 4. So that's describing equation 4. So if we come back here, equation 4, Z0L, so the 0th token of this output is what we're going to pass to our final layer norm. Well, let's keep reading. Both during pre-training and fine-tuning, a classification head is attached to Z0 of the last layer, L. That's the capital L there, the last layer. The classification head is implemented by an MLP with one hidden layer at pre-training time and by a single layer at fine-tuning time. So if we just want to do training time, we want to go MLP equals one hidden layer at training time or pre-training time, and MLP equals single linear layer at fine-tuning time. So a couple of different interpretations that you can take from that, but let's write it out in pseudocode. So if we look at equation 4, y equals ln of an MLP. Now this is where it also gets a little bit confusing to me. So if we come back to the keynote, it says MLP, but equation 4 doesn't have MLP there. So that confused me a little bit, but I'm pretty sure they mean that this ln is within an MLP. And in fact, if you find that this is different, you can correct me, but I'm going to interpret this ln as being within this MLP head. So let's come back here. In pseudocode, in Python, we want y output because that's going to be the final output. We want y. I'm getting y from here. Y, and this is going to be equation 4, will be an ln layer. So we want a linear layer, so a single hidden layer, wrapping ln layer of X output MLP block. Do you see where that's coming from? X output, so the output of equation 3 is going to feed in to equation 4. There we go there. So that's the linear layer. So an MLP with one hidden layer. We could really do it like this. MLP. MLP, or in our case, we'll just do a linear on the outside. Linear layer. And we can, of course, customize that to suit our needs. But we have now turned equation 1, 2, 3, and 4 into pseudocode. So what we can now do is start to map this pseudocode to PyTorch code. And so that's what we're going to start doing over subsequent videos, is instead of having this all in pseudocode in the form of math, figures, and text, we want to turn all of this into usable PyTorch layers. So we're going to start working towards doing that. In fact, that's what we've been working towards doing the whole time. But in the next video, I'm just going to break down table 1, and then we'll have all of the pieces of the puzzle ready to start replicating the VIT architecture. If you'd like to jump ahead, you can try to break this table down yourself with reference to the paper. In fact, I'd definitely encourage you to do so. You can find it here, table 1. And then, of course, table 1, you can search for different breakdowns. Yeah, model variants. That's what you'll want to read. So give that a shot, and I'll see you in the next video. Welcome back. So over the last few videos, we've been slowly breaking down the overall Vision Transformer paper into smaller pieces of the puzzle. We started with figure 1 and broke it down into inputs, outputs, layers, and blocks. Then we looked at the 4 equations, which describe what happens behind each of the layers or each of the blocks. Now we're up to table 1, which describes the different hyperparameters of each model variant of the Vision Transformer. And you might have already read ahead about what's going on here. Table 1, details of the Vision Transformer model variants. So we've got a little section here We'll have a look at that in a second, but let's just jump back to the keynote and just reflect what's happening with the four equations. So we start by splitting an image into fixed size patches and then turn each patch of the image into a learnable embedding. Now that's going to be the representation of our input. So if we come over to equation 1, that's what describes the patch and position embedding. So we have x1 patch embed, x2 patch embed, which is this one, and then all the way up to n, which is number of patches. Then, just like the BERT architecture, we use the standard, or the authors use the standard approach of, it's going to be us in a second, standard approach of adding an extra learnable classification token, so X class, to the front of the patch embeddings. Then we create a position embedding. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, because we have 9 patches here. And of course, 0 is for the class token. And so the position embeddings are to retain positional information. Then if we keep going, we have alternating layers of multi-head self-attention within the transformer encoder block. And this is going to be referred to as our MSA block. So MSA layer norm takes the embedded patches as the input. And because there's multiple blocks of this transformer encoder, we've got the nomenclature here of ZL-1 for layer -1, all the way up to the final layer, which is the capital L. So this is equation 2 here. Then we move on to the MLP block, which is MLP wrapping a layer norm, takes the output here as the input, and the residual connections we're adding the inputs to the MSA block to its outputs, as well as the input of the MLP block to its output. So a fair bit going on here, but we've broken these down step by step now, and we're going to start to work towards turning this all into usable PyTorch code. So now let's move back to table 1. So if we have a look at what's going on in table 1, you can see we have different model names here, such as VIT base, VIT large, VIT huge, and you'll see that the numbers go up. This is kind of a trend that you'll see with a lot of research papers, is that the authors often release different variants of their model under different scales. So if we look at the number of parameters here, VIT base, the smallest version, has 86 million parameters, but that's still far more parameters than any of the models that we've built so far. And then it goes up as the other numbers go up. So if we add more layers, so this is doubling the number of layers, we get almost triple or over triple the number of parameters. And then it goes up again, and then we have 632 million parameters. So we're edging towards a billion parameter model here with VIT huge. So we base VIT configurations on those used for BERT. So BERT is one of the original transformer architectures used for text. As summarized in table 1, the base and large models are directly adopted from BERT, and we add the larger huge model. In what follows, we use brief notation to indicate the model size and the input patch size. So this is something to be aware of. The patch size, if we go back to our figure here, the patch size is this. So this is an important note. For instance, VIT L, so VIT large, means, or VIT L16 means the large variant with a patch size of 16 by 16 input. So that's the patch size that we're going to use. So when we split our images into patches, they're going to be 16 by 16. So that's the input patch size. Note that the transformer's sequence length is inversely proportional to the square of the patch size. Thus, models with smaller patch size are computationally more expensive. Now, where does this come from? Inversely proportional to the square of the patch size. Now, if we come back up to here into section 3.1, that's because the number of patches is patch squared. So height times width divided by patch squared. So you can imagine if this number gets smaller, the number of patches is going to be more because height times width is going to be divided by a smaller number. So the higher P goes, the smaller number of patches there is. So if we jump back down into here, table 1, let's break this down, hey? We're going to start by replicating VIT base, the smallest version, because that's what I like to do as well when I'm replicating things. Start with the smallest version, get it working, and then design it in a way that we can upscale these hyperparameters if we needed to. So you'll see later on when we create our vit class, we'll put in parameters so we can change the number of layers, the hidden size, MLP size, and number of heads as we wish. Let's just see if we can break this down. So vit base, vit large, and vit huge are all different sizes of the same model architecture. So with different hyperparameters. And then we have layers. So layers is going to be the number of transformer and coder layers. So this is where that capital L comes from for layers. Well, not necessarily, they may be unrelated. I just pretend that they are. And LX. So if we have L equals 12, or number of layers equals 12, that means we're going to have 12 transformer encoder blocks. And then if we come down here, that's in the case of vit base. And if we have layers equals 24, we'll have 24 transformer encoder blocks. And then subsequently, the same thing for vit huge with 32. So we have hidden size D, and this is where you can use LaTeX. So you can use the dollar signs there to surround D to get that cool little italicized D over there. So hidden size D is the embedding size throughout the architecture. So if we have an embedding size of 768, that means we're going to be turning each patch, each image patch, which may be 16 by 16, into a vector of 768. And if it goes higher, well, then it's going to be a higher number vector. So when we embed our patches, if our embedding size D is 768, that means all of the patches are going to be represented by a single vector of size 768. And that vector will be learnable, of course. And then 1024 for vit large, and then 1280 for vit huge. Then we can keep going. So we have MLP size. Where is this going to go? This is the number of hidden units / neurons in the MLP. Now, where's our MLP? If we come up here, we have an MLP and we have an MLP. So that's what the MLP size stands for. Within this MLP, we may have a hidden layer. And so if the MLP size is 3072, in that case, the number of hidden units in this MLP layer will be 3072. So if we keep going, we've got one more. Heads equals. Heads is the number of multi-head self-attention. So 12 is the case for vit base, which is what we're going to be paying attention to. But again, these will all be hyperparameters that we can set if we want to. So if we come up, multi-head self-attention. So we can set the number of heads within multi-head self-attention to whatever table 1 is telling us. So let's look up multi-head self-attention. Do we have that in PyTorch? PyTorch, multi-head attention. Embed dim, there we go, that's D. This is all going to make sense once I'm glad we've spent some time here breaking this down, because once you see it in code, everything is going to fall into place. Hidden size D, that's our embedding dimension. Embedding dimension, number of heads is here. Oh, excuse me, number of heads. There we go. And then we've got other parameters that you can look into as an extension, but here's where it came from. The paper, attention is all you need. And then once again, if you wanted to find out more, where could you go? Multi-head self-attention explained. A lot of resources there, but if we just look at the first one, Papers with Code is one of my favorite resources. Yeah, that's the head dimension, H. So we split it across a number of heads, so we have H there. And I'll let you read more about that there. So, friends, we have just made it through breaking down all of the major pieces of the puzzle. I mean, we've got table 3, but that's going to be extra curriculum at this stage. I feel like we've done enough. We need to start coding before we all go crazy, because that's what will happen. You'll start to read stuff too many times before writing any code, and it'll get too confusing. So we've got equation 1, 2, 3, and 4. We've got figure 1, the inputs, the outputs, the layers and blocks, and now we've got the hyperparameter settings. So with that being said, let's now start to replicate the Vision Transformer architecture, and we're going to start with turning our image into a patch, or into a patch embedding, or a position embedding as well. So how do we do that? Have a think about it, and we'll start to work towards that in the next video. Welcome back. In the last video, we finished off putting together the pieces of the puzzle with a VIT overview. We've broken down figure 1, we've broken down the 4 equations, and now we've had a look at table 1, which defines the different hyperparameters of different Vision Transformer model variants. And we discussed that we're going to be replicating VIT base because that way we can just start small, experiment quicker, and then if we want to upscale, we can do so. And I just added a little note here that the nomenclature in the paper is VIT-B, which stands for VIT base, so these hyperparameters, and 16 stands for an image patch size of 16 by 16, which is of course detailed here under model variants, and there we go. VIT-L16 means the large variant with 16 by 16 image patch size. So 16 is our patch size. And speaking of which, how about we start moving towards writing some actual code? To begin with, we're going to replicate all of these equations over time, that is. But to begin, we're going to start with equation 1, and that is the patch, position, and class embedding. So have a think for a second. How do you think we might turn our image, a single input image, into a sequence of patches? And then how might we embed them? You may have an idea if you've read through the entire paper, but if you don't, that's perfectly okay. You can almost guess if you wanted to. But I'm not going to reveal the secret yet. Let's instead see an overview of the VIT workflow. Now this is part of the visualize, visualize, visualize motto. Oh, we've skipped ahead. I've got a little animation here to overview what we're going to be replicating with code. So this is Food Vision Mini meets VIT. We cut it into patches. Now we have to embed each of the patches. Oh, we might embed it with there's a little spoiler there. It's a layer that we've used previously. And then if we embed each patch into a series of numbers, represent them as a learnable embedding. We've got 9 patches. There's another PyTorch layer we might have seen before. We flatten it to a sequence. That looks familiar, doesn't it? Then we've got the convolutional... Oh, excuse me. I've spoiled it. We've got embedding tokens. Then we've got class embedding. And then position embeddings in purple. We feed that to the transformer encoder layers. We feed the output of the transformer encoder layers to the MLP output. And then hopefully we get our class. So if we start again, I'm not going to rewatch this. You can watch this on your own time. It's also available in here. If we go, we've got a little overview somewhere. I believe it's in here several times actually. Yeah, there we go. So you can jump ahead and have a look at that. But we're up to equation 1. Split the data into patches and creating the class, position, and patch embedding. So let's jump in here. We'll start equation by equation. Equation 1. And this is going to be split data into patches and creating the class, position, and patch embedding. So what I like to do first is we've discussed previously that layers equals input and then some sort of function and then output. But what's another really important thing of machine learning? And I know that's kind of a general question, but when we have our input, it's some sort of representation, right? And so what's the input shape? We have a tensor, and what's its shape? And then the function does something, and then what's the output shape? So when I'm replicating a new architecture or trying to use an existing one, I always like to check out the input and output shapes of each layer, of the entire model, you name it. Input and output shapes. One of the biggest problems you'll find in machine learning and deep learning is misaligned tensor shapes. So let's begin by finding out the input and the output shape. Now, we kind of actually know what the input shape is. So the input shape will be a single image of 224, 224, 3. But what's the output shape of the patch embedding layer? This is equation 1, by the way. We're focused on equation 1. So this is single image, which is, of course, height, width, color channels. Where could we get this information from? Well, if we go back up to section 3.1, it's described here. So let's copy this down, equation 1. I know we're doubling up here, but I'm trying to explain, as we've discussed before, some non-linear information in a linear fashion. So let's just take a little second here to read through this again, because this is going to give us our input and output shapes of equation 1. Once we have our input and output shapes, we can start to work backwards from there. So to handle 2D images, which is our input, in our case, we're going to start with inputting a single image, such as this image of pizza. You see what we're doing here? We're breaking things down into as small a piece as possible, a single input image and a single layer at a time. So we have X input is an element of a real number, height times width times color channels, 224, 224, 3, or in PyTorch it might be 3 first for color channels first by default. You can set it up so that it's this way though. Into a sequence of flattened 2D patches where X patch is an element of a real number of shape n times p squared dot c, where c is the color channel, and h and w. Let's write this down, hey, while we're at it. So let's go. Input image is h. I'm going to use, or maybe can I do this in dollar signs? I'm not very good at writing. I don't think this will come out nicely, will it? Maybe we can go times. This is experimenting on the fly here. Hey, there we go. So the input image is height, width, color channels. So I'm just going to put this down here. Height times width times color channels. And where am I getting this from? Well, it's from right here. Now let's get the output image, or the output sequence of patches is of this shape. So we need to figure out what output image is $n, and then I'm going to go times, and then I'm going to go p. Oh no, I'm not quite sure how to get squared here. Maybe we'll just copy this, hey? Math B, we want this one. Beautiful. Might just get that there. And I can get rid of this R at the start. So we're just breaking this down step by step. And now let's go H equals height. I'm just going to start type. I'm not going to bother with the fancy text here because I'm much faster at just doing it like this. Color channels. Now N, what is N equal to? Let's find out what N is equal to, because we've got N here. N is equal to height times width divided by p squared, where p is the resolution of each image patch. So we actually know what p is now. We've said we're going to use a patch size of 16. So p equals patch size, and n equals height times, we'll write here, equals number of patches, equals height times width. We'll put that in brackets, hey? Height times width, and then we'll divide that by p and then squared. And then do we have anything else here? Uses constant latent vector size d. D equals constant latent vector size, which is also equal to embedding dimension. See table 1. Now that's just what we went through before in the previous video. So we've got all of the pieces of the puzzle here for the input and output shapes here. I just want to emphasize, yeah, there's the hidden size D. That's where D comes from there. So we don't actually want input image. It's going to be, we know it's an image, we just want the shape. So let's calculate it by hand. How do we start to do that? Well, how about we create some example values? Example values. So our input shape is height, width, color channels, and we know that the input shape is 224 of the image shape, and we're using colored images, so it's going to be 3 color channels, right? So height equals 224, width equals 224, color channels equals 3, patch size equals what? We've said that this is going to be 16. We got that from the model variance section. VitL16 means large variant with 16 by 16 input size. And I believe if we go to, yeah, here we go. We've got some good results here from 16, 16. And then if we looked at the further results, if you read through the rest of the paper, VitB16 performs pretty well across ImageNet. So it gets about 77 or 76% on ImageNet, so 1,000 classes, so that's pretty darn good. So this is what we're replicating. VitB, VitBase with a patch size of 16. And we're trying to work out the input and output shapes of the first equation, breaking it down step by step. So we've got the height, the width, the color channels, the patch size. Now let's calculate by hand the number of patches. Calculate the number of patches. So number of patches, which is going to be n. We can use the formula here. We'll turn it into an int. We'll go height times width, because it needs to be a round number, that is. That's why we're turning it in an integer. And I'm going to divide it by the patch size squared. And so that is here. N equals height width divided by patch size squared. So we've just replicated that. Have I got one too many brackets there? Let's check out the number of patches. 196. Beautiful. So that is going to be our n dimension there. So how can we work out p squared times c? Well, we can do that as well. Let's go, let's create an example input size. So input shape equals, we'll create the input shape, and we'll go embedding layer input shape equals, what's this going to equal? So this is the input into our first embedded layer. So if we go back, we'll find figure 1. There we go. So we want the input shape of our image into our embedding layer. Oh, we've already got this, haven't we? Let's go back here. Is going to be height, width, color channels. Now, what's the output shape going to be? Well, we want embedding layer output shape is going to be equal to, we want number of patches times p squared dot color channels, or times color channels. So let's calculate this by hand. We'll go in here, number of patches, and then we'll go patch size squared times color channels. Let's see where this gets us, hey? Now, you notice we've only got 1 comma here, so this is just going to calculate this there. So let's print it out, and we'll go input shape. So this is going to be a single 2D image, and then we'll go embedding layer input shape, and then let's go print, and then we'll go output shape. This is of the embedding layer. Single 1D sequence of patches. So embedding layer output shape. Let's go. Beautiful, look at that. Now, where does this value come from? So we know this one, that's going to be our image size. And then we have number of patches. But this value, what does that remind us of? Well, that's from table 1. Hidden size D. Now you notice we didn't actually hard code that. That was inferred by the patch size squared times the number of color channels. So there's our embedding dimension. So the input shape of our first patch embedding layer is going to be a single image. And then to make sure that everything's correct, we've just calculated by hand what the output shape should be. A single 1D sequence of patches. Now, how do you think we get from this shape to this shape? So have a think about that. I revealed it in the little animation that we went through. So maybe you rewatch that, or if you want to skip ahead, there's some spoilers in the book here. But we're going to start moving towards creating this input and output shape with PyTorch layers. So with that being said, I'll see you in the next video. Welcome back. In the last video, we started off by reproducing the information for equation 1, and we knew what the input shape was, but we didn't know what the output shape was supposed to be of equation 1. And one of the best ways to break down an individual layer in deep learning and neural networks, or even a whole model that is to figure out the input and output shapes. And so in section 4.1, which is what we just did, we calculated input and output shapes by hand using the information available to us here. And so what we're doing is we're still just breaking it down piece by piece, figuring it out and calculating things to make sure that when we recreate it with PyTorch layers, we've got things in the right shape. So let's turn a single image, we'll break it down even further into patches. Because what we're doing is, just to reiterate, as we'll go back to figure 1, we're starting with this. We want to create the patch and position embedding. How do we split a single image into patches? We know what shape it should be, but do you have any idea how we could get our image into patches? Well, how about we follow the Data Explorer's motto of visualize, visualize, visualize. Let's visualize, visualize, visualize. And you know what's our other motto? If in doubt, code it out. So let's view a single image here. And we'll go plt.imshow. We should have one stored in memory. Image.permute. And I'm just going to make it compatible with matplotlib. plt.title. We'll go class names. And we'll pass in the label. And then we'll go plt.axis. And we'll turn off the axes. Stake. Wonderful. So how do we turn this image into patches? And if we have a look at our image right now, it's a tensor of shape, which is our input shape. So we need to convert this shape here, this tensor shape, which is what we've got here. Now, the color channels is a little bit flexible here. We can rearrange that if we want, but we've got the same dimensions here. We need it to be converted into these dimensions, which of course is N, which is number of patches, and D, which is embedding size. I might just put a note here. So number of patches. So number of image patches that we turn our single image into. And then we've got embedding size or embedding dimension. And the embedding dimension comes from table 1. But in our case, this was calculated by doing patch size squared times color channels, which was this little formula here, output shape. So let's keep going now. How about we start by trying to patchify this one image, turn this into patches. But before we turn the whole image into patches, why don't we turn a portion of it into a patch? I'll show you what I mean. So let's get the top row. Get the top row of the image. How might we plot the top row? So we've got some dimensions here, 3, 2, 2, 4, 2, 2, 4. But why don't we start off by permuting the image so it's compatible with matplotlib. You know matplotlib likes the order to be color channels on the end. Convert image to color channels last. So HWC. Now let's go index to plot the top row of pixels. So we want, let's set a patch size to 16 because that's the patch size we've discussed that we want to use. If we go back to here under model variance, there we go, 16, input size 16 by 16. So we'll just set the patch size to a variable here, 16. And now what if we indexed on our image to go fig size equals, well, we'll create a plot here. We'll go patch size by patch size, and then we'll go plot.imShow. Now I'm going to index on the image permuted that we just created, and I'm going to get, for the height dimension, I'm going to get the pixels up to the patch size. We'll see what this looks like in a minute. For the width dimension, I'm going to get all the pixels, and for the color dimension, I'm going to get all the pixels. That's what the colon here does. So this is indexing up to patch size. Now we should see the top row of about 16 pixels for our image. Beautiful. So that's all we've got. We've got these 16 pixels from here to here, and then all the way across, because we've got up to 16, so 0 to 16, and then we've got the entire width dimension, so 0 to 224, and then we've got all the color channel dimensions, so we've got a colored image here. Now, if we go back up to where we visualized a single image, if we get another image here, we should have the same outcome. Pizza, okay, so this is a colorful image. This will look a little bit better. Now, just mind you, if you come back to this at a later date and we've rerun this, you're going to get a different image each time, because it's random, the order of this train data loader. So don't worry too much if our images aren't exactly the same. This is just for demonstration purposes. It should work with any image. So pizza, same image shape because we've pre-processed it in such a way. And then we permute the same image, and then we're going to get the top row here. There's the top row of pixels. We only get that little bit of crust on the end because we're only going from 0 to 16 on the height dimension with this index here. Now, what if we wanted to patchify just this section? So if we wanted to turn this into patches, much like we have in figure 1, I know I'm jumping back and forth here, but it's one of the best ways to illustrate things. So we've got this top row. How do we turn that into a sequence of patches? Well, one way to do so would be to iterate through all of these pixels, and then every patch size, make a cut here. So how about we try to replicate that with matplotlib, hey? So set up code to plot top row as patches. We're trying to build some intuition here over how an image is processed in the patch embedding layer. And the patch embedding is arguably like one of the most important sections, because I had a friend, this is a little anecdote, who's a machine learning engineer, who said it's all about the embedding. Meaning, if you can represent your data in a good learnable representation, in other words, an embedding, well then the model architecture is probably going to be able to learn something. So it's all about the embedding. So let's keep going here. Num patches we can calculate to be image size divided by patch size. Does that work? Num patches, 14. Okay, that makes sense. So there's going to be 14 patches across here. So let's go assert. We just want to make sure that the image size here is divisible by the patch size. Now the reason I'm coding them like this is so that you can try it out, or we can try it out later with different image sizes and different patch sizes. For now, we're just going to stick to 224 and 16. So let's write here, image size must be divisible by patch size, because if we had a patch size that didn't divide into 224, well, we wouldn't get even patches, would we? So I'm just going to put this little assertion here, and then let's keep going. So let's create a series of subplots. Now I'm going to do that because I want to iterate through all of the pixels here, and I want to cut them into patches and plot them individually. So what I mean by subplots is I'm going to go fig axes equals plt.subplots, which is going to help us create multiple plots. Then I can set number of rows equal to 1, number of columns equal to, it's going to be the image size, which is 224, or in other words, this dimension here, 0 to 224. So image size, columns I want divided by patch size. So I want 1 column per patch. So 1 column for each patch. And what I might do here is just print out a little bit of information. You know how much I love printing out information. So number of patches per row is going to be num patches. And then I'll go here. Patch size is going to be patch size times, or patch size pixels to be more exact, times patch size pixels. Beautiful. And let's go on the next one. There's a little parameter here called share X and share Y. That just means, do I want them to share the X and Y axis values? Well, if you want to research what that is, you could go matplotlib subplots. This is where we're getting this code from. Share X and share Y, control sharing of properties among X or Y, and then true or false, and there's more information there. So let's just see what this looks like, hey? You know the saying, if in doubt, run the code. So this is going to create the subplots. Now we need to put something on those subplots. So we want to iterate through the pixels here, and every patch size, so 16, 16, 16, 16, we want to cut it and plot it to its own plot. Let's see what that looks like. So iterate through a number of patches in the top row. For I patch in enumerate. So we're only doing the top row here, but the principle of what we're doing can be expanded later on. In fact, I'll set that as a challenge to you. Expanded for the whole image. The top row and every other row. So right now we're going through enumerate, range 0 to image size, so 0 to 224, and we have a step of patch size. So let's just print out this. Print out patch, just so you can see what it looks like. There we go. So there's our plot, nothing on it. So we have number of patches per row, 14. Patch size is 16 by 16 pixels. And our iterator here is going from 0 to 16. This is exactly what we want. 0 to 16, patch. 16 to 32, patch. 32 to 48, patch. Oh, is that right? Oh yeah, 32 to 48. Excuse me, yeah, I can't do math. Trust the code, Daniel. So axes I. So this is that enumerate I, and axes here, I. And because we've got 16, or we've got image size divided by patch size columns. So we've got 1, 2, 3, 4, 5, up to 14 columns. So on I column, we want to im show image permuted, and let's go up to patch size, just like we've done to plot the top row. But now we want to go from patch to patch plus patch size on the width dimension, and then we want all of the color channels. So a fair bit going on there, but if we step back through, so im show image permuted, on the height dimension we want up to patch size, so 0 to 16, and then we want to start at patch. So for the first one it'll be 0. So 0 to patch 0 plus 16. So 0 to 16, we want 0 to 16. Then for the next one, it will be patch will equal 16 plus, or 2 patch plus patch size. So 16 to 32, 16 to 32, 32 to 48, 48 to 64, etc., etc. And then we want all of the color channels. So let's now just set a few parameters here so we get a nice and clean plot. X labels, or X label I plus 1. So this will be set the patch label. This will make a lot more sense once we plot it out. It does take a little bit of practice to be able to create plots like this. Matplotlib is a fun challenge to work with. So and then finally we're going to go set Y ticks. Do we have the top row plotted? Oh yes we do, look at that. But it's quite small. Let's see if we can make this plot bigger, hey? where do we create the fig size? Maybe here? Fig size equals patch size, patch size. Is that going to tell me that it's an error? Oh, we need a comma here. There we go. Beautiful. So we have now turned the top row of our image into individualized patches. Now it's another step to turn these patches into embeddings, but we're one step closer to preparing our input image. So my challenge to you is to expand what we've done here, turning a single row into patches across the whole image. So what you might have to think about doing is looping through both dimensions. So you might need 2 loops here. So right now we're looping through the width dimension here with this one here. You might need to do the same, but also looping through the height dimension. So a little bit of a challenge, but nothing you can't handle. Give it a shot. And in the next video, we'll turn the whole image we've got here into patches. I'll see you there. Welcome back. Now in the last video, we turned a small section of our image, namely the top row, into patches. And I issued you the challenge of trying to patchify the whole image, because that's the first step in the patch and position embedding, is turning our input image, a single input image, into patches. And then we got to flatten those patches and then turn them into some kind of embedding. We'll do that flattening and embedding projection later on. But now let's focus on how do we visualize this image of pizza. And now your image might be different because the data loader is random. So way back up here, just keep that in mind. The image doesn't really matter. Just, it should work with any image. So this may be an image of steak or sushi. Let's keep going. The code should still work. So what we're going to have to do is this one we iterated through the width dimension. And I gave the hint that we're going to have to iterate through both the width and now the height dimension. But the overall code here is going to be quite similar. So let's go here. We'll set up code to plot whole image as patches. So we'll redo the image size equals 224, or in fact, what we might do is just copy this down to here. So image size equals 224, patch size equals 16, number of patches equals image size divided by patch size. And we will go here, assert image size. We want it to be divided by patch size and then equal to 0. And then image size must be divisible by patch size, otherwise we'll get uneven patches. And let's print out some information here so we know a little bit about what's going on. Number of patches per row. So num patches, and then we'll go to a new line, we'll tab in, print out here, and then we'll go number of patches per column, which will be num patches as well. So we're doing the whole image now. Then we'll get another line and we'll go total patches, which will be equal to num patches times num patches. Num patches sound like a rapper name. Num patches, patch size. Once we've built a vision transformer, we'll be able to call ourselves num patches times patch size pixels. So a whole bunch of information here about what's happening, but let's just see what it does. So we should have number of patches per row, 14, number of patches per column, 14, and total patches is 196. Where does that number come from? If we come back up here, we've already calculated that, number of patches. So we need to figure out later on how to turn each one of these patches into an embedding of size 768. Well, let's not get ahead of ourselves. We're trying to visualize one single image here. And then each individual patch is 16 by 16 pixels. So you're ready? Let's now create a series of plots, a series of subplots that is, to plot each one of our image patches. Fig axes equals plt.subplots And this time we're going to have a number of rows, which will be equal to image size divided by patch size. And we're going to have a number of columns, which was going to be equal to the same thing, image size divided by num patches, or patch size, sorry. Then what do we need? Well, we need a fig size, and let's just turn this fig size to num patches and num patches. And then we'll go share x equals true. So we share the x axis information and we'll share the y as well. So that is, we want to share these labels here. Share x, share y. So let's keep going. We've got a subplot there. What happens if we print this out? It might take a little while here because we're trying to visualize 196 patches or 196 plots. You'll see down here, we've got executing time. Unless there's an error. There we go. Okay, so that took a little while, it took about 40 seconds, but that's because we're working on Colab here and it's got about 2 CPUs. I believe Matplotlib, if you're plotting lots of plots, can be quite CPU intensive, but the good thing is that we've got them set up. And this is just for visualization purposes. This is not going to be the same code that flows through our model. So loop through the height and width of the image. So for I, we will start with the patch height. In enumerate, we want to go through a range of 0 to image size using a step size of patch size. So this is going to be iterate through height. So this is our height dimension here. We want to break our image, our single image, into patches. So we want to go through the height and then through the width and create patches of size, patch size. So now let's go for I patch width in enumerate. You may already have code similar to this because that was the challenge for the last video. But if not, that's fine. That's why we're doing it together. Now let's plot the permuted image on the different axes. So what we actually might need to do is, because we've got I above, we need to change this one to J. So we need this one to be separate so we can separate patch height and patch width. And because we've got 196 axes, so 1, 2, 3, 14 by 14 is 196, we can index on each one of those axes by going axis I, J. So this is going to, for the first one, it's going to be 0, 0. And then for the next one, 0, 1. And for the next one, oh sorry, this way. 0, 1, 0, 2, 0, 3, 0, 4, etc. 1, 0, 1, 1, 1, 2, 1, 3, and so on. So let's now go ax ij im show, and we want to go image permuted. Now here's where the trick comes for indexing. So the first dimension is patch height, and we want to go patch height to patch height plus patch size. So this is going to iterate through the height dimension. Then on the next one, we want to go on the width dimension. We want to go patch width to patch width plus patch size. And then finally, we want to get all of the color channels. So iterate through width and then get all color channels. So a little bit going on there, but nothing we haven't done before. All we're doing is we're expanding this to loop through not only the width, but the height as well. So now we've got the height axis in there, or height dimension of our image tensor. So now we can set up a little bit of information. So set up label information for each subplot. Now each subplot, of course, is also known as a patch. So we'll go axis ij, get the current axis, and we'll set the y label. We want the y label to be I plus 1. And then this is a little bit of formatting here. Because this is a machine learning cooking show, I've actually cooked up this plot earlier. So I'm just going to make the y labels look pretty. We can do this without it, but they don't look as good. Horizontal Now, alignment, that's probably definitely a spelling error, but we want this one to be vertical alignment. We might get some spelling mistakes wrong here, but if we do, that's all right. So now we go axes IJ to clean up some things. We want to go set X label. We'll go J plus 1. So we've got I and J. So the Y label is the I, X label is the J. Then we'll go axes IJ dot set X ticks. Otherwise, we'll get all of these little ticks here. Just removing those. And then axes IJ. Set Y ticks. We'll do the same for the Y ticks. And then finally, we'll go axes IJ and make sure the labels are on the outside, label outer. To figure all this out, by the way, took a fair bit of exploring through the matplotlib documentation. So don't think this just comes naturally to me. I definitely had to do my research. And then we'll set up a title for the plot. So fig, there's an attribute called, or a method called super title, which is going to go above the whole plot. So we'll go class names, we'll index on the label. So whatever image label that we're working with will appear up the top. And if we've written the code correctly, it will be patchified. So just remember, your image may be different to mine because the data loader is random. And then we'll go plot.show and see if we have no errors. Fingers crossed. So this, again, may take a while because we have to create 196 individual plots. And that's going to be a little bit CPU intensive for our Colab workspace. So I'm just going to fast forward this until it works for me. Boom. There we go. Pizza patchified. So look at all those little image patches. We turned our image into a patch of smaller images. I don't really know how to describe that. But you can see here we've got 1 to 14 rows and 14 columns, which equals 14 times 14, which equals 196. Now, if we go back up here, how many patches do we have per image? 196. So we've just figured out how to turn our image into patches, but our code is quite verbose. And if we had to wait that long for every single image, like going through a neural network, if we're working with thousands of images, well, then our network's going to be untrainable because it's going to take too long per image. So you might want to think, how could we turn each one of these patches into an embedding? Because that's our next step, right? We've got the number of patches dimension. If we're working towards going from a single input image, the input shape of 224, 2243, to an output shape of a single 1D sequence of patches, we've got 196. So we've got 196 patches, but we need to embed them into 768. How do we do that? What layer have we used in the past that slides over an image like a window? I'll give you a hint. We covered it back in PyTorch computer vision. And if you want to jump ahead, you can check out this animation. It'll give you a little hint. Oops. There we go. Spoiler alert. We're going to cover that in the next video. But if you want to jump ahead and try it out yourself, I encourage you to give it a go. I'll see you there. Welcome back. In the last video, we turned a single image into patches. And you'll notice that I've got a different image here to the last video. It's now of sushi, but that's because I took a little break and just reran all of my cells again. So if we do that, it's going to load with a different image here just to verify that the code still works. So while that's running, let's start to create a heading. We're up to section 4.3, and that is creating image patches and turning them into patch embeddings. Now, you might have already jumped ahead because I've revealed a few hints over how we're going to turn our images into patches using PyTorch layers, and then of course turn them into patch embeddings. So there we go, we've got another image here, steak turned into patch. So we see the overall premise of what it's like to turn an image into patches, but now we need to flatten our image into a sequence, but we also need to turn it into embeddings. So we can do both of those steps with inbuilt PyTorch layers. And the hint that I gave you, oh, there it is. I guess this is a gift. It's going to keep playing. .gif, that is, not gift. Well, it is kind of a gift because it's a beautiful animation. But let's just hide this for a second. Back in PyTorch Computer Vision, we had a look at the CNN Explainer website. So let's jump back into that. So if we need to create patches, if we need to turn each one of these into an embedding, what does that kind of operation look like? Because we looped through the image's height dimension as well as its width dimension. If we go back to the CNN Explainer and go back down to a convolutional layer, we've got different hyperparameters here. So if we play this, what's happening? Let's change the input size to be 7 by 7. And we'll set the kernel size to be, 2 by 2 is good enough. And a stride of 2 as well. Now let's play and see what happens. Oh, can this not work? Maybe we make this 1. You see the red tiles, how they're sliding across the image? Is that something similar to what we want to do? We want to slide across our image and create patches. Perhaps this could be considered, this input 7 by 7 could be considered our input image. And then over here, these could be considered our patches. So how would we recreate this with a convolutional operation? So if we go back here, if we wanted to make a 16 by 16 patch, and we wanted to use torch nn conv2d, what could we set the hyperparameters to? So we've got in channels, out channels, kernel size, and stride. Well, let's go back to the keynote. Do we have that animation here? Yes, we do. So this is what we want to do, right? We've seen, oh, excuse me, little spoiler alert as well. Let's play this animation. So we want to cut it into patches. We've seen how to do that with matplotlib. But now how do we turn these into embeddings? Well, we could use a conv2d layer and set the kernel size to the patch size. So we've got a window here, and then stride to the patch size as well, so it slides over. And then we turn each of the patches into convolutional feature maps, or in other words, embeddings. And then if we wanted to flatten to a sequence, well, we could use the torch.nn.flatten layer. So now we've got convolutional feature maps act as our patch embeddings. And then we've got other embeddings to add, but we'll get to those in a second. So let's jump back to Colab, right down here. So perhaps we could create the image patches and image patch embeddings in a single step using torch.nn.conv2d and setting the kernel size and stride to patch size and stride values or parameters to patch size. Because if we go back to the CNN Explainer, that will give us, if we set this kernel, this red square here, to 16 by 16, that'll be the kernel size, and then set the stride to 16, well then we'll get a patch, a patch, a patch, a patch, and so on. Of course, this image is not to scale, but if we get out of these two and go back to here, this image is to scale, so we get kernel size, 16 by 16, and then the stride, if that equals 16, well then we'll jump to that patch. We'll turn this into a convolutional feature map, then we'll turn this patch into a convolutional feature map, and recall that a convolutional feature map is a learnable representation. In other words, an embedding. So we'll turn this patch into an embedding, this patch into an embedding, this patch into an embedding, and so forth. So let's see that in practice, hey? And you might be wondering, where did the idea of the conv2d come from? Well, there's one more thing that we're going to look at before we start to write the code to do this. And if we go down to the method, section 3, 3.1 is just a treasure trail of different ideas. There's this section here, hybrid architecture. So as an alternative to raw image patches, the input sequence can be formed from feature maps of a CNN. In other words, a convolutional neural network. So in this hybrid model, the patch embedding projection E from equation 1, if we go up to here, this is E, the patch embedding. This is what we're creating. We're replicating this section. We'll get to the class embedding and the position embedding later on, but we're just focusing on the patch embedding. So that's what it's referencing down here, is applied to patches extracted from a CNN feature map. So as a special case, the patches can have a spatial size 1 by 1, which means that the input sequence is obtained by simply flattening the spatial dimensions of the feature map. So that's where the flatten layer will come in. We'll see that in a later video. Of the feature map and projecting to the transformer dimension. The transformer dimension is from table 1. And then the classification input embedding and the position embeddings are added as described above. So what it's saying is that we can create these using a convolutional layer, and then we can add these, the X class embedding and the position embedding later on, which is what we're going to do. So let's, one more time, have a look at this. Visualize, visualize, visualize. Here's what we're doing. We're going to original image. We're going to cut it into patches. To turn each of these patches into an embedding, we're going to apply a convolutional layer. And we can set the kernel size equal to the patch size. So the kernel is going to create, and then the stride to the patch size as well. And then the convolutional layer is going to turn each patch into a learnable feature map, or in other words, a learnable embedding. And then we can flatten to a sequence, and that is going to be our patch input embedding. There we go. Let's start to write some code, hey? So I'm going to jump into here. And so let's go create com2d layer to turn image into patches of learnable feature maps. And this is embeddings. So patch embeddings. Now, how might we create this? So of course, we can just do it like we've done before. From torch, import nn, and then we're going to set the patch size. So patch size equals 16. And then let's create a com2d layer with hyperparameters from the vit paper. So we'll call this com2d equals nn.com2d. In channels is going to be equal to what? 3 for color images. And then we're going to have out channels, which is going to be equal to what? Well, I'm going to set this to 768. Now, where did I get that from? So this is D size from table 1. So that's the embedding size. So when we run our convolutional layer over our image, it's going to have a kernel of 16 by 16 and a stride of 16, but we wanted to turn this patch into an embedding size of 768. That's where that number comes from. So let's keep going. Oh, table 1, sorry. We can go back up to table 1. 768, hidden size D. And if we wanted to replicate a different size model, we could use another value here if we wanted to. But that's the beauty of creating it like this. We can just set that value just like that. Then we can go kernel size equals patch size. And then we can go stride equals patch size. And then padding, we're going to set to 0. So let's have a look at our com2d layer. Wonderful. So it takes in channels of 3, a color image. Out channels is 768, which is our embedding size. A kernel size of 16 by 16. And a stride size of 16, which is exactly what we want. So let's keep going. We'll visualize a single image. View single image, just to remind ourselves of the image that we're dealing with. Plot im show, image.permute. We'll go 1, 2, 0, and then we'll go just to make sure the dimensions are compatible with matplotlib. We'll set the title to class names label, and then we'll go plot axis false. So I think my current image is of sushi. Oh, it's of steak, excuse me. And then of course, if we reran all of these cells, we'll get a different image here. Now, while that runs, what should we do next? Well, of course, we want to pass our image through the com2d layer. So pass the image through the convolutional layer. So how can we do that? Well, we can go image out of conv equals conv2d image.unsqueeze. We have to add a batch dimension here. Add batch dimension, because that's what our conv2d layer is going to be expecting. So this is now going to be an image of batch size, color channels, height, width. And then we want to go print image out of conv, and we'll get its shape. Beautiful, look at that. So we have a batch size of 1, and then 768, where does that come from? That's our dimension, so our embedding dimension. And then we have 14 by 14. Now, where does that number sound familiar from? 14 by 14. 196. So that is our number of image patches. So how do we get that into this dimension? Well, if we go back to our visualization, let's just rewatch this again. So our original image, we'll cut into patches. What we've just done is cut our image into patches, and we've applied this convolutional layer. So we've set the kernel size equal to the patch size. So we've got a patch, and then the stride is also equal to the patch size, so it jumps to the next patch, and it creates feature maps here, which are learnable representations of each patch. Now, if we wanted to flatten to a sequence, well, we can use the torch.nn.flatten layer. So that might be an extension that you try for the next video. So give that a shot. You can read forward if you like. But now we've got a learnable representation of our image in the correct size that we need. But we just need to flatten these outer two dimensions. So instead of being convolutional feature maps, we have a flattened sequence, which is what it states in here. So as a special case, yeah, here we go, which means that the input sequence is obtained by simply flattening the spatial dimensions of the feature map and projecting to the transformer dimension. So give that a go. We want to flatten these two outer dimensions into one single dimension and get 196. We'll try that in the next video. I'll see you there. Welcome back. So we're now in the process of creating image patches and turning them into patch embeddings. And we figured out that we can use a conv2d layer to take an image. Well, this is a patchified image, but we have an unpatchified image. And we can use a conv2d layer to turn it into patches of size 16 by 16 by setting the kernel size of our conv2d layer to 16 by 16. So we get this square here. And then it goes to the stride, so it steps over to this next patch and does that for every single one. And then it's going to turn each of these into a convolutional feature map of embedding size. We've set it here, out channels, D size from table 1. So now we've got this tensor after we pass a single image through our conv2d layer. Now, I might just explain what's going on in this size so we can just have a little bit more of an understanding. Now we've passed a single image to our conv2d layer. Its shape is, and so I might just turn this into some code. And you might have already jumped ahead to the next stage, and if you have, as in flattening these outer dimensions into a single dimension. And if you have, well done. Otherwise, that's what we're going to work towards in this video. So we want to flatten these two outer dimensions into a single sequence because that's going to be the input to our vision transformer. So if we go up here, this is what we've done. We've done this part so far. We've turned each of these patches into an embedding, but we want to flatten these embeddings into a sequence like this. So let's just define what's going on here. We have, this is the first dimension on the batch size. I might just actually put this as a comment, so it's a different text. And then we have embedding, dim, and then we have feature map height and feature map width. These are all learnable, by the way, because I believe if we go image out of conv, let's have a look at what it looks like. Beautiful. So it's turned our image into a whole big list of numbers. But you see how here it's got grad function. So that means the gradients, I wonder if I call requires grad on here. The gradients of this tensor will be tracked. by PyTorch, and they will be updated behind the scenes by gradient descent when we pass it through our training loop, and the optimizer gets called optimizer.step. These values will update, forming a better representation, hopefully, of our image over time. And that will account for every image in our data set. So to make this a little bit more concrete, how about we view some of the feature maps? Because this is what we're working towards. We want to combine these feature map height and feature map width into a single sequence. A sequence like this, because that's what the transformer is built to work with. A sequence of vectors. So this is the block that we're working towards, hybrid architecture. We've done the first step, formed a CNN feature map. Now we want to, here, the input sequence is obtained simply by flattening the spatial dimensions of the feature map. Well, what is this feature map? It's these 14 by 14 on the end. So let's visualize. Let's go plot random convolutional feature maps. Now, embeddings, I'm calling feature maps embeddings, similar word. So import random. Let's go random. We'll select random indexes of random.sample along our embedding size. So because we're using an embedding size of 7, I might actually do just leave room for 10 at the end. Oh, excuse me. Range 0 to 758, and then k equals 5. So because we've got 768 14 by 14 feature maps, we want to randomly select 5 of these. So we're not visualizing every single one, otherwise it would be too many. So I might just put an E in here. I'm not sure how indexes is spelled. You might correct my spelling there. So print, let's go showing random convolutional feature maps from indexes, and then we'll go random indexes. Wonderful, let's just see if this works. So yeah, we've got 5 random indexes. So now we want to use these random indexes to index on this dimension and visualize these 2 dimensions. So a fair bit going on here, but you know the motto, if in doubt, code it out. Let's go fig axes equal plt.subplots, and I'm going to go n rows equals 1 and n cols equals 5 for 5 columns, 5 random samples. I mean, subplots has been our friend in this section so far, hasn't it? Let's go plot random image feature maps. So we want for I and IDX, which is short for index. In enumerate, we will go random indexes, which is that list of random indexes we just created there. We'll come down here. We'll go image conv feature map equals image out of conv. So our image passed through the conv layer up here. A single image, we passed it to our conv2D layer, which is set up here, conv2D. In channels equals 3 for color images. Out channels equals 768, which is for the D size for table 1 for vit base. We're focusing on vit base to begin with. Kernel size equals patch size. Stride equals patch size. So we'll just come back down here. Now we want to index on here, get everything from the first dimension, because the first dimension is the batch dimension. But here is where we want to go IDX. So because this is going to loop through these IDXs, we only want to select IDX on the embedding dimension. So we don't want to get all of them, we just want to get 5 random ones. And then we want to get everything on the feature map height and everything on the feature map width. Wonderful. So let's go here. Index on the output tensor of the conv2D layer. And now we can plot it. So axes i.imshow, we want to show the image conv feature map that we just created in the line above. And we're going to have to squeeze it to remove the batch dimension. And we're also going to have to detach it and turn it into NumPy so that it plays nice with matplotlib. So I'll just write here, remove batch dimension, that's what squeeze does. Remove batch dimension and remove from grad tracking / switch to NumPy for matplotlib. Now you can try it without those things and you'll probably get an error. In fact, why don't we try that? Command X. Let's see if this works. I might eat my words here. Axis I, and then I'm going to set the X tick labels just for some aesthetics here. It's important to make good looking plots, you know. Y tick labels equals empty list, X ticks empty list, and Y ticks equals empty list. You guessed it. Okay, you ready? Let's see how this looks. We might get an error here. Oh my goodness, we've got 5 plots. There we go. Can't call numpy on tensor that requires grad. There we go. So this is where that error was coming in. Use tensor.detach.numpy, and you'll often find this if you're trying to plot tensors that have gradients tracked. So we checked out this before by going image out of conv.requiresGrad. This is how we know that our feature maps are learnable, or our embeddings are learnable, because PyTorch is behind the scenes going to track their gradients. So I just put back in these detach and numpy, which was the suggestion here, tensor.detach.numpy. So thank you for the error codes, PyTorch. Let's run that and see what it looks like. Okay, so these look like nothingness, but behind the scenes, they are actually what our convolutional feature map looks like. So if we were to closely look at this image, we would sort of be able to make it out in these feature maps. So if we ran it again, have a look at 5 more feature maps. Now this is not the best image to visualize, so I might just run all again so we get a new image. And while that's running, let's prepare some code. So what do we want to do? So we want to get a single feature map in tensor form. Single feature map. This is just another part of visualization. Image out of conv. We haven't got to the flattening of the later dimensions yet. So this is just going to be a single feature map. And let's go single feature map. Hopefully we get a better looking image. Oh, okay. So that's got some outlines above. We're looking good here, people. Dot requires grad. So this is what our single feature map looks like. A whole bunch of numbers, and it requires grad. So this is going to be a learnable representation of our image. So what does our image look like now? Pizza. So there's a pretty definite sort of line there. I didn't really have the words to describe that, but an outline of a pizza. Now, if we look in this feature map, can we kind of see? You can kind of see where those outlines are. So if we run this again and have a look at 5 more random, we get some outlines here. And you might want to try this with your own images. Of course, your image may be different to mine, but if I keep running this, we get slight different. Now, of course, these are going to change over time, and we don't necessarily need to understand what's going on with these ourselves, because this is what the computer is going to recognize our images are as. So these are just random convolutional feature maps to begin with, but these will be learned over time. That's the important point. So let's keep going. What are we trying to do? We're trying to flatten this feature map into a sequence. So we want to bring this row over here. Maybe we use the last one because it's got more space. So this is the first row. Then we want to bring this row up here. So we've got over to there. Then this row up here. So we've got over to there. And so on and so on. So that the input sequence is obtained by simply flattening the spatial dimensions of the feature map. So this is the feature map, and we want to flatten the height and the width so it's a single sequence. And we can do that with the flatten layer. So let's go here. We want 4.4, flattening the patch embedding with torch nn.flatten. And now, to prevent this video from getting too long, I'm going to issue a challenge. I know we said we were going to take care of this in this video, but I thought it was important to visualize what a feature map actually is. This is a learnable representation of our image created by our conv2D layer. So right now we have an image of this shape, or an output from our conv layer, which is 768 feature maps of size 14 by 14. But we want to change this these two last dimensions, we want to flatten that into a single dimension of 196. So my challenge to you is see how you can do that with the flatten layer. Can you take this input, pass it to the flatten layer, and get an output that is in the shape of 1768196? That's what we're after. So give that a go, and I'll see you in the next video. Welcome back. So in the last video, we explored our convolutional feature maps after passing a single image. So for me, I've got an image of pizza right now. Yours might be a little bit different, through to our conv2D layer. And we see that we get 768 feature maps because that's what we set our embedding size to be. And right now, the feature maps kind of represent the input image. But it's not really that important that we can understand what these feature maps are as much as the computer can understand what they are, because this is going to be the learnable representation that our VIT architecture uses behind the scenes to represent each image. And so we're just working with one image for now to keep things simple, and we're up to flattening the patch embedding with torch.nn.flatten. And you might have tried this already, but let's write down what we've got. Right now, we've got a series of convolutional feature maps that we want to flatten, and these convolutional feature maps are our patch embeddings that we want to flatten into a sequence of patch embeddings to satisfy the criteria of the VIT transformer encoder. Now this should really be the input criteria. And of course, this information is from here, hybrid architecture. The input sequence is obtained by simply flattening the spatial dimensions of the feature map and projecting to the transformer dimension. So you might have already looked up the documentation for torch.nn flatten. This is the hint I gave you in the last video that we can flatten certain dimensions here. Now we've used flatten before, but we haven't passed in the parameters. So we can choose which dimensions, start dimension and end dimension, that we want to flatten. So let's try it out, hey? What dimensions do we want to flatten? We want to flatten these two. We want to keep this one. So let's flatten this and this into a single dimension. So I might just put a little note here. This is a shape, F, create a string, and this is, we got batch size, embedding dim, feature map height, feature map width. And I know we're spending quite a big amount of time on the patch embedding, but this is possibly the most important part of the entire architecture. Once we get this down pat, we can put all the other pieces of the puzzle together. There we go. So what size do we actually want here? Well, let's write down what we want. We want batch size, and then we want number of patches, and then we want embedding dim. So this is what we're working towards, and we're getting very close, don't you worry. Now, where is this from? This is the output shape that we calculated before. We did this by hand, right up here. So output shape is 196. Well, I've put the batch dimension on down below. So number of patches and embedding dimension. We've got the embedding dimension, and we're so close to getting the number of patches. So let's finish this off. We'll go here. So flatten layer equals nn. I might just from torch import nn. Flatten. What dimensions do we want to flatten? Start dim is 0, 1, 2. So we want to start on dim 2, and end dim is 3. So 0, 1, 2, 3. Beautiful. Now, why don't we see what happens when we pass image out of conv through our flatten layer? So flatten layer and image out of conv. What do we get? What if we check the shape? Yes! Look at that! So now we've got batch size, embedding dimension, number of patches, but what do we want? The order we want is batch size, number of patches, embedding dim. So how could we rearrange this? Well, let's put everything together, right? So put everything together. We'll start with a single image. So what's our image? So we'll go plot.imshow. Image.permute. Oh, this might be a hint of how we could rearrange those dimensions just above. So we've used permute plenty to rearrange the dimensions of an image for matplotlib. Who's to say we can't do it to rearrange the dimensions of a patch embedding tensor? Plot.title, and we'll go axis equals false, and then print. Let's go, we'll get the original image shape. I love printing the input and output shapes of every layer. Image shape. Now let's go turn image into feature maps. This is where we're going to use our convolutional layer and create the patches. So image out of conv. We've set the kernel size and the stride size to our patch size. So image.unsqueeze, I'm just adding a batch dimension here. So add batch dimension. Then I'll print the shape here. Image feature map, so patches, shape. We have image out of conv dot shape, not comma, want dot. Then what's next? So flatten the feature maps. So we'll go image out of conv flattened. So this is just going to be the same output here. So image out of conv through our flatten layer. We're on a roll here. Flatten. We'll get our flatten layer and then we'll pass it image out of conv. Beautiful. And finally, print flattened image feature map shape. Image out of conv. What do you reckon? Have we done it? We're going to be so close, I reckon. Flattened. A lot of code there, but let's see what happens. There we go. Oh, I didn't get the shape. So we've got pizza. So we go from 3 224 224 to 1 768 14 14 and then 1 768 196. But what can we do to rearrange these dimensions to get at what we want? What do we want? Batch size, number of patches, embedding dim. So let's go rearrange output of flattened layer. So let's go image out of conv flattened. And we might permute. What do we have to swap? We want to keep 0 there. And then we want to go 2, 1 dot shape. Image out of conv flattened. Do we have a typo here? Image out of conv flattened. I've definitely spelt this wrong. You might be able to see that. I can't really see that right now. Image out of conv flattened. There we go. Beautiful. Look at that. Batch size of 1, 196 patches, number of patches, and embedding dimension there. So we can go print F, and we'll get that here. We have just turned our 2D image into a 1D sequence of patch embeddings. Oh my goodness. So this shape is batch size, and then we have number of patches, and then we have embedding dimension. We have the input to our transformer encoder. That is amazing. Now, the question is, how do we turn these steps into a PyTorch layer? Because right now it's kind of all over the place. So that's my challenge to you, is actually first and foremost, try and visualize one of these patches or these flattened sequences, because this is a sequence. So try and visualize one of these to see what it looks like. And then try and turn the flattened layer that we created, as well as the convolutional layer, into a single PyTorch layer, so that if we pass the single PyTorch layer a single image or a batch of images, it'll go through this conv2D layer and then through this flatten layer, and then the output will be in this shape here. So give that a shot, visualize, and then turn our conv and flatten layer into a single layer. And we'll work towards that over the next few videos, but well done. We've now just gone from a single image to the correct input shape that we wanted for our transformer encoder. We're putting together the Lego bricks. We're going to push it further in the next video. I'll see you there. Welcome back. Over the last few videos, we've been working towards turning a single image into patches. Then we turn those image patches into patch embeddings using a convolutional layer. And then finally, we've just flattened our patch embeddings into a sequence of patch embeddings using the flatten layer. And now we've got the input shape for our first layer and the output shape correct. So this is a fantastic milestone to reach, but let's not stop there. Let's visualize one of these single flattened sequence of patches just to see what it looks like. So we'll start off by, you might have already done this by the way, because that was a challenge I issued in the last video, but let's get a single feature map. We'll go single flattened feature map equals image out of conv, and then we'll go flattened, and then we'll go reshaped, and here we want to get, so this indexing here, oh, excuse me, maybe I save this to a variable here, and we'll go image out of conv flattened permuted. And then I'll copy this in here, just so we have two different variables for the original and one that's been permuted. So I want this here. So I'll run this and then visualize this. So see these indexes here is batch size, number of patches, I want all of that. And then the embedding dimension, I just want the 0th one, so only the first one. So single flattened feature map. Wonderful. So this is an embedding vector. So this is what one of our images is represented by. 768 of these flattened embedding vectors. And now the beautiful thing, I've said it a lot of times, is that this is going to be learnable, so it's going to be updated over time. And that's the beautiful thing about machine learning, is that, or embeddings in general, it's all about the embedding. So plot the flattened, let's plot this, hey? Visually, plot the flattened feature map visually. So this might not look like much, but that's not for us to decide, because this is the representation that our model is going to be using. So 22 by 22, this is a machine learning cooking show, so I kind of know these figure sizes ahead of time. So single flattened feature map, and now we want to detach. Why do we want to do that? Because we've learned before that matplotlib doesn't work too well with tensors that have their gradients tracked, and we turn it into numpy because matplotlib loves numpy. So flattened feature map shape, we'll just get a little bit of a printout here. Single flattened feature map dot shape, and then finally let's go plot axis false. Let's see what it looks like. Ah, okay. So it doesn't look like too much to me. It might look like something to you, but this is what we've turned our image into. We've gone from a single image like this into a patch embedding, into a flattened sequence of patch embeddings. And so what does this look like? I mean, it doesn't look as pretty as the original paper, but this is what we've got. We've got a series or a sequence of vectors to pass into our standard transformer encoder. Now, mind you, we haven't yet got the class learnable embedding, but we can do that in a future video, as well as the positional embeddings. But we've gone from image to patches to sequence of patches, all in a linear projection of flattened patches, or a learnable embedding, linear embedding. So many different words for embedding here. But let's keep pushing forward. And just summarize what we've done. We've recreated this section of equation 1, the patch embedding. We've got a sequence of patch embeddings. This is our vector. So now we're going to push towards making the class token embedding and the position embedding. But first, what we should probably do is, as I discussed in the last video, and what you might have already tried, is to convert our flatten layer and convolutional layer, which we made up here, to turn an image into a sequence of patch embeddings into a single PyTorch layer, so that we could just pass it, hey, here's our image, turn it into that. That's what we want. So that's your challenge for this video. Give it a go, and we'll do that together in the next video. Friends, welcome back. So far we've gone from a 2D image here to a flattened 1D learnable embedding vector, or in VIT terms, a linear projection of flattened patches. But right now our code is a little bit all over the place. So let's turn it into a single PyTorch module, because that's our goal, right? We want to turn a paper from math, text, and figures into reusable code. So I'm going to make a little heading here. 4.5, turning the VIT patch embedding layer into a PyTorch module. So what we're doing here is we're slowly constructing layers and blocks, inputs and outputs, little Lego bricks that we can eventually put together and create the overall VIT architecture. So we want this to do a few things. We want this module to do a few things. 1, create a class. We'll call it the patch embedding class. Nice and simple. 2, we want it to initialize with appropriate hyperparameters, such as channels. We want embedding dimension and patch size. 3, what else do we want to do? Well, we want to create a layer to turn an image into embedded patches using conv2d and encom2d. You might want to go ahead and try this out yourself once we've got these steps, by the way. So you can pause the video, and then we want to create a layer to flatten the feature maps of the output of the layer in step 3, so the flatten layer. And then 5, we want to define a forward method, because if we're creating a PyTorch module, this is going to, that inherits from nn.module. Recall that we've made a few of these now. All PyTorch subclasses, or all classes that subclass nn.module, should have a forward method that defines the forward computation. So we want it to, e.g., pass through layer from 3 and 4. And then finally, 6, we want to make sure the output shape of the layer reflects the required output shape of the patch embedding. We want to make sure our shapes line up, right? Because that's one of the biggest issues in machine learning and deep learning, is mismatched tensor shapes. So there's a few steps here, and my challenge to you is to pause the video now and give this a go. And I have some advice for you. It's from one of my favorite people. Oh, well, before we get into it, I'll just show you what we want our layer to do. So this is our original image input. We might come and rewatch this movie again. So original image, this is what we want it to do. Cut it into patches using the conv2d layer. Now we've done this by hand so far. There we go, conv2d. Then we want to set the kernel size equal to the patch size, so we can create a patch here. Then we set the stride equal to the patch size as well. So our kernel steps over patch size steps each time. Now this is only 9 patches, but our image is going to use more than that. Then we're going to flatten it into a sequence using a flatten layer. And then these steps will come later on, but these are the first steps that we want to focus with the module that we're building now. And so this is Lao Tensor, one of my favorite people in the world of machine learning lore. You can see he loves machine learning. He's got PyTorch and TensorFlow symbols there. Just remember, the creation of a deep neural network starts with the first layer. So that's a wise quote from Lao Tensor, and that's what we're doing here. We're rebuilding VIT, and this is starting with the first layer. So give that a shot, and I'm going to continue the video in 3, 2, 1. How'd you go? Did you create the patch embedding layer? I hope you gave it a shot. Otherwise, let's do it together, hey? So I'm going to start off by creating a class and call it patch embedding. So this is step 1. Step 1, create a class called patch embedding. And we want the input and output of this layer or class or PyTorch module to be, not patching embedding. I want it to be patch embedding. To be an image and the output to be something like this. So let's see if we can do that, hey? Then we need to initialize our layer. So this is step 2. Initialize the layer with appropriate hyperparameters. Now we're going to construct this in a way so because we're focusing on replicating Vit base to begin with, we're going to construct our layers though in a way that if we wanted to add more parameters later on, we could do that. So we can do that by setting this in channels. We'll give it a type hint to be int. Out channels, we don't actually need that. That'll be the embedding size, won't it? So the patch size, we want that to be 16 by default. And then the embedding dimension, which will be the out channels of our conv2d layer, is going to be 768. This is from table 1 for Vit base. So you see later on, if we wanted to create this class, an instance of this class, we could update the embedding dimension there if we wanted to, and also the patch size. So let's keep going. We'll call super.init. Wonderful. And now we have to start setting up our layers. So we need to create a layer to turn an image into embedded patches. Embedding patches, embedded patches. We've got typos galore through here, but we're not here to learn how to type properly. So step 3 is to create a layer to turn an image into embedded patches. So let's call this self.patcher for the patching layer. And we'll use nn.com2d. So just exactly the same steps that we did above. We just need a layer that's going to replicate this. So we have in channels is 3, out channels is the embedding size, and the kernel size is equal to the patch size, and the stride size is also equal to the patch size. So we'll come back down here. So I'll set the in channels equal to in channels, because that's going to be this parameter up here. And then the out channels, what will that be? The out channels will be the embedding dimension. Embedding dimension. Then we can set the kernel size is going to be equal to the patch size. The stride is equal to the patch size. Look at us go, we're on a roll. And then the padding is equal to 0. We don't need any padding here. Beautiful. So let's keep going. Number 4 is to create a layer to flatten the feature maps of the output of this. So we just want to replicate what we've got here. Nice and simple flatten layer to flatten the feature map dimensions of the output of our convolutional layer. So just like we did in the step above. So that's going to flatten our patch embeddings into a sequence. So create a layer to flatten feature map outputs of conv2d. Self.flatten equals nn.flatten, and the start dimension is going to be dimension 2, and the end dimension is going to be dimension 3. Beautiful. Now what are we up to? So we've got to define a forward method. Look at us go. We're creating the patch embedding. I mean, that took us a while to create it, but now we're just replicating the whole thing. After we've been through it step by step, we're doing the whole thing in a few lines of code here. So forward, I'm going to take self. I'm going to just write a little note here. Number 5 is define a forward method to define the forward computation steps. Not the most ideal comment, but we get what's going on. So the input here is going to be our input image, and we want it to go through the patch embedding first. But we also want to get the image resolution. Let's get a little check here, hey? We'll make an assertion, because we want to make sure that the image resolution is compatible with the patch size. To check that inputs are the correct shape. So we can go image resolution equals x.shape, and we'll get the last dimension. And then we'll create an assertion here. So we want to assert that the image resolution is divisible by the patch size and that there's nothing left over. And so if it's not, let's go input image size must be divisible by patch size. And the image shape we'll put in here, image resolution, and then we'll go patch size is equal to self.patch size. Beautiful. I think that should work. If not, we'll find out, won't we? Let's now perform the forward pass. So if our input image passes the assertion, we want to now pass it through the patch embedding. So we'll set it to xPatched equals self.patcher on the input. And then we can pass it through we'll call it xFlattened, and pass it through the flatten layer, self.flatten, and we'll pass the patched embedding through there. Wonderful. And now finally, we want to recall that the output of this is not going to be in the right order of dimensions. So we originally had, the embedding dimension as dimension 1, but we want the number of patches as dimension 1. So we can call a permute, just like we've done here, to rearrange it to be batch size, number of patches, embedding dimension, right at the end. So that's step 6. Make sure the returned sequence embedding dimensions are in the right order. So we want batch size, number of patches, and then embedding dimension on the end. Return, we want xFlattened, and we're going to permute. We want to change, keep 0 where it is, so keep the batch size where it is, then we want 2, 1. Now, is that correct? Well, we're going to find out, aren't we? So how do we test this? We're going to pass an image through, and we can also test our assertion as well, right? So let's call our setSeeds function, because whenever we instantiate a layer, it's going to instantiate with random weights. So if we instantiate an instance of this, just to try and make sure you're seeing what I'm seeing, we'll set the seeds, and actually we're probably going to see something different, because unless your image is the same as mine, we're going to get different results. So let's go create an instance of patch embedding layer. So we're mostly interested in seeing the shapes are correct here. Patch embedding, this is just what we've got above. So we don't actually need to insert any parameters here because the defaults are going to work for us. But why don't we do that for completeness? Patch size equals 16. So this is where you can see that if we wanted to change the patch size, we could. And if we wanted to change the embedding dimension to something else, we also could do that. And so let's go pass a single image through patch embedding layer. So let's go print, we'll go input image size, go image.unsqueeze 0.shape, and then we'll go patch embedded image equals patchify. So this is our layer that we just created here. And then we'll pass through image.unsqueeze, add a batch dimension. So here, add an extra batch dimension. We did the same thing here as well, actually. And what is Colab telling me? Oh, I need to finish the F string here. Did you catch that? And then finally, let's print the output shape. Output shape. This is actually a sequence or a patch embedding sequence shape. A lot of manipulation here, but that's all right. Nothing we can't handle. Patch embedded image. Do we have the right shape? 3, 2, 1. Let's go. No errors. Yes! We did it. We've got a single layer here that now turns our single image into a patch embedding or a sequence of patch embeddings. Look at that. We start with the image, 1, 3, 2, 2, 4, 2, 2, 4, and we end with 1, number of patches, embedding dimension, which is exactly what we wanted. If we come right back up here where we calculated the input and output shapes by hand, oh my gosh, we've written a lot of code. Here we go. Input shape. Well, our color channels is at a different point, but that's okay. And then we've got here the output shape, single 1D sequence of patches. Well done. We've got our first layer of the VIT. So what's next? We could reuse this whatever we want. Patch embedding. What should we do next? Well, we've got the main part of equation 1 done, right? So equation 1, the patch embedding. Now I've just altered figure 1 a little bit just to focus on the linear projection of flattened patches. This is what we've replicated. We've gone from a 2D image into a sequence of flattened 2D patches. So we split an image into fixed size patches, linearly embed all of them. So that's what we've done. We've created these linear projection of flattened patches. We've made this portion of equation 1. So if we keep going, this is what we've replicated so far, one layer at a time, patches and map to D dimensions with a trainable linear projection. So D dimensions is our embedding dimension. So if we use an embedding size of 768 and an image size of 224, 2243, we've now got number of patches 196 with an embedding size of 768. And this is going from this shape to this shape, which is this shape, height, width, color channels, to number of patches times patch size squared dot color channels. So that's a huge effort. And to see it in code, well, this is what we've done. So now we've done probably the largest portion of the patch embedding. We still have the class token and the positional embedding. So you might want to think about how you could do that on your own. So we need to create this little class token here and these position embeddings. But we're going to start to do that together over the next few videos. So equation 1, the class token. Let's come and check this out in the next video. I'll see you there. Welcome back. In the last video, we created our first layer of the VIT architecture, the patch embedding. And we adhered to the quote from Lao Tensor, the creation of a deep neural network starts with the first layer. So it's very exciting, but we've got a few more layers to go. And just to show you that our assertion works, or we'll check if we can, to make sure that we've got the right image shape as we go through the patchify layer or the patch embedding layer, let's just create a random tensor, rand image tensor, and we'll set that to torch.randn, and we'll go 1, 3, 2, 2, 4, 2, 2, 4. So that's a good shape. So rand image tensor bad equals torch rand n 1, 3, 250, 250. So 250 isn't going to divide well by 16, which is what our patch size is. So let's just try to pass each one of these through. So patchify, we'll go rand image tensor. How does that work? Oh, rand, not random. Wonderful. We get the output there. But then if we try to put through the bad one, do we get an error? There we go. Oh, wait. Has no attribute patch size. What's going on here? Oh, self.patchSize. We didn't initialize that. So self.patchSize equals patch size. There we go. So input image size must be divisible by patch size, image shape 250, patch size 16. So that's just an example of our assertion, making sure that our input image is compatible with the patch size. So let's now jump back to the keynote. And we're up to equation 1, the class token. So we've done this little portion here, but let's remind ourselves of what the class token is all about. So in order to perform classification, we use the standard approach of adding an extra learnable, that's a key word there, learnable, classification token to the sequence. So we've got this at the start here. So extra learnable class embedding. And then we have this token right at the front of our patch embedding sequence. So similar to Bert's class token, we prepend. So prepend means to add to the front instead of append, which goes to the back. We prepend a learnable embedding, so our token needs to be learnable, to the sequence of embedded patches. So at Z0, 0, 0, so right at the start, equals X class, whose state at the output of the transformer encoder, Z0L, so that's this one here, serves as the image representation Y, so that this is related to equation 4 as well. So prepend a learnable class embedding token to the 0 index of the patch embedding. So how do you think we might do that? Well, if in doubt, code it out. Let's go here. I'm going to create a little heading. I believe we're up to 4.6 maybe. 4.6, we'll go creating the class token embedding. Now what do we want to do? Want to prepend a learnable class token to the start of the patch embedding. Turn this into Markdown. So if we have a look, this is our patch embedded image. Patch embedded image. And don't worry too much if your numbers are different to mine. This is because we're probably using a different image or different random initialization, but the shape should be correct. So your shape should be something like this, or well, it should be exactly that. So the class token we want to prepend right at the start here of the number of patches dimension, that is. This will actually be 197 by the end of this section, because we're going to prepend a learnable class token to the front of each one of those. So let's start with that. Now, how do you create a single learnable token? And I'll give you a hint. I'm pretty sure we covered this right back in PyTorch workflow fundamentals. Do we have parameter? Yes, here we go. NN parameter contains the smaller parameters like weights and biases. Put these together to make NN modules. So right back at the start, we created the linear regression model using NN parameter to create weights. And NN parameter has requires grad equals true. So that makes it learnable. There we go. Requires grad equals true means PyTorch will track the gradients of this specific parameter for use with torch.autograd and gradient descent. For many Torch NN modules, requires grad equals true is set by default. That means it's a learnable parameter, which is exactly what we want, right? In order to perform classification, we use the standard approach of adding an extra learnable classification token. So let's see what this might look like in code. We'll start off by get the batch size and embedding dimension. And batch size, because we've got our patch embedded image, because we want this class token to work across batches. So patch embedded image, we'll get the shape, and then we'll get the embedding dimension. Now we already know these, but we want to be able to write code that works regardless of what the values are. So rather than hard coding the batch size or hard coding the embedded dimension, we want to get it from the patch embedded image. So then if we go, we got a typo here. Let's check out the batch size and embedding dimension. Wonderful. So right now we're working with a single image and our embedding dimension is 768. So now we want to create the class token embedding as a learnable parameter that shares the same size as the embedding dimension. So this will make sense in a second. D. So let's try this out. Class token equals nn.parameter. Why are we using that? Because nn.parameter is going to make this token learnable. And then for demonstration purposes, I'm going to create the class token as a series of ones. In practice, you'd probably use torch.randn, but ones is going to just make it more visible. So later on, when we make it officially, we'll use rand_n, but we'll start with ones. So let's go batch size. Then we only want one single token for the class token because it's just a single token, and then embedding dimension on the end here. So we've got a few steps there, but we'll see what it looks like in a second. And we'll go requires grad equals true. Now this is by default. We don't actually have to set that, but I'm just showing you that this parameter is going to be learnable. Now let's have a look at the class token. Beautiful. So we have a parameter containing all of these tokens here. And so if we go, let's get the shape, hey? So we have torch size 11768. That's beautiful. That's exactly what we want because we want to go patch embedded image dot shape. We want to add this one across every dimension of these. So that's why we have to match up the dimensions on the end here. So how can we do that? Well, let's prepend it. So add the class token embedding to the front of the patch embedding. Because if we go back to the keynote, we want it to be right at the front. So right now we've got this embedding. We want to add it, the class token to the front. So I'm not sure if we've covered this method yet of how to do that, but we will. So how could you add something to the front of a tensor in PyTorch? Well, let's look at that up. Add value to front of tensor in PyTorch. How do I add an element to a PyTorch tensor along somewhere? Oh, torch cat, that might help. Appending to a tensor, insert an element to a tensor. How to append an int tensor to a list tensor. So we've got a whole bunch of different options there, but let's just keep going. So I'm going to create a patch variable here. Patch embedded image with class embedding equals torch.cat for concatenate. And then we pass in a tuple here or a list of tensors. So we're going to first want to concatenate the class token, which is what we just made up here, to the front. So that's why it comes first. Class token to the patch embedded image. And what dimension do we want it to go on? Dimension 1, because that is dimension 1. Dimension 1, that is the number of patches dimension. Number of patches, we'll go underscore, number of patches dimension. And we've got a typo here once again, no worries. So let's see what happens. So let's print out our updated patch embedded image with class embedding. Our variable names are getting quite long here. And then we'll go sequence of patch embeddings with class token prepended shape. So we'll go here. We'll get the shape of the above variable. So patch embedded image with class embedding dot shape. This is going to be batch size, if we've done it right, that is, number of patches, and then embedding dim. Number of patches, or well, class token, plus number of patches. You ready? 3, 2, 1, let's go. Beautiful. That's exactly what we wanted. So we've now got a series of ones at the start of our sequence of patch embeddings. So I did it with ones to demonstrate, but of course, if we just change this to rand_n, it's a little bit harder to see, but it'll do the same thing. Yeah, you can't really tell the difference there. So that's why I did ones at the start there. So ones, but in practice, we do rand_n, so it starts with a random number and gets optimized. So now we've got this learnable class token right at the front of our sequence of patch embeddings. And you'll notice that the shape has changed to be 197 because we've now got a class token right at the front. So if we go back to the keynote, we've now got this section here. And you might see that ePOS, This is why ePOS, the shape of ePOS, is n plus 1. Because we originally started with 196 patches, but once we add in the class token, we now have 197, which is why we have number of patches plus 1. So over here, this is our linear projection of flattened patches, or in our case, we have 196 of them. But then we just added this learnable class token to the front, we prepended it, so now it's n, number of patches plus 1. So when we create our position embeddings, which is going to be in the next video, we need to make sure that it's the same shape as our linear projection of flattened patches plus the class token, which, the beautiful thing, we've already got that here. So we're almost finished with the patch and position embedding. We've got one more thing to do, and we've hinted at that already. It's the position embedding. You might want to skip forward and give it a shot yourself, but otherwise, I'll see you in the next video. Let's create some position embeddings. Welcome back. In the last video, we created our first layer of the VIT architecture, the patch embedding. And we adhered to the quote from Lao Tensor, the creation of a deep neural network starts with the first layer. So it's very exciting, but we've got a few more layers to go. And just to show you that our assertion works, or we'll check if we can, to make sure that we've got the right image shape as we go through the patchify layer or the patch embedding layer, let's just create a random tensor, rand image tensor, and we'll set that to torch.randn, and we'll go 1, 3, 224, 224. So that's a good shape. So rand image tensor bad equals torch rand n 1, 3, 250, 250. So 250 isn't going to divide well by 16, which is what our patch size is. So let's just try to pass each one of these through. So patchify, we'll go rand image tensor. How does that work? Oh, rand, not random. Wonderful. We get the output there. But then if we try to put through the bad one, do we get an error? There we go. Oh, wait. Has no attribute patch size. What's going on here? Oh, self.patch size. We didn't initialize that. So self.patch size equals patch size. There we go. So input image size must be divisible by patch size, image shape 250, patch size 16. So that's just an example of our assertion, making sure that our input image is compatible with the patch size. So let's now jump back to the keynote. And we're up to equation 1, the class token. So we've done this little portion here, but let's remind ourselves of what the class token is all about. So in order to perform classification, we use the standard approach of adding an extra learnable, that's a key word there, learnable, classification token to the sequence. So we've got this at the start here. So extra learnable class embedding. And then we have this token right at the front of our patch embedding sequence. So similar to Bert's class token, we prepend. So prepend means to add to the front instead of append, which goes to the back. We prepend a learnable embedding, so our token needs to be learnable, to the sequence of embedded patches. So at Z0, 0, 0, so right at the start, equals X class, whose state at the output of the transformer encoder, Z0L, so that's this one here, serves as the image representation Y, so that this is related to equation 4 as well. So prepend a learnable class embedding token to the 0 index of the patch embedding. So how do you think we might do that? Well, if in doubt, code it out. Let's go here. I'm going to create a little heading. I believe we're up to 4.6 maybe. 4.6, we'll go creating the class token embedding. Now, what do we want to do? Want to prepend a learnable class token to the start of the patch embedding. Turn this into Markdown. So if we have a look, this is our patch embedded image. Patch embedded image. And don't worry too much if your numbers are different to mine. This is because we're probably using a different image or different random initialization, but the shape should be correct. So your shape should be something like this. Or well, it should be exactly that. So the class token we want to prepend right at the start here of the number of patches dimension, that is. This will actually be 197 by the end of this section, because we're going to prepend a learnable class token to the front of each one of those. So let's start with that. Now, how do you create a single learnable token? And I'll give you a hint. I'm pretty sure we covered this right back in PyTorch workflow fundamentals. Do we have parameter? Yes, here we go. NN parameter contains the smaller parameters like weights and biases. Put these together to make NN modules. So right back at the start, we created the linear regression model using NN parameter to create weights. And NN parameter requires grad equals true. So that makes it learnable. There we go. Requires grad equals true means PyTorch will track the gradients of this specific parameter for use with torch.autograd and gradient descent. For many Torch NN modules, requires grad equals true is set by default. That means it's a learnable parameter, which is exactly what we want, right? In order to perform classification, we use the standard approach of adding an extra learnable classification token. So let's see what this might look like in code. We'll start off by get the batch size and embedding dimension. And batch size, because we've got our patch embedded image, because we want this class token to work across batches. So patch embedded image, we'll get the shape, and then we'll get the embedding dimension. Now we already know these, but we want to be able to write code that works regardless of what the values are. So rather than hard coding the batch size or hard coding the embedded dimension, we want to get it from the patch embedded image. So then if we go, we got a typo here. Let's check out the batch size and embedding dimension. Wonderful. So right now we're working with a single image and our embedding dimension is 768. So now we want to create the class token embedding as a learnable parameter that shares the same size as the embedding dimension. So this will make sense in a second. D. So let's try this out. Class token equals nn.parameter. Why are we using that? Because nn.parameter is going to make this token learnable. And then for demonstration purposes, I'm going to create the class token as a series of ones. In practice, you'd probably use torch.randn, but ones is going to just make it more visible. So later on, when we make it officially, we'll use randn, but we'll start with ones. So let's go batch size. Then we only want one single token for the class token because it's just a single token, and then embedding dimension on the end here. So we've got a few steps there, but we'll see what it looks like in a second. And we'll go requires grad equals true. Now this is by default. We don't actually have to set that, but I'm just showing you that this parameter is going to be learnable. Now let's have a look at the class token. Beautiful. So we have a parameter containing all of these tokens here. And so if we go, let's get the shape, hey? So we have torch size 11768. That's beautiful. That's exactly what we want because we want to go patch embedded image dot shape. We want to add this one across every dimension of these. So that's why we have to match up the dimensions on the end here. So how can we do that? Well, let's prepend it. So add the class token embedding to the front of the patch embedding. Because if we go back to the keynote, we want it to be right at the front. So right now we've got this embedding. We want to add the class token to the front. So I'm not sure if we've covered this method yet of how to do that, but we will. So how could you add something to the front of a tensor in PyTorch? Well, let's look at that up. Add value to front of tensor in PyTorch. How do I add an element to a PyTorch tensor along somewhere? Oh, torch cat, that might help. Appending to a tensor, insert an element to a tensor. How to append an int tensor to a list tensor. So we've got a whole bunch of different options there, but let's just keep going. So I'm going to create a patch variable here. Patch embedded image with class embedding equals torch.cat for concatenate. And then we pass in a tuple here, or a list of tensors. So we're going to first want to concatenate the class token, which is what we just made up here, to the front. So that's why it comes first. Class token to the patch embedded image. And what dimension do we want it to go on? Dimension 1, because that is dimension 1. Dimension 1, that is the number of patches dimension. Number of patches, we'll go underscore, number of patches dimension. And we've got a typo here once again, no worries. So let's see what happens. So let's print out our updated patch embedded image with class embedding. Our variable names are getting quite long here. And then we'll go sequence of patch embeddings with class token prepended shape. So we'll go here. We'll get the shape of the above variable. So patch embedded image with class embedding dot shape. This is going to be batch size, if we've done it right, that is, number of patches, and then embedding dim. Number of patches, well, class token, plus number of patches. You ready? 3, 2, 1, let's go. Beautiful. That's exactly what we wanted. So we've now got a series of ones at the start of our sequence of patch embeddings. So I did it with ones to demonstrate, but of course, if we just change this to rand end, it's a little bit harder to see, but it'll do the same thing. Yeah, you can't really tell the difference there. So that's why I did ones at the start there. So ones, but in practice, we do rand end, so it starts with a random number and gets optimized. So now we've got this learnable class token right at the front of our sequence of patch embeddings. And you'll notice that the shape has changed to be 197 because we've now got a class token right at the front. So if we go back to the keynote, we've now got this section here. And you might see that ePOS, this is why ePOS, the shape of ePOS is n plus 1. Because we originally started with 196 patches, but once we add in the class token, we now have 197, which is why we have number of patches plus 1. So over here, this is our linear projection of flattened patches, or in our case, we have 196 of them. But then we just added this learnable class token to the front. We prepended it. So now it's n, number of patches plus 1. So when we create our position embeddings, which is going to be in the next video, we need to make sure that it's the same shape as our linear projection of flattened patches plus the class token, which, the beautiful thing, we've already got that here. So we're almost finished with the patch and position embedding. We've got one more thing to do, and we've hinted at that already. It's the position embedding. You might want to skip forward and give it a shot yourself, but otherwise, I'll see you in the next video. Let's create some position embeddings. Welcome back. Now we are on an absolute roll here. We've just created the class token and prepended it to the start of our sequence of patch embeddings. So let's get a little visual overview of what we've just done. Equation 1, we've replicated the patch embedding sequence. Now we've replicated the class token. We're up to doing the position embedding. We'll get to that in a second, but let's just review what we started with. A sequence of patch embeddings. of size 1, 196, number of patches, embedding dimension. We then created a learnable class token. We set it to NN parameter. We use torch.ones just for demonstration purposes, but in fact, you'll probably use, or we will use later on, torch rand_n to start with a random number, because that's the whole art of machine learning and deep learning. Start with randomness and optimize it some way, shape, or form. Then we prepended it to the patch embeddings. So you'll see that we've now got this learnable class token right at the start of our patch embeddings, or our sequence of patch embeddings. So now our shape has updated from 196 to 197, and that is reflected in the position embedding dimension. So here's what we want to do. Add position embeddings. This is where the patch and position embedding name comes from, and that's here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And of course, this will go up to whatever number of patches we have. This is called the ePos, or position embedding, and ePos is an element of a real number of shape n plus 1, so number of patches plus 1. We've already seen this. In our case, it's going to be 197 times d, the embedding dimension. There we go. Add a learnable 1D set of position embeddings. So this is to retain positional information. The whole thinking behind this is we turned this image into patches, embeddable patches, using conv2D, but once you flatten it, the spatial information of the image is lost. So the position embeddings, the whole thinking behind it, is that if you prepend these, well, hopefully we can learn the order that these patches come in, so that this patch is known to be next to this patch, and so on. The paper, if you want to read more, states a little bit here, but then there's more in Appendix D.4. But let's focus on replicating this with some PyTorch code. So we'll come back here, up to 4.7, creating the position embedding. We're making you proud, Lao Tensor. So want to create a series of 1D learnable position embeddings and to add them to the sequence of patch embeddings. So this is going to be very similar to what we did with the class token. The difference here is going to be the shape, of course, because where the class token was just a single variable, the position embeddings go across the entire shape. So you might already know what sort of way we can create it. It's going to be very similar to this here. So if you want to pause the video and give it a go, you'll have to update the shape on this dimension though. If you gave that a go, well done. Otherwise, I'm back. I probably never left if you just kept the video rolling. But let's view the patch embedding so far with the class token. View the sequence of patch embeddings with the prepended class embedding. And it's very important what we're doing here. We're often checking the inputs and outputs of every single thing that we do, because that's really what a neural network is all about, is inputs feeding into another layer and then outputs of that layer feeding into another. So patch embedded image with class embedding, that is a very long variable name. Patch embedded image with class embedding dot shape, which is exactly what we've got above, but why not try it again? So here we go. So what we might try and do is create the position embedding with torch ones as well. And then in an ideal world, each one of these variables will have one added to them. That is because our position embedding goes across all of the dimensions here. So let's keep going. Let's try that out. We first need to calculate number of patches. Why do we do this? So this is because we don't want to be hard coding almost anything with our neural networks. We want it to be able to calculate itself behind the scenes. So if we did have a different n value here, it wasn't just hard coded at 196. It was inferring this from the data itself. So let's go back here. We know the formula for calculating n. Number of patches is equal to, we covered this before, int height. I'm turning it into an int because I want a round number. Width, it should be a round number anyway, shouldn't it? Divided by patch size squared. So then if we get number of patches, if everything is still set up correctly, we have 196. Beautiful. And then so get the embedding dimension. And really, ideally, we probably don't even get the variables height and width on their own. We just get this directly from the image, but we'll leave those how they are for now. And we'll go embedding dimension equals patch embedded image with class embedding. And then we'll go shape. We'll get the last shape there because our embedding dimension is on the end. Got a typo there, classic. 768, wonderful. So this will work now if we had a different embedding dimension. Now I want to create the learnable 1D position embedding. So let's go position embedding. This will be very similar to what we created above. Equals nn.parameter, so a learnable parameter of torch dot ones. Ones is just for demonstration purposes. And we can pass in 1 here, or we could do batch size. Batch size, but we'll just do 1 to begin with. And then we'll go number of patches plus 1. Why are we going to do that? Because it is n plus 1. That should come out to 197. And then we're going to do it across the embedding dimension. So now let's have a look at the position embedding. Position embedding, and we'll get the position embedding dot shape. Typo, of course. And then by default, by the way, this is just going to have the requires grad equals true. So it's learnable. Very important. Wonderful. Okay, so we've got the right shape there. Now, how do we add this to our patch embedded image with the class embedding? So this is what we got so far. We've got the pink tokens. We want to add the purple tokens. Well, we've got that plus symbol. So we can just do that because they're the same shape. We can just add them together. So let's do that, hey? We'll go add the position embedding to the patch and class token embedding. So we'll call this patch and position embedding because that's what the paper calls it. And then we'll go patch embedded image with class embedding. My gosh, possibly the last time we need to type that long variable, plus the position embedding. So that's all we're doing. All we've done is replicate exactly what this little equation is saying. There's our class token with our sequence of patch embeddings. We're just adding the positional information right here. So let's get out the shape, hey? Excuse me, I just had to pause the video because I had to sneeze. But we're getting the shape of our patch and position embedding, which shouldn't be any different from what we've got here. What we should notice is that the values have changed. So these are the original values. What I might do is we'll get this down here. Wonderful. And then we'll go print patch and position embedding. And now we'll get the shape. So patch and position embedding shape. So patch and position embedding dot shape. Beautiful. So there we go. That's exactly what we're expecting. So have a look. We've got all these values. Now, because we created the position embedding with torch ones, we add it to the patch embedded image with the class embedding. And so each one of the values in here, once we've added the positional embedding, increase by 1. But the shape stays the same. And this shape is reflective of the shape over here. Position embedding shape, number of patches plus 1, embedding dimension. So we've just replicated equation 1. We've created the class token, we've created the patch embeddings, and now we've added the positional embedding. So that deserves a big clap. Well done. We've done the first layer, but let's get a little bit visual. We'll finish it off. So this is the position embedding. We started with the patch embeddings with the learnable class token right at the start. This is what we did in the last video. So we've got 197, number of patches plus class token. We then created the position embeddings in the same shape as what we needed it. So we've got number of patches plus 1 along the embedding dimension. We made sure that they're learnable, and we created them with 1s for demonstration purposes only. So this is just, ones is easier to see the difference between these two, but in practice, we're going to do it with random. And then we have a patch embeddings with learnable class token and position embeddings. So we have this tensor here. This is our image representation. That's what's going to feed into our transformer encoder. Here's what we're going to do. This is your challenge for the next video. You can pause it here and try to replicate this, but we've done equation 1. So in the next video, we're going to put it all together. Here's a little spoiler. Don't look at this and try to put it all together. Go from an input image, replicate the patch embedding using our patch embedding class, create the learnable class token, prepend it to the start of the sequence and patch embeddings, and then add the position embedding. And then we should end up with our tensor that we have here. So give that a shot, and then the next video, we'll put it all together so that it happens in a single cell, from image to embedding. I'll see you there. Friends, welcome back. We've come a long way from turning our image into a sequence of patch embeddings. Now, how about we put together all of these sections here into a single cell so we can see it run end to end? So let's start up with section 4.8. Now, you might have already taken on the challenge of doing it, but we're going to do it together anyway, because seeing it all in one place is going to help with our understanding. So from image to embedding. So we've written code to turn an image into a flattened sequence of patch embeddings. Now let's see it all in one cell. To start off with, we're going to set the seeds so that we get reproducible results. We don't necessarily need to do this, but I'm just doing it in case you may have a different image to me. So that's why we may have different results. Just be aware of that. What image do I currently have? I have an image of steak. Now, of course, this is going to change every time you rerun the notebook. So if I run all of these cells, we're going to get a different image here because the training data loader is random. But all of this should run end to end. And so now we want to see it in one cell. So we're going to set the patch size. And we've been working with a patch size of 16. But of course, as you'll find in the VIT paper, there are different values for patch size. Patch size, I believe one of the other patch sizes that they use is 14, the authors. Yeah, VIT huge and a patch size of 14. But just recall, the lower the patch size, the higher number of patches there will be. So let's keep going here. Then we'll go 2. Let's find out the shapes. So print shapes of the original image and get the image dimensions. So this is important to know so that we can calculate n, which is the number of patches. So print image tensor shape, and we'll get image.shape here. And then we'll go height, width. We'll set these equal to our image.shape, and we'll get the first dimension there, image.shape, and we'll get the second dimension there. We'll just see what comes out here. And a little reminder of what our image looks like. It's a big tensor of numbers here. And then if we get the shape of that image, we have color channels, height, width. And I've just rerun all of these cells, so I should have a different image up here. Yeah, another image of steak. And why don't we just rerun all of those just for the hell of it while we're writing some more code down here. So next, what might we need to do? Well, we've got our image height and width. How about we get the image tensor and add a batch dimension? Why do we do this? Well, because our images are going to be in batches when they pass through our network. So we'll create an image called X. X is a generic variable name. Unsqueeze, and we'll unsqueeze it there. And then we can print, let's go input image shape is going to be x.shape. See what comes out there. So we've just added a batch on the 0th dimension. And next, what do we need to do here? Well, we can create the patch embedding layer. And this is where we can use the class that we created before. So we'll instantiate an instance of our patch embedding class. And we'll set in channels equal to 3 because we're dealing with a color image. We don't necessarily need to set these parameters here because by default, we've got in channels equal to 3, patch size equal to 16, embedding dimension equal to 768, in line with table 1. Recall that we're replicating vit base here, but we've set up our class so far in a way that if we wanted to change the embedding size, we could change it. But let's just stick with a patch size of 16. Well, patch size is going to be patch size above. And then embedding dim is going to be 768. So that's going to be our patch embedding layer. Now we've got an input image and we can pass it through, pass input image through patch embedding layer to create our series of patch embeddings. So patch embedding equals patch embedding layer, and then we'll pass in X, which is our batchified image, just up here, X. Now let's find out the shape. So patch embedding shape. Do you see what we're doing here? We're just constantly passing or manipulating data and then finding out how that data is changing. The input and output shapes, I keep writing patching here. Input and output shapes is one of the most important things in all of deep learning and machine learning. So let's now create a class token embedding. So this is the class token of equation 1. If we scroll up here, what we've just done is we've created this. So recall that we're going through equation 1 to begin with. We're putting it all together. We've done each of these parts individually. So now we're going to create the class token and prepend it to the patch embedding. And then we'll create the position embedding. Let's jump back in here. So the class token requires knowing what the batch size is, and we want to do this programmatically. So we'll get the shape. I keep writing patching embedding. So batch size equals patch embedding shape 0, so the 0th dimension there. And then we'll get the embedding dimension. The embedding dimension is the last dimension. So patch embedding dot shape. And we'll get the -1 there. So that's going to be the dimension on the end. I'll just run this so we know what's going on. There we go. So batch size is going to be 1 because we're just using one image. And the embedding shape is going to be 768 because that is the last dimension there. And now we can create the class token. Look at us. So this is where all that work that we've been putting in over the last few videos is all coming together. So torch.ones, I'm only using ones here for demonstration purposes. When we build the actual VIT architecture, we'll use torch.randn to start with a random number instead of a 1. So we'll make sure it's learnable. Now, the class token is learnable because it's in an nn.parameter. If we only used torch.ones, it wouldn't be learnable. So because we've wrapped it in nn.parameter, it is now a learnable parameter. So now let's print out the class token shape. I want to go over here. There we go. So print f class token embedding shape. So we will go class token dot shape. What's next? Well, we said we were going to create. Oh, I'm jumping ahead. We need to prepend the class token to the patch embedding, and then we can create the position embedding and add it to this. So let's go back into here. So we want to prepend the class token embedding to the patch embedding. So patch embedding class token. Variable names are getting a little bit longer here. So torch.cat, we want to concatenate the class token to the front of the patch embedding, which we have above, and across the first dimension. The first dimension being the number of patches here. So then if we check out the shape, so print patch embedding with class token shape. Let's go patch embedding class token dot shape. Let's see what that is. I'll run it again, step by step. There we go. So our class token has a shape of 11768, so our embedding dimension. And then if we prepend it to the front of the patch embedding, we now have an increased shape of, instead of 196, we have 197 because we've prepended this value here. So what are we up to next? Well, we have to create the position embedding. And the position embedding is a series of 1D learnable tokens. So, and we want it in this shape here so that we can just add it onto that. So we'll go create position embedding, and we'll set number of patches equal to int, and then we'll go height times width, so we can calculate this. Now this is where we get these values up here, height and width. And technically you could put all of this into a single class, such as patch embedding. And in fact, that might be a little extension that you want to try. See if you can put all of this into the patch embedding class. That'd be a really fun exercise. And then divided by patch size. So that's going to calculate the number of patches. We're doing this programmatically because we never really want to hard code values. Wherever we can calculate things on the fly, that's often a good choice. So position embedding is going to be also an nn.parameter, so it's learnable. That means PyTorch behind the scenes is going to track the gradients and then update them with gradient descent via our optimizer.step. So we'll calculate this as number of patches plus 1, this size, and this is going to be, of course, embedding dimension, which we have already saved. So the embedding dimension stays consistent throughout the entire transformer or the vision transformer layer. Wonderful. And then what do we do now? We can add it. So add the position embedding to patch embedding with class token. So patch and position embedding equals patch embedding class token. So the value that we have above here. So this is what we're replicating right now. This is patch embedding with class token, and we want to add the position embedding. So plus position embedding. Wonderful. And now let's print out. Have we just put everything together? Patch and position embedding shape. So we want patch and position embedding dot shape. Let's see. Does it all come to life? No errors. Wonderful. That's exactly what we wanted. Look how far we've come. We started with an image tensor and we slowly broke equation 1 down step by step. We first turned our image into learnable patch embeddings. Then we created a learnable class token and prepended it to those learnable patch embeddings. Then we created a position embedding and added it to that class token and patch embedding. So a fair bit going on there, but we've just broken that down step by step, and now we're doing it in one single cell. So we've got a way to go from an image to, this should be into a flattened sequence of patch embeddings. That is equation 1. We've just replicated equation 1. We've turned it, let's go back to the keynote. We've turned equation 1 into reusable PyTorch code. And now I've said a good extension to this would be we've got a fair bit going on here in terms of creating the class token, prepending the class token, creating the position embedding, and adding that position embedding to the patch embedding. All of this could really be incorporated in the patch embedding class. So my challenge to you is to see if you can incorporate that into this class. And if you do, post it on the course GitHub and show me your code, and I'd love to see it. So just to summarize, then we create the class token, and then finally we create the position embedding and add it to the other embeddings that we have here. So that is equation 1. Now, what have we got to do next? Equation 2. If you want to read ahead, I'd encourage you to do so. See if you can work it out. See if you can map where equation 2 fits into this figure. And otherwise, we'll continue on in the next video. Welcome back. Now we are on an absolute roll here, but let's not stop there. We've put it all together. We've replicated equation 1. We've now got a way to turn our images into a flattened sequence of patch embeddings, which is equation 1 here. We've got that in PyTorch code now. And if we go back to figure 1, we've now got this little section here. We've got a way to patchify our image and turn it into a linear projection of flattened patches. So now let's start working towards replicating the transformer encoder. And the transformer encoder, as you can see, is comprised of 4 main layers, but also comprised of 2 main blocks. So I'm going to call this a block here, and this a block here. So this block is defined by equation 2, and this block is defined by equation 3. So let's start with replicating this block here, or equation 2. So if we jump down here, we've got this. It's a fair bit going on here, but we've got Z prime of a certain layer equals MSA, which stands for multi-head self-attention. MSA layer wrapping a layer norm layer with the input of the previous layer, so ZL-1, plus that input. Residual, or skip connection. That's a fun word to say, residual. So a fair few things going on there, but of course, if you wanted to learn more, how could you find out? I've already searched this. What is multi-head self-attention? Plenty of resources there. What is layer norm? Plenty of resources there. So let's jump back to the keynote. So that's how you would find more information about what we're covering. We're going to focus on writing the code to implement it though. So just to rehash, here's what we've done so far. We've split our image into patches. We've flattened those patches, or we've embedded them. This is what we've already done, equation 1. Kernel size equals patch size, tick. Embedding of this patch, tick. Embedding of all the other patches, tick, 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 tick. Flatten into a sequence. We've got that. This is what we're up to so far. We've got that. Then we added the class token embedding over here. Then we added the positional token embeddings. Beautiful. Now we need to start replicating the transformer encoder block. So let's get started on that. We don't need to see any more of that. You can replay that if you like. Equation 2, the MSA block. This is what it's called. MSA stands for multi-head self-attention. Equation 2 is, we're going to refer to this as the MSA block. So the transformer encoder, which is this grey big block here, consists of alternating layers of multi-headed self-attention, so multi-headed self-attention, and MLP blocks, equation 2 and 3. Equation 3 is the MLP block. And layer norm, which is this yellow layer here, is applied before every block. So layer norm here, layer norm before MSA, that's why it's on the inside of the brackets here. And residual connections are after every block. So this, we're adding the input to the output of the block. And the same thing with up here. But we're going to begin with replicating this, equation 2, the MSA block. So if we wanted to learn a little bit more about multi-head attention, well, one thing, we could search it. So what is multi-head self-attention? And we've got some explanations here. We find that it was first introduced in the paper Attention is All You Need. So we'll let this load. It might take a little bit longer to load because the PDF's on archive. Oh, that's pretty quick, but we'll come back to that in a second. But if we wanted to find out more about it, where else could we find out? Well, the paper says here, Appendix A. So if we look at what Appendix A says, we have multi-head self-attention from Attention is All You Need paper. And look at this, we have more equations. We have 1, 2, 3, 4, 5, 6, 7, 8. But the beautiful thing is that for many of these layers here, is that PyTorch has implemented them for us. So typically, if a layer gets used quite often, PyTorch will recreate this. So we have standard QKV self-attention. That's a little bit hard to read for me. From S.A. Vaswani et al. 2017. So that is the Attention is All You Need paper. If we go up here, we're jumping around a bit, but that's all right because this is the nature of research and paper replicating. There's Ashish Vaswani. So that's that name, Attention is All You Need, from 2017. There's a whole bunch of other researchers from Google Brain and University of Toronto. So this is why paper replicating is a bit of a challenge, right? Because not only is this paper authored by a dozen or so researchers from the Google Brain team, it leverages research from a whole other team of people from the Google Brain team. And of course, that's not all. There's a lot more references down below here. So this paper is built off the research from about 30 or 40 others. So we're not doing any small feat here. But let's jump back. Attention is all you need. If we scroll through here, where do we find it? You can read all this as extension if you want. There's the original transformer network. As you can see, this is very similar to our transformer encoder. We've got a multi-head attention, add and norm, feed forward, add and norm. Feed forward is another word for MLP. We've got our input embeddings, but this was originally for text. Ours is for images. So we come down here, attention, beautiful. So we've got an attention function can be described as a mapping, a query, and a set of key value pairs to an output, where the query, keys, and values and output are all vectors. So we've got a vector right now. We've got an embedding vector of our flattened sequence of images. The output is computed as a weighted sum of the values, where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. So this is where papers get a little bit technical, like compatibility function. Behind the scenes, it is actually just a matrix multiplication. You see here? The output is computed as a weighted sum of the values, where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. So to me, that sounded quite wordy. But if you look at it in a diagram or this beautiful colorful block figure, we just pass in the query and the key as vectors. So this nomenclature could really be smaller letters because a smaller letter usually is a vector, a capital letter is a matrix. But we matrix multiply Q and V, then we scale them by some parameter, mask them optionally. So the masking was to do with text, you would hide a word. Softmax function, we've seen the softmax function in Torch softmax. So you see what we're doing here? We're trying to just map everything that you find in a paper to some sort of code. There's PyTorch's softmax. And then we take the output of this series of functions here on the query and the key and do another matrix multiplication on the value. There's the scaled dot product attention. And then for multi-head attention, we do the exact same thing, scaled dot product attention. We put this into here, except we do it across multiple other dimensions. So we add a dimension here for depth. So if you'd like to read more about this, I'd encourage you to jump into the paper. Attention is all you need. It may take you a few times, but you can also search attention explained. One of my favorites is J. Alamar. I've linked this in the book version of the course, PyTorch paper replicating. So the illustrated transformer. So if we look attention, what do we have? So self-attention layer, feed forward, we've got colorful blocks, we're encoding, self-attention at a high level. So previously, this is a great diagram. When attention was introduced, it was for text. And so the idea of self-attention is if we input a vector and say our vector was a series of words, the whole idea of self-attention is which words should pay attention to each other. As in, if you were to read the sentence, the animal didn't cross the street because it was too tired. So the word it, what does the word it relate to? In this sentence, the word it, because it was too tired, relates to the animal most. So this is why this is the darker color here. Whereas it doesn't really relate to the words because. You see how because is faint here? Now, we want to replicate this same paradigm, but with images. So what do we have right now? So if we go back, let's go to figure 1. We have, I'm just going to zoom in a little bit. We have turned our image into a linear projection of flattened patches. So you could imagine this as a series of tokens or a series of words in a string. So we've essentially turned our image into a sequence of words. Now we want to use the self-attention mechanism or the multi-head attention mechanism so that our patch embeddings know which patch, so each patch knows which patch to pay attention to on a high level. So is this patch significantly related to this patch? Or is this patch significantly related to this patch? Or this patch to this patch? Well, for us, we can quite clearly see that all the patches are related. But the whole idea is that we want this attention mechanism to learn which patch should be most related to another patch. We don't want to have to define that in programmatic rules. So we want this relationship to be learned and this representation to be learned. That's why we incorporate it in a neural network. So a fair bit going on there, but if we jump back to the keynote, we can see what's happening here. So we have multi-head self-attention from the paper Attention is All You Need, originally introduced for text to pass in query, key, and value to go through a series of equations here. We pass in the query, key, and value equals something. Then we calculate attention by passing in the values here to a softmax formula. We can do that with pure PyTorch if we wanted to. We take the dot product of the query and the key transposed. Then we divide it by, where does D come from? Well, D is our embedding dimension. So we scale it, that's scale dot product attention. Then we take the output A and multiply it with V. So what these series of equations have done is if we go back to the paper Attention is All You Need, a little extension here is that if you wanted to map that, we've just replicated this. In these equations in Appendix A, we'll just go here, Appendix A. So the transformer encoder consists of alternating layers of multi-head self-attention, MSA, see Appendix A. We've got 3 equations here. These 3 equations, and then subsequently this one, is exactly from Attention is All You Need. So we've got this, scale dot product attention, which is these 3 steps here. And then we've got multi-head attention, which is these steps here. But if we wanted to implement multi-head self-attention in PyTorch, well, of course, we could replicate each one of these equations line by line. But the beautiful thing about PyTorch is that if we look up PyTorch multi-head attention, we've got it here in a PyTorch layer. So it takes in KQV, which is what we've already seen. Now you might be wondering what KQV is. Well, the whole idea of self-attention, do we have the word self here? Self-attention is that, this is what tripped me up a bit. The query, key, and value are all instances of the same vector. So that's where the idea of self-attention comes from. So if we go back to this diagram here for text, the self-attention mechanism is asking the question, how much should a given sequence pay attention to itself? Do you see what I mean here? The animal is paying attention to the word it. Now we want to replicate this but with image patches, hence self-attention, of a given sequence. So in our case, a sequence of image patches, or in this case, words. Which word or which image patch should pay most attention to which other word or image patch in the same sequence? So it'll take a while to sort of get your head around this, but that's the whole crux of self-attention. And we can implement it with a PyTorch layer here. So before this video gets too long, we're going to start to write some code in the next video. So I'm just going to put this here, this heading here. My challenge to you is to do what we've just done, but the exact same thing for the layer norm layer. So equation 2, we'll call it multi-head self-attention. This will make a lot more sense once we see it in code. So the MSA block. So before we go to the next video, one final challenge is see if you can do what we've just done for the norm layer. So look up what is layer norm and then layer norm in PyTorch. I'll see you in the next video. Friends, welcome back. In the last video, we covered a high-level overview of multi-head self-attention, but we also covered a fair bit of ground. So let's just quickly summarize. So multi-head self-attention, the whole premise of it is which part of a sequence should pay the most attention to itself, hence self-attention. And so in our case, we have a series of embedded image patches, which patch significantly relates to another patch. And the reason why we've incorporated this into a neural network is because we can look at a patch and know that it's sort of related to another patch, but we want this to be learned. So we want our neural network, so our VIT, to learn this relationship / representation. Because if it learns the relationship between patches, what has it inherently learned? Well, it hopefully learned a good representation of what's inside an image. And if we wanted to replicate multi-head attention, we can take this layer from PyTorch and go into here. To replicate MSA in PyTorch, we can use this. And I issued you the challenge of checking out the same thing of what we've just done, but for layer norm. So if we jump back up to equation 2, which is what we're working on replicating, we're going to start writing code very shortly, don't you worry. So there's a lot of details in this paper. Here we go. So we've sort of covered MSA. We're going to see it in practice. That'll make a lot more sense. Now we've got layer norm. But before we jump into layer norm, there's just one more thing I'll just show you here. The reason why there's 3 arrows is because we've got Q, K, V. So we'll see this when we implement it, but this is query key value. Query key value. And these are 3 instances of the output of the norm layer. So just 3 instances of we pass our embedding patch, let's call that X, into the norm layer. We're just going to Q, K, and V is going to be X, X, X. So if we look at this, what do we have in PyTorch? What does it take as input? If we come down to here, in the forward method, it takes in a query, key, and value. We'll see this when we implement it, but that is from here, query, key, value, scale, doc, product, attention. And then if we come back to the keynote, we have query, key, value. Just realign it to here, query, key, value. Query embeddings, key embeddings, value embeddings. Beautiful. So let's come back. What were we up to? So we have layer norm. So layer norm equals, what did you find when we researched layer norm? What is layer norm? Understanding and improving layer normalization. There we go. Layer norm in PyTorch. Look at all these resources we have. So what does this say? Layer normalization, layer norm, is a technique to normalize the distributions of intermediate layers. It enables smoother gradients. Beautiful, that's what we want. Faster training and better generalization accuracy. I'm just going to copy this straight in here. So if we go here, layer norm equals this. And the way I like to think about normalization equals, so we want to make everything have, so when it says distribution, normalize, we want to make everything have the same mean and same standard deviation. And then if we look up layer norm in PyTorch, what do we have? So applies layer normalization over a mini batch of inputs as described in the paper. The paper is going to link us to here. And the mean and standard deviation are calculated over the last D dimensions. Where is D in our replication so far? Where D is the dimension of normalized shape. So let's just bring this into here. We're going to tie all of this together with code in 1 minute. In PyTorch equals this. So normalizes values over D dimension. In our case, the D dimension is the embedding dimension. Oh, I love it when pieces of the puzzle start to fall together. And so if we want to look at the embedding dimension, this is our layer norm here. This is C in the case of the color channels. When we output from the convolution layer, what are we projecting to? Our out channels of our convolution layer and our patch embedding goes to 768 or our D dimension. So we're going to normalize across our embedding dimension. Now, how is that going to help? So we can get out of a few things here. What is layer norm? If you want to research more, please feel free to do so. We're going to focus on coding this out. If in doubt, code it out. So when we normalize along the embedding dimension, it's like making all of the stairs in a staircase the same size. And now this is my little analogy to sort of explain normalization and how I understand it in many different cases. So let's find an image of a staircase. So you can think of, where's a good image? Here we go. So imagine you're trying to walk down these stairs. So that's what gradient descent does, right? But it tries to get to the bottom of a loss curve. We want a loss curve. Gradient descent is trying to get to the bottom of a loss curve. What do we have gradient descent here? Gradient descent. Yeah, there we go. We're trying to get to the bottom. So this is what we're trying to do with the staircase. But imagine each one of these stairs is a sample in your data set. So if you were walking down this staircase, but you had the stairs were all different heights, and they were all different weird like squiggly shapes like this, and each step was a different width, so it all just had different parameters. You would find it quite hard to walk down those steps quite quickly, wouldn't you? However, if we normalized the steps, so made sure that they had the same height and the same width, or in our case, they had the same mean and same standard deviation across the embedding dimension, you could walk down those steps pretty quickly. So you wouldn't really have to think. So that's where layer normalization comes into play, is that layer normalization is a technique to normalize the distributions of intermediate layers. So if we normalize the distribution over our embedding dimension, in other words, make sure all of our samples have the same mean and same standard deviation, or in the stairs analogy, make sure all of the steps have the same width and same height, well, not only can you walk down the stairs faster, you can train faster in terms of your gradients. And you can generalize better because instead of thinking about each sample or each step and you have to adjust for each step, you can generalize because you can just walk down the steps because you know that they're going to be the same height and width. So we've covered a fair few complex concepts quite quickly here. And I've definitely linked a whole bunch of resources in the book version to learn more about it. And I know I said we were going to start coding in this video, but to prevent this one from getting too long, let's start coding in the next video. In fact, with what we've covered, you might actually be able to do it yourself. We've got a layer for multi-head attention, and we've got a layer for layer norm. So how about we start off by creating a class called multi-head self-attention block, nn.module. So we've got a class there. How about you give it a go at initializing it and then just implement a multi-head self-attention layer using PyTorch, and the same thing with the layer norm. And in the forward method, we come back to the figure 1. In the forward method of your class, just pass the embedded patches through, or X, through the norm layer and then through the multi-head attention layer. Give that a go, try it out, and we'll do it together in the next video. I'll see you there. Welcome back. Over the last couple of videos, we've been breaking down equation 2, or the MSA block, which is if we jump into here, this little section there, and equation 2. And we learned that equation 2 is actually comprised of a few other equations that were introduced in various papers, such as attention is all you need, which again was by a team of researchers, and layer norm was itself introduced in a research paper. So it's understandable if you're not quite sure what these actually do to begin with, because we've only covered them very briefly. So if you'd like to learn more, there's resources in the book. Otherwise, you can definitely search it up. But now it's time for us to start writing code. So let's just write a doc string here. I issued you the challenge in the last video to give it a go and see if you can create a multi-head self-attention block. I trust you gave it a shot, but let's now do it together, hey? So creates a multi-head self-attention block, which is MSA block for short. So if you weren't quite sure like what KQV means in multi-head self-attention, might make a little bit more sense once we code it out. You know the motto, if in doubt, code it out. So to begin with, we're going to initialize it. Now we need an embedding dimension here with 768, and then we need a number of heads parameter, which is going to be an int. This will be the number of self-attention heads. So I'll write this down here, heads from table 1, and this is embedding, or the hidden size D, that is, hidden size D, embedding dimension. We already know that from the parameter name. from table 1 for vit base. And I'll just write here as well, this is for vit base. And we'll go down here. We also need a parameter attention dropout. This is a little bit hidden in the paper, but nothing you can't find with a quick little search. So if you search for dropout and label smoothing, dropout, we actually find that there's no dropout used with the attention. So we kind of had to wait all the way to Appendix B to find this out. So as I said, papers are just treasure trails of different information. Dropout, when used, is applied after every dense layer, which is in our case going to be within our MLP layers or our linear layers, or dense layer is another word for, there's actually like 4 or 5 different names for a dense layer. You could call it fully connected, you could call it linear, you could call it feed forward or something like that, except for the KQV projections. So this means dropout, when used, is applied for every dense layer except for the KQV projections. Now, where have we seen KQV projections? We've seen it here. KQV. We haven't seen this in, QKV. It's quite hard for me to read that. QKV projections. So that means we're not going to use dropout in our attention layers, according to the paper. And directly after adding the positional to patch embeddings. Oh, we haven't done that yet. We might have to do that later on when we create the full VIT architecture. But let's not stop there. We've got embedding dimension, number of heads. What is number of heads? Well, this is the H dimension over here. When we say multi-head attention, there's just regular attention, scaled dot product attention. Multi-head attention splits this equation across multiple dimensions, hopefully giving it more learning opportunities. And I say hopefully because a lot of this stuff is sort of, you're thinking that it will work, and then you kind of have to test it to see if it does. You can theorize it that it will, but until you actually try it out and then publish a research paper with your results and going, hey, this actually improves things, you don't really know. So that's the H dimension here, number of heads. And if we jump back into the paper, a lot of jumping around here, but this is kind of what you have to do to replicate a paper, is that we have vit base, attention heads is 12. And then we're coding it in such a way that if we wanted to upgrade it to 16 for the other model variants, we could definitely do that. Whew. So we've initialized our MSA block. What do we do next? Well, let's create the norm layer, which is, if we jump back to the keynote, which is this one, we're going to create the norm layer first, layer norm, ln, and we can do that in PyTorch using what? Layer norm. So our layer norm layer is going to do what? It's going to normalize our input values across the dimension that we pass it. The normalized shape equals embedding dim. How do we know that? Well, if we go to the PyTorch documentation for layer norm, do you see what we're doing here? We're slowly breaking it down, and I've said this a few times now, we're breaking the architecture down into single layers as much as we can. So norm is just one layer in PyTorch. Applies layer normalization over a mini batch of inputs as described in the original paper. Here's the equation that it does. So the output of the layer normalization layer is this, x minus all this jazz. I can't even read most of these. I like to learn things with code instead of trying to read math symbols. The mean and standard deviation are calculated over the last d dimensions, where d is the dimension of normalized shape. So normalized shape here. We've got epsilon value. I think that is mentioned in the paper as well. So if we go epsilon, I don't think it is, maybe. So this is the thing, right? A lot of hyperparameters aren't actually mentioned, but they're just inferred. So if you find that, please let me know. But what a lot of layers often have by default is a pretty good value to begin with. So we're just going to leave this as it is. Let's jump back into here. There's our layer norm. And now let's create the multi-head attention layer. Now you might have tried this out yourself. So MSA, multi-head self-attention layer is self.multi-head attention. We could call this whatever we want, really. I'm just calling it that. Now we're going to do nn. multi-head attention straight from PyTorch. So thank you, PyTorch team, for implementing this. I was getting ahead of myself. So this takes an input parameter of embedding or embed dim, and I've called ours embedding dim, which is this. And then we take num heads, which is going to be number of multi-headed attention. That's where the H dimension comes into here. Then what else do we need? Well, there's a dropout parameter here. Now, the paper doesn't mention using dropout on the attention layers, but I've put it in here anyway, so if we did want to try it out later on, we can do so. And then there's one final parameter, which is batch first, and I'm going to set that equal to true. Now, where could we find out what that parameter does? Of course, in the documentation. So if we come here, we've got embed dim. So what's our embedding dimension? How many attention heads do we want? What's the dropout? And then a whole bunch of other parameters that I'll let you research. And then we have batch first, which is false by default. So if we come down here, so if true, then the input and output tensors are provided as batch, sequence, feature. Is that what we've done? So I just want to copy this because this is another little confusing thing about machine learning and deep learning is, again, different names for the same thing. The default is false, so the sequence comes first, then the batch, then the feature. So what is our input to block 2, to the MSA block? We've embedded our patches, and we're going to put the output here of this equation into this equation. So what is the shape? We're back to input and output shapes once again. If we have a look here, our patch and position embedding shape is going to go into this block. So what is the dimensionality here? We have batch, number of patches, embedding dimension, or in PyTorch terminologies, if we come back here, batch, sequence, feature. So let me just write this down. So I'm going to write, is the batch first? Question mark. Batch, sequence, feature, which in our case is batch. And then we have number of patches, which is our sequence of patch embeddings. And then feature is our embedding dimension. So sequence, short or SEQ, short for sequence. In our case, we have a number of patches that are in a sequence, and feature, which is another word for, say, learnable features. So we want learnable features of a sequence. And in our case, we're calling that embedding dimension. So there's some terminology there for you. Now, if we keep going, we've got 2 layers. What do we have to do next? Once we've instantiated some layers, we have to define a forward method so that we can say, how does the computation flow through these layers? So here's another little tricky part. But if we jump back, we've got embedded patches, X comes in, goes through the normalization layer. That's pretty straightforward. But then here is the multi-head attention part. This is a little bit tricky. But we know that it's going to take in query, key, and value. So if we jump into the documentation, the forward method takes in a query, key, and value. Now the tricky part here is that all of these are the same thing. That's where self-attention comes. Remember when we described self-attention or multi-head self-attention? Is which part of an input sequence should pay the most attention to itself? We're not going to define this. The network is going to learn this on its own. So we just pass in 3 versions of the sequence as the query, key, and value. And by going through these equations, and if we go to Appendix A, we can see here, by the query, key, and value, going through all of these steps here, our network is going to learn which part of a sequence should pay the most attention to itself. And inherently, if it learns that representation, or if it learns which sequence should pay the most attention to itself, hopefully it learns a good representation. So let's see what this looks like in code. We're going to do the norm layer first, layer norm, just pass X through that. And then we're going to go here, attention output. And I'm going to do an underscore here because the PyTorch attention layer outputs an attention output and attention output weights. So we don't actually need the weights. We just want the activations out of the layer. So I'll let you read more into what the outputs of the weights will do if you'd like. So in this example, they're creating a multi-headed tension layer with embed dim and number of heads. And this is just showing how to get the output. You pass in a query, key, and value, which is exactly in line with what the paper is saying here. 3 heads or 3 inputs, query, key, value, or QKV. So let's jump in, go back to code. So I'm going to take our multi-head self-attention layer. So multi-head attention. Oh no. Multi-head attention. That's Codelab saying, hey Daniel, you've spent too much time explaining and not coding. I know, you're right. So there's a query, key, and value is equal to X. And do we need the weights? I'm going to say false because that is that underscore there. And if we jump back in there, it's going to output the attention weights. That is that parameter there. If specified returns attention output weights in addition to the attention outputs, default true. I'm setting that to false. Okay, now let's return the attention output. So have we just replicated equation 2? So a fair bit of explaining there, or 2 videos worth of explaining, maybe more, but we've just replicated the entire MSA block in 24 lines of code, and we could actually do less if we got rid of the comments. So that, my friends, is equation 2. We go right back up. A lot of information here. But we've just replicated equation 2. So we've got MSA wrapping the output of a layer norm that takes the input of a previous layer. Now, there is one part we haven't included though. That's the skip connection here. So I want you to have a think about how we could put the skip connection into this, but we're going to use that later on. And you'll see when we create the overall transformer encoder, which is this here. When we create this, we'll implement the skip connection there. But what we've done is now we've got this and this in a reusable piece of code. So in the next video, we're going to practice using this layer and we'll see what the inputs and outputs look like. So have a think about how we could create the residual connection. And if you want to jump ahead, create an instance of this block and then pass our patch embedding through it and see what happens. I'll see you in the next video. Welcome back. Now, we've come a long way. We've replicated equation 1 and equation 2 so far. We've got 2 more to go, then we can put it all together and create the vision transformer. But let's not get ahead of ourselves. First, we want to test our MSA block. So we'll create an instance of our MSA block, which combines multi-head self-attention and a layer norm, and then we will pass our patch image through it. So multi-head self-attention block. We're just going to set it equal to our class that we created above. We're translating the paper into reusable PyTorch code. So multi-head self-attention block, and then we have a few inputs here. We need the embedding dimension. We don't necessarily have to set this, of course, because we have a default value. Number of heads, which is the number of attention heads. We'll set that to 12. We could increase that if we wanted to build a larger vision transformer architecture, but we're going to stick with VIT base. And then we set the attention dropout to 0. We keep going. Let's now pass the patch and position image embedding sequence, that is, sequence through our MSA block. And we'll go patched image through MSA block. A little bit of a creative variable name there. And I'm just going to scroll up. So this is in the center of my page there. So multi-head self-attention block. You might have already tried this out. We've got a typo, classic, multi-head. And then we'll pass it in the patch and position embedding. Is that all it's called? Yeah. So this is what we created before. We turned our image tensor into a patch and position embedding, just like in the figure. So what we're doing now is we're passing this, our embedded patches, through these 2 layers. And mind you, we're missing this skip connection here, but we're going to code that later on when we make the overall transformer encoder. So we jump back into Colab. And let's see what happens here. So print F, let's get input shape of MSA block and patch and position embedding shape. You know I love to always find out the input and output shapes of different layers. Output shape of MSA block, which is just going to be the patched image through MSA block dot shape. So let's see what happens here. Oh no, what's going on? Cannot assign module before init call. What have we done? Oh, I think I've forgotten super. Did you catch that? Super.init. I often forget that. But that's what coding's all about. Oh, look at that. It works. Our patched image through the MSA block works. So the input shape of the MSA block is 197,768, so our number of patches. And then what? The shape doesn't change. But that doesn't mean the values don't change. Oh, I've mistyped this as well. Block. Is that going to work? Oh, I've mistyped this as well. Okay, there we go. So even though the shape doesn't change, that doesn't mean the values haven't changed. So let's grab this. And we may see this as being almost incomprehensible because there's so many values here. But that's not up to us to decide. So you notice at the patch and position embedding, as it goes through the multi-head self-attention block, all the values get adjusted here. Now, to me, these values don't really make sense. But again, this is not for me to decipher. This is for our neural network to learn a representation of an image. And of course, these values are just going to be randomized, much like these are. Well, these are from an actual image, but these values are going to be randomized because, well, we've instantiated our layer here with random values and our neural network hasn't done any learning yet. So hopefully later on, these values, as our image goes through multiple layers of this MSA block, multiple transformer encoders, looks at multiple different samples of image, the representation that this patched image through the MSA block forms is a good quality representation. So with that being said, it looks like our MSA block is ready to go. How about we now move on to equation 3, or the MLP block. And now that you've seen how the MSA block is done, you might want to set a challenge for yourself to replicate what we've just done with the MLP block. I'll give you a hint. It's going to be very similar to what we've done here. But instead of a multi-head self-attention layer, you're going to create an MLP layer. So give that a shot, and I'll see you in the next video. We'll start to move towards replicating equation 3. Welcome back. Now, we're going to continue our momentum with replicating different equations from the paper. And we're up to the multi-layer perceptron block. Multi-layer perceptron, or MLP block. I'll call that MLP block for short. And so if we jump into the paper, this is the MLP block. So we've already done this. You might have given this one a shot here. It's very similar to this attention block or multi-head or MSA block, except instead of using multi-head attention, we use an MLP block or MLP layer. So let's jump into the keynote and get a little bit of an overview. Oh yeah, and here's a summary of what we've just done. We're turning figures or images, math, and text into reusable PyTorch code. So there's our layer norm layer, and then we create our multi-head attention layer, and then within this is the MSA block. We've already covered that. So now we're up to equation 3, the MLP block. So what do we want to do here? Well, we've got MLP, multi-layer perceptron, MLP block, and then if we draw some colorful lines, the transformer encoder consists of alternating layers of multi-head self-attention, MSA. We've already done that. Look at us go. And MLP blocks, equation 2 and 3. So alternating MSA and MLP blocks within the transformer encoder. layer norm, we've seen layer norm, is applied before every block, so just like here, and residual connections are after every block. So much like our MSA block has a residual connection, we haven't coded that just yet. The same thing is with our MLP block. And recall the residual connection is equivalent to adding the inputs to the outputs of a block. And that enables larger and deeper models because it prevents our gradients and weight updates from getting too small. So let's start to replicate this in code. Or what we might do actually is just explore the paper to find out what the MLP block is created. We know what layer norm is. Let's find out what the MLP block. So if we jump into 3.1, which describes an overview of the model, we've read here, equation 2 and 3, then there's one single line that describes the MLP. The MLP contains two layers with a GELU nonlinearity. So let's see what this looks like in pseudocode. We go here, I'll bold this, MLP is equal to, this is from section 3.1. So previously we may have defined an MLP. MLP is quite broad, equals a quite broad term for a layer or series of layers, or a block really, maybe a block, for a block with a series of layers. So layers can be multiple or even only one hidden layer. So we see here that the VIT paper has an MLP with two layers. So it's giving us that. And by layers, usually they mean fully connected. I'm just going to write this down because there's multiple different terms. Layers can mean fully connected, dense, linear, feed forward. All are often similar names for the same thing. In PyTorch, they're often called, this is torch nn.linear. So PyTorch calls them linear layers. And just for reference, in TensorFlow, which is another very popular deep learning framework, they might be called, I think it's tf.keras.layers, or maybe tf.keras.dense. So TensorFlow dense. TF keras layers dense. So that's different names for the same thing. So what is a GELU nonlinearity? Let's look that up. What is GELU nonlinearity? There we go, GELU explained. Okay, so the Gaussian error linear unit, or GELU, which is similar to ReLU, which we've used before, is an activation function. The GELU activation function is, I'm not actually sure where that is the standard Gaussian cumulative distribution function. The GELU nonlinearity weights inputs by their percentile rather than gates inputs by their sign, as in ReLUs. Consequently, the GELU can be thought of as a smoother ReLU. Okay, here we go. So the ReLU is this hard orange line, which we've seen before. So let's go ReLU nonlinear. What does that look like? So ReLU is this, it zeroes all the negative inputs. Then what happens with GELU is we give a little bit more space for some negative inputs to come in. It's a bit more smooth there. And then of course we've got ELU as well, which is different again. So this is the thing with a lot of activation functions. If we go into PyTorch activation functions, of course they implement different methods of how they work, but they all kind of do a similar overall process, is that they add in non-linearities. So instead of just being purely straight lines, we get some sort of non-linear line. And remember, machine learning, what can you draw with an infinite combination of straight and non-straight lines? Well, you can draw some pretty intricate patterns, can't you? So here we go. We can implement GELU with that. So let's bring this in. If in doubt, code it out. So GELU in PyTorch, there we go. And if we read the docs of what that does, applies the Gaussian area linear units function. Wonderful. So we've got the GELU function there. We've got this little gap here. for values that are negative. So we'll see how we can implement this in code. And in fact, we've already got the pieces of the puzzle here. How about we create it in pseudocode? So the pseudocode for this is going to be, this is where your challenge is going to come in. You'll notice I'm going to start issuing more and more challenges because I think our skills are getting pretty good, you know? So x equals, this is going to be the input to our MLP. So let's call this MLP, is going to be 2 layers with a Gelu nonlinearity. So we want x to go through linear, and then we want it to go through nonlinear, and then there's one piece of the puzzle we actually haven't coded here yet, drop out, linear, and then finally nonlinear. And then maybe drop out. Or actually, we'll have a look at the paper and see what they did. I think that'll be it. So linear contains 2 layers with a Gelu nonlinearity. So we've got our linear, nonlinear, dropout, linear, dropout. So I think that'll be the order, but dropout, we need to talk about this. Dropout, another one of those treasures. We're explaining a nonlinear paper in a very linear way. So dropout, let's go here. Dropout when used, we've touched on this before, is applied after every dense layer. And what did we say before? A dense layer is another word for a linear layer. So in PyTorch, we call them linear. In TensorFlow, you might call them dense or a fully connected layer. So we need dropout after our linear layers in our MLP. So give that a shot. I'm just going to copy this in here actually. There we go. Dropout. That's one of those treasures you kind of have to search for in the paper. So if we create a class here, we're going to call it MLP block, inherit from nn.module, and implement the MLP, implement dropout, and then of course in the forward method, you'll want to pass it through. If we go back to figure 1, you'll want to pass it through a norm and then through the MLP block and then return the output so we can create the residual connection later. So give that a go and we'll do it together in the next video. All right, put your hand up if you're ready to turn equation 3 into reusable PyTorch code. I've got my hand up. I trust you're doing the same. And I issued you the challenge in the last video of giving it a go. So well done if you did. And if you didn't, well, we're going to do it together right now, aren't we? So we need our initialization function and we need an embedding dimension parameter. So the transformer architecture keeps the same embedding dimension throughout. So we'll pass that in. Now we need a value for the hidden unit size of the MLP. And now this is something we didn't actually put in here. So well done if you found this out. We may have touched on it before. MLP number of hidden units equals, I think it's MLP size in table 1, which of course, if we jump into the paper, we have table 1, which is the MLP size for VIT base is 3072. So we'll set that as our default. And then of course, we're creating it in such a way that if we wanted to upscale our model variant, we could insert these sizes here. So let's jump back into there. I'll just keep going. So the integer here is going to be 3072. And then if we keep going, we want dropout. So where is the value for dropout? I kind of hinted at it here. This is in appendix B, but we want the value for dropout, another treasure of the paper, value for dropout, available in table 3. So if we go back, table 3, so hyperparameters for training. So if we're replicating VIT base 16 patch size, our dropout is going to be 0.1. So let's go back. We'll set that to default because that's going to come after our dense layer or our linear layer in our MLP. And then we're not going to forget super this time. Let's go super.init. And then what can we do? Well, we can create the norm layer. So we've done this before. norm layer, which is ln, and we'll go self.layerNorm equals nn.layerNorm, not normalized shape, equals the embedding dimension. Then we can create the MLP, which stands for multi-layer perceptron. And we read in the paper, section 3.1, is the MLP contains two layers with a GELU nonlinearity. And we know that from Appendix B, dropout when used is applied after every dense layer. So let's see how we might do this. So self.mlp equals, we're going to create it as a sequential. So a sequential is just a sequential series of layers. And the first one is going to be nn.linear, or dense layer, or fully connected layer. The input size here is going to be the embedding dimension. Then the output features is going to be our MLP size, which is from above. MLP size. Then we actually don't need another bracket after that, or another parameter. Then following nn.linear, what are we going to do? We're going to have our non-linear layer, which is nn.GELU, or GELU, however you want to pronounce it, contains two layers with a GELU nonlinearity. So we've got one layer so far, a nonlinearity, and now we need dropout. So nn.dropout, p equals dropout. And then we're going to add another linear layer. And the in features of this one are going to be what? Well, this needs to be MLP size. Why is that? Is because we need our in features of a subsequent linear layer to line up with the output features size of a previous layer. Otherwise, we'll get shape mismatches. And now the output feature size of this is we're going to project back to our embedding dimension. So what happens here is that we get in features, which is the size of embedding dim. We use this layer to project to a larger size to hopefully capture some more information. So the larger size is there, and then we squeeze it back to the embedding dimension. And now whether this works or not, well, hey, hopefully the authors of the paper did this for a reason. And in fact, if you look at the results, if we go to results, it turns out they got fairly good results with architecture design. Comparison to state of the art. Yeah, here we go. Pretty darn good results. So let's jump back into here. And then we'll finish off with nn.dropout. P equals dropout. So that's just going to get the parameter there. And so now we have the layer norm and we have the multi-layer perceptron. So if we jump to the keynote, what have we done? We've created a variable for this layer and we've created a variable for this layer. And so to put them together, what do we do? Well, we define a forward method. So we'll jump back to Colab. So def forward self, and we take in x. What are we going to do here? Well, we're just going to pass it through x equals self.layerNorm, x. Then we go x equals self.mlp, pass the output of the layer norm through our MLP, and then we can just return x. And we could also code this the same way, which is, or we could even go, I'll just do this all in one hit, return, I'll comment this out so we don't get errors though, return self.mlp, self.layerNorm over x. And that will probably also benefit from operator fusion, but this looks exactly, self-MLP, looks exactly like what we've got there, except of course for the residual connection. Now, I want you to have a think about how we might implement this if we wanted to, but we're going to do that when we create the transformer encoder. So with that being said, let's just write this, same as above. Let's test it out. Let's see what happens when we pass a tensor through this layer. So we'll go create an instance of MLP block. We'll call this MLP block. I'm just going to make this a little bit in the center of the screen. I always love doing a test forward pass. If in doubt, run the code. So embedding dimension is what? 768. We don't necessarily need to put that in because we've got that as default. Same thing here, but we're putting them in anyway. Both those values are from table 1, and dropout is from table 3. So we've got our MLP block. So now we're going to pass the output of the MSA block through MLP block. So we'll go patched image through MLP block equals MLP block, and then we'll go patched image through MSA block. Now, technically this is not the right order of doing things because we haven't yet included our residual connections. So if we go here, what we're doing is we're taking the output of this block that we coded up in the last few videos, and we haven't got the residual connection yet, but we're just seeing if the output shape of this layer can still pass through this block here. So this is not 100% correct, but we're just trying out, we're checking the input and output shapes. So this patched image through MSA block is the variable that we got up here, which is the output of equation 2. So if we go down here, let's go print f equals input shape of MLP block. So we're going to go patched image through MSA block dot shape, and then we'll go print output shape of MSA block, and then we go patched image through MLP block dot shape. Now, what do you reckon is going to happen? Oh, well, we get the same input and output shape, but did the variables change? Let's have a look. So we've got that there, and we'll pass in the input. We'll just check the input. So don't worry too much if your values are different to mine. These are all going to be randomized, but just notice what's changed here. Have the values changed as they go through the MLP block? Yes, they have. So you can see almost all of the values here are different to the output. So what is going on here? We've replicated figure 1. Well, most of figure 1. We've got MSA block and an MLP block, and we're passing through our embedded image patches through those. And they're getting manipulated by the various equations that are behind the scenes of these colored blocks. And so hopefully, we're going to create more stacks of these in a second as we build the entire transformer encoder. Hopefully, behind the scenes, our vision transformer is forming a learned representation of an image. Now, of course, the representation probably doesn't mean much because it's all randomized and our model hasn't been training. But hopefully, after it goes through a series of training iterations, this representation really well represents, in our model's eyes that is, really well represents our single input image. Now, we want that to be the case across all of our training data set so that we can use that learned representation to predict on unseen data, aka data from the test data set, or data that our model has never seen, a la custom images. So we've covered a fair bit here, but now we've got all the pieces of the puzzle to start replicating the entire transformer encoder. So you might want to give it a shot to create a PyTorch class and stack together equations 2 and 3. We've got the PyTorch code to do that. And then add in the residual connections. We haven't covered exactly how to do that, but I think with what we've covered so far, you could definitely give it a shot. So try that out, create a PyTorch class for the transformer encoder. And I'll see you in the next video. Welcome back. In the last video, we finished off coding the MLP block. Oh, excuse me. We got a little bit of a typo here. This should be MLP block. Beautiful. But where were we? So we've now done equation 1, equation 2, and equation 3 in reusable PyTorch code. So what's next? Well, it's time we put together equation 2 and 3 to create the transformer encoder. Creating the transformer encoder. The transformer encoder is a combination of alternating blocks of MSA and MLP. Now, if we jump into the keynote, we can get a little bit of a colorful overview. There's equation 3, And if we just map that to code, this is what we did in the last video. We've got our MLP layer, which is here. We create it by using alternating layers of linear and non-linear and put a dropout in between or after each of our linear layers. Then there's also a norm layer, which we created here using torch nn.layerNorm. And then we put it all together using a forward method. But there is still something missing from both of our MSA and MLP blocks, and that is the residual connection. Now, you might want to think about how we could implement a residual connection in the forward method here, in both the MLP and the MSA block, or we could implement it when we create the overall transformer encoder. So now let's map this. So if we have a transformer encoder, which is alternating layers of equation 2 and 3. So if we see here, this is from section 3.1 of the paper. The transformer encoder consists of alternating layers of multi-head self-attention, MSA, so this block here, equation 2, which we've already turned into a code block, and MLP blocks, which is of course equation 3, which is what we turned into a code block in the last video. Do we have residual connections here? I haven't highlighted it, but we have this line here, which says layer norm is applied before every block and residual connections after every block. So let's go back to the Colab. We'll just write here. So this is equation 2. And this is equation 3. And we'll go here. And there are residual connections between each block. So we'll just make some definitions here. So if you want to know what an encoder is, you could look this up. What is an encoder in machine learning? You might be able to guess here. Encoder-decoder models allows for a process in which a machine learning model generates a sentence describing an image. So that's one use case of it. What is an encoder-decoder in deep learning? Encoder-decoder, what and why? Autoencoder. Machine translation, encoder-decoder model. Encoder and decoder. So we could go through all of those, or we can sort of infer what's happening here. So if we pass in our embedded patches and it goes into a transformer encoder, what is happening? Well, first and foremost, we've turned our sequence of image patches into a learnable representation or an embedding, and then it's going through this encoder layer multiple times to further learn that representation. So we could think of an encoder is turn a sequence into learnable representation. And then subsequently, what do you think a decoder could be? Well, it would be go from learned representation back to some sort of sequence. So if we go to Google Translate, one of the most common use cases, so we say machine learning is amazing, and we translate that into maybe Japanese. So Kikai gakushu wa sugui. That may be wrong, but what's happening here? Behind the scenes, if a machine learning algorithm is running this, well, the encoder will turn this into numbers, and then the decoder will deconstruct those numbers into another sequence. So essentially, we've got sequence to sequence. So sec to sec, or sequence to sequence, sec to sec, here we go, is usually a model used in family of machine learning approaches used for natural language processing. But this is where the idea of an encoder-decoder comes from. Recall that the original transformer paper was introduced for text problems. So attention is all you need. So that's where the name transformer encoder comes from. And what are we dealing with? Well, we're dealing with a sequence of image patches. So the transformer encoder is to turn that sequence into a more learnable representation. And then the decoder, well, we don't have a decoder in this architecture, would be to take the output of the encoder. You could probably actually call the MLP head our decoder, but it's not officially called a decoder here. But the decoder would be to translate it into another sequence rather than just a class name. But because we're focused on image classification, our output goal is a single class name rather than a sequence. So if we go back here, one more thing we're going to define, residual connections equals add a layers input to its subsequent output. This enables the creation of deeper networks, and it prevents weights from getting too small. So that's the idea of residual connections, encoder and decoder. And now if we do it in pseudocode, and of course you can research all of these different topics. Let's create it in Python, and we've got our transformer encoder. So what are we going to have as our input? Let's just call it X input. Nice and simple, the output of our embedding patches or our sequence of embedded patches. And then we're going to, I'm not going to set it equal actually, we'll pass it through an MSA block, which is equation 2. Then we will create the MSA block output, and we will also add, this is the residual connection, plus X input. And then we will go through the MLP block. So we're passing this here through the MLP block, and then we'll pass to the next section, the MLP block output, plus the MSA block output, plus X input to the next. So really this is just, I've done it like this because it's in pseudocode, but really this is going to be a single vector. So let's see what that looks like in Python or PyTorch code. So we create a class here, and I might call this the transformer, just nice and simple, nn.module, transformer encoder, nn.module. So actually, before we start to code it out, I think this is something you can handle. We might call this block, because we've been saying block a lot as well. So see if you can create the transformer encoder block using a combination of MLP block and multi-head self-attention block and residual connections. So what you'll be trying to replicate is, if you come into here, you'll want a forward method that passes an input through the MSA block, adds the input to it, and then same thing again, but with the MLP block. So give that a go, and then we'll create a transformer encoder together in the next video.